Good morning. Yeah, so it's been a pretty calm evening and morning. Everybody have a good time at the party last night? I'm glad you did. Wow. I don't really have any prepared words because anything that I would have had really doesn't make any sense now. I assume you're here, so you kind of have an idea of what's been going on. So I'll just quickly update you. We had a underground fire in downtown Portland, which affected large swaths of the area. Of course, our primary venue was affected by that, but it's hard to do these Tuesday morning things without getting emotional. We have an amazing group of volunteers and staffers and everybody that pitched in and put this together under the less than optimal circumstances. I wanted to shout out some names. If you hear your name, please stand up and stay standing up until we're done. Andrew Ferbert, Brian Balderston, Matthew Case, Robert Wyatt, Pete Wilkins, Brad Lotsky, Elizabeth, Anessa, and PCS staff, Jeremy Katz, Ed Muller, Jeremy Brinkley, Bo Blanton, Kevin Stone, Pete Silva, Aaron Bento, Derek Britson, Jack Neely. No, I'm not just reading from the attendee list. Caleb Haley, Jordan Haley, Molly Shelton, Danielle Hildreth, Ryan McKern, Luke Caney's, if you're here, the folks from Logsy, who I don't have your names, the team at Searle Video, the remote folks at Matt Ellis and his team at Cloudability, and folks at Puppet. If we could please give them a round of applause. Thank you, everybody. I don't want to say it's unprecedented to have a conference outage and move it in less than 12 hours, but let's just say it's going to make for a very interesting post-mortem and talk at the next event. Anyways, I've taken enough time. Again, just a quick thank you to everybody who's been understanding, cooperative, assistive. Yes, sorry. All right. Oh, yes, thank you. Logistics. So bathrooms, the primary bathrooms in this space, which is pure space, are directly behind this screen. So you can just get around it from the side here. There are also restrooms in flex space, which is just go through the stairs, take a right, and there's restrooms back there. I believe there's 3 or 4 men's, a couple, 2 or 3 women's. So I would ask, there's actually there's a family room. If we could please keep that for the ladies, if you don't mind. We have some refreshments here. We have Nosa Familia bringing their coffee over at approximately 10:15, so we'll have that. If you need power, I think we have some strips to the back of the room. I know a lot of you missed out on power last night, so please try to recharge when you can. Otherwise, we're going to try and maintain our schedule as much as possible today. So that said, kicking off day 2 of Monitorama. Very excited to bring, Betsy Nichols, who's is architect, chief scientist, just general big brain at Nuitive. So we're very happy to bring her. Please give her a very large, great round of applause. Thank you. Thank you very much, Betsy.
Oh, no problem. Thank you. Yes, good morning, Monitorama. This has been quite a morning, hasn't it? And quite an evening before. I actually managed to walk into an elevator at exactly the wrong moment last night. I discovered there's a protocol. It's very interesting. I survived, as you can see. Some anomalies, I guess, are easier to detect than others. So anyway, getting right down to it, I guess, the talk that I want to do this morning, the 30 minutes, is on the subject of anomalies and alerts and how we can do better with them. I think that, I guess I could start off with an assertion that monitoring systems today probably could do better, and they should do better. And what I want to do is start a conversation about how that might happen. So what I want to do is sort of take this in 3 acts to begin with, I guess. Act number 1 is just sort of looking at this current state of the art with respect to alerting and monitoring and discovering anomalies. And then look at the pain that has ensued and do some analysis on the pain to see what we can do to potentially find some relief, and then discuss some possibilities for relief. As a bonus, I got a use case at the end, but I'm not sure I'll have time for it. We'll see. Okay. So let's look at the now. This is sort of your typical workflow. It starts off with data coming in across a fire hose, typically. There's an engine that does some analysis, and then there's an alert that's issued appropriately at the end, ideally anyway. I think one of the problems that occurs is in the middle. The issue is that when anomalies are detected, it's sort of part of the same atomic operation to issue an alert. And I think that those two things, the detection part and the action decision part, those need to be separated. So that's what we're going to talk about. As a result of this fact that the two are not separated, you end up effectively equating anomalies and alerts, which essentially means every time you detect an anomaly, you get an alert, and the alert's quality suffers as a result. So there are bad ideas, and then there are worse ideas. Taking your cat into your bathtub to give it a bath is probably a much worse idea, so we shouldn't be too hard on ourselves. Bad ideas can also be corrected. So moving right along, let's look at the pain that this equating anomalies and alerts can cause us. One area that's a problem, and yesterday's talks were great, and a lot of the talks raised the issue of alarm fatigue or alert fatigue. By the way, if I say alert or I say alarm in this talk, as far as I'm concerned, they're the same. You could differentiate them, but at least as far as this talk goes, they're the same. So let's look at alert fatigue and sort of the root causes behind it. Well, basically you can raise alerts under various circumstances. You can have a problem or not a problem, and then you can raise the alert or not raise the alert, depending, and the quality of the alert is kind of judged by the correlation between those two facts. So if you have a good situation, if you have a problem and you get an alert, that's good. If there's no problem and there's no alert, that's a true negative. That's what TN stands for there. There's a true negative, and that's good too. So true positives and true negatives are good. Bad is when you have a problem and you get an alert. No problem, excuse me. Bad is when you have no problem and you get an alert. That's a false positive. And that's otherwise known as noise, and that is certainly a major contributor to alert fatigue. The really ugly situation, though, is where you have a problem and the monitoring system doesn't tell you about it. That's the worst case. I mean, why do you have a system if it's missing things, right? So that's one way to sort of judge the quality of alerts and begin to understand where the pain comes from. So the sort of first thing to ask is, if you're going to stick with this notion of equating alarms with alerts, or alarms with anomalies, or alerts with anomalies, you're going to get alert fatigue, and you're also, the anomalies are going to be contributors to the alert fatigue. And that's a problem, because anomalies can be good anomalies. If you go to the racetrack and you win $2 million, that's an anomaly, right? But it's not worthy of an alert. So equating anomalies and alerts is a problem, and if you think about the sort of the basic nature of an anomaly, is that it's a probabilistically rare event. And once you recognize that, you can begin to answer the question of how many anomalies you really should expect, and therefore how many alerts you really should expect, right? So looking at just a simple sort of common probability density function. This is the Gaussian distribution, and you could think of it as a smooth histogram. I love the fact that histograms came up so much yesterday. It's very valuable to understand how the information that you're getting is distributed. And this is kind of a typical distribution. There are lots of other distributions, and everything I'm saying will apply equally well to other distributions. But just looking at this one, where the anomalies live is in the tails, right? And the question is what's the likelihood that you're going to see things in those tails? And in this particular graph, what we're showing is a possible, if you're looking, let's say, at a metric, just pick one metric, and you're looking at all the observations that you could see from that metric, then what the graph on the y-axis is showing is what the frequency is that you saw that particular observation, right? You can express the observation in the units of the metric, or if you want to normalize and be able to compare sort of apples to oranges, what you can do is normalize and express what you're seeing in values of the metric as values in terms of units of distance from the mean, numbers of standard deviations from the mean. And what this graph is just showing is what percentage of observations you should expect to see at various different stages or at various different distances from the mean, right? So in the tail, if the tail is far enough out, the percentage really goes way down. And that's why it's called an anomaly. The anomalies live there, they're rare, and so they're unusual, right? So if you look at this, it's expressing a percentage of the total population of observations you've made. Well, taking a look at how many observations you might see, that's one thing that we don't lack for in monitoring, is we have sample sizes which are huge. The good news is you get statistical power. The bad news is that you get a lot of anomalies, which if you just go through some calculations, you'll see that if you take, for example, one metric, you're doing 1 minute observations, you'll get about 500,000 observations in a year, and you'll get about 1,440 observations in a day. That's for one metric. People were talking about monitoring systems that were managing millions of metrics. So the numbers really get large, right? With the length of the time series or the metric that you're managing, as well as the numbers of metrics. So in the case of CloudWatch, an EC2 has 14 metrics. So 14 times 1442, that's roughly 15,000 metrics a day, or 15,000 observations a day. So just looking back, looking at the, I gotta press that way, right? There. Taking the percentages that we showed in the earlier slide and applying them then to the total population, if you had 50,000 metrics, which is not a huge organization, certainly, if you had 50,000 metrics, you'd have approximately 5,000 observations that are 4 standard deviations away from the mean, which would reasonably be called anomalies. So in a shot, you're getting this 5,000 a day. Okay, now maybe 50,000 is too large for you. If you were to have that and make it 2,500 metrics, then that number the 5,000 would be cut in half, and you get 2,500 observations that could reasonably be called anomalies. So anomalies are actually very plentiful. I'm just showing my work here, if you're interested. Also, any mathy presentation should probably have some Greek letters, so there they are. Enjoy. Okay, so next slide. What did I just do? I just turned something off? So the next slide, what it says is that anomalies are plentiful. Yes! These last few days have had a few anomalies, haven't they? Thank you, and recovery. Quick recovery. Most impressive, thank you. This group, I must say, I have to thank everybody who managed to make this happen. It's incredible, it really is. So anyway, this may motivate you to sort of break the equality. Anomalies and alerts, they shouldn't really be equal. So let's try to break that equality. Well, if you do that, then now you've got this pile of anomalies that we just discussed, right? Pile of anomalies. You've got to decide which ones that you want to alert on and which ones you don't want to alert on, and therein lies the rub. So another interesting point, I guess, just besides the fact that the little area where, the area where, in the tails, that's so full of anomalies that it's a mixture. Some are true positives, and some are false positives. And so, if you choose to just sort of take the easy way out and say, if it's an anomaly, I'll alert on it, well, you're going to get flooded. And if you start to back off and say, well, I'm just going to only alert on a subset of these, then you're risking a false negative, which is the absolute ugliest type of circumstance. So these trade-offs they have consequences and they can be dire. So, okay. How do you look for the needles in the haystack, so to speak, where the true positives are, and only alert on those? That's kind of the problem. So here's the statistical approach to answering that question. So let's just suppose that you had a supervised learning circumstance, perhaps, where you have been observing one metric for a long time, and you've kept track of when there was a problem and when there was not a problem, and you created two distributions. You put the observations of that metric into two piles, the pile where there was a problem, the pile where there wasn't a problem, and you've got the two distributions here. This particular metric you can see from the graph, the green side is the low side. So low values for this metric are generally good, high values are bad. So it could be something like CPU utilization, for example. But the point is that you've got these two distributions, and they both have their anomalies that live in the tails. There's the really, really bad anomalies that are way far at that end, and there's the good anomalies where are at this end. Those may be noteworthy, but where the problems are is where these two overlap. So one of the things you can do with a alarming strategy is say, okay, I see an alarm, or I see an observed value of the metric. It's this blue dot here. And I look at the difference in the probabilities that it's bad, that it represents a bad problem, or that there is a problem there, versus the probability that we're okay. And that difference is big, and the probability that we're okay is higher. So I could say, all right, I won't alert. And you could do the same thing on the other end. Okay? And that's a very good strategy. It works well. It actually, if you take a look, it works well for, the vast majority of observations that you would see. However, when you look in the center there, that's where the decision gets much harder, right? That's where the difference in the two probabilities begins to, approach zero. And as we saw before, in that little area, there are lots and lots of anomalies. So let's zoom into that area. What you can do inside of that area is you can certainly err in the direction of not alerting on one side and err in the direction of alerting on the other side. That's cool, but that does not get rid of the sort of the middle area, and there the decision is very hard, and you're making a very hard trade-off between having your head in the sand where you choose not to alarm, or crying wolf where you choose to alarm. And so the statistical aspect of trying to implement an alarming strategy doesn't cover all cases, essentially. And unfortunately, the cases, there's lots of them, and that's due to the nature of monitoring, which just has a lot of data. So you end up trying to make trade-offs, and the trade-offs are the ugly case where you issue, don't issue an alarm when there's a problem. That tends to be customer visible. The other case is where you're, issuing too much noise, and you're hurting your support folks and the ops people with too many false alarms. That trade-off is often made in favor of lots of false alarms. That's the way monitoring systems work today, for the most part. So the question is what to do about this. Where can we seek some relief? And in my opinion, I guess as I'm anxious to talk to people about what you guys think about all this. This is sort of a proposition. Where I think the problem lies, the root cause, is there's not enough information from the statistics or from the quantitative models. There's not enough information to make the decision. So how do we solve that? Well, I have one word: context. You need more context. Well, what is context? Well, here we've got two pieces of pizza. They look pretty nice if you like pepperoni. I would happily eat either one of them, right? However, with context, choice becomes a little more obvious, right? That's the importance of context. That's one type of context. Another type of context just sort of has to do with just the whole phenomenon of parts, the sum of parts making a whole, and the whole is greater than the sum of the parts. This particular case, I've got a bunch of parts lying here. When I put context around it, what I get is a nice SUV that may have air conditioning, four-wheel drive, and can go a long way in the desert. That's a lot more information. That's the kind of thing that context can provide. I just put this in at the last minute. This is our weather. And what's interesting about this is you see an interplay of context between how much sun you get and what the temperature is. Kind of an obvious piece of context, but without that, these wiggly lines wouldn't mean nearly as much. So let's look at a more sort of DevOps-esque example. This is an example of a time series. It's a plot of a time series. It has raw metric values, which are the black line. And this is a very fancy algorithm. It has two bands of normalcy, one that's based on multivariate models and the other that's based on univariate models. The multivariate model is much more accurate. It's an adaptive algorithm, so once it sees a change in what's normal, it adapts. So you can see all this happening here. We start off at one level, it jumps up to another level. For a while, the bands, it's outside of the bands, so it's anomalous, and then the bands adjust. Okay, that's without context. You notice I don't have any label for the y-axis. There's no other information that you have. So it's hard to know exactly what alerts to issue or not issue based on what you know from this. But if you start to add context, let's just suppose that what we're showing here is CPU utilization. That's all well and good. That's still almost not enough context. What you also may want to know is that this EC2 changed. Its instance type went from a large instance type to a smaller instance type. So that jump is expected. However, if you have an alarming strategy based on the anomalies, then you're going to get a bunch of false positives. And this isn't the fault of the statistics here or the fault of the anomaly detection or the algorithms that are determining the band's width, the normalcy band's width. It's really the fact that you need to have context. So let's take a look at another case. Here, if I label the y-axis response time, then what happens is on the one side, I've got good response time. On the other side, the SLA is not met. So I'll get some alarms for a while, but then what's going to happen is the algorithm adjusts, and now I'm getting false negatives. So context is critical here. The question is how do you add it to in a monitoring system? So here's one approach to doing that. You start off with the basic strategy, which is fine and works, and there's no reason to disturb that. What we do is we add to it. So first of all, just looking at the strategy as it exists today, and in terms of what context is being applied, you get values, you can tag values, so that's a form of context. You can also associate values with metrics. You can associate metrics with servers. This is all good context, and most monitoring systems today readily do that, some in more fancy ways than others. And then there's the engine side of things, and the engines can be quite fancy. They can have very nice query languages. They can create new metrics from old metrics by combining them and transforming them and all kinds of things. But what happens typically is the step of doing all the analytic work and then making the decision what to do, that step is one atomic step, and then you end up with an alert. So, I think I skipped ahead. Okay, so what I'm suggesting here is what we might do instead is separate the two steps. So the first step, you get the data in, you add whatever context you can on the fly, but then think of alerting, the analytics aspect of the engine, think of that as something that's just adding context to a semantic model that you're keeping of the thing that you're monitoring. And the semantic model could include all kinds of things. The next slide actually shows that. But the idea is, this isn't new art. This is just standard information modeling, nothing new. But the idea is to keep all of that you know about what you're seeing or what you're deriving from what you're seeing, no matter how fancy the analytic is or on what time scale it executes. It could be streaming mode, it could be events coming in, it could be something that you're looking at cost maybe once a month. No matter what you find out, no matter how you find it out, it goes into that semantic model. Okay? And here's all the kinds of things you can do. I won't spend a lot of time talking about it, but I think the key point from all of this is that a lot of the analytic work is done on different time frames. Some of it has to be done at sub-minute levels, perhaps. Some of it can be done and is best done week over week or month over month. Or in the case of credit card clearing that you're doing and you're worried about Black Friday, year over year. So all of these different time scales play into what you know about each thing that you're monitoring. So the next thing you do, this is just another example. This is an example that involves relationships. It's important to understand what dependency relationships exist, what containment relationships exist. This is all stuff that can go into the model, and there can be very, very different tools that all end up in the same place. And once you've got it all in the same place, then what you can do is apply the next phase, keep that separate. The next phase is sort of an action policy that makes the decision, knowing what we all know, of what to do. So what does an action policy look like? It typically has three pieces: a scope, which basically says what subset of all the things you're monitoring does it apply to, what kind of things do you want to test, what conditions you want to test, and then based on the outcome of those conditions, then you take action. So that's one piece of it. Another piece, this is an example, I guess, of just a policy, what it might look like, and you can see that it's defining a scope as being EC2s, and they have to be in production, and they have to be a member of a particular ASG. Some of the conditions are involving things like computed metrics, things like slowly changing attributes, such as the number of CPUs in the EC2. If it's changing instance type, that may change. It won't change as fast as CPU utilization, but it does change. And it's also got a notion of time and a notion of calendar. So all these things are part of the tests, and then you can decide to send an alert, and then you can also possibly close the loop by taking an action, automating some remedial action, if you have confidence in that remedial action. So that's sort of the engine side of it, and then the other side, which is something also that came up yesterday, was just what the alerts should look like, what should be in them. And they almost always have things like timestamps, severity, maybe the duration, but all these other factors will definitely serve to reduce mean time to repair. So those are alerts with context. So going back to the with and without context slide, this is the without context slide. The with context slide then has a semantic model included. It has an engine that has two distinct components that operate on their own cycles, whatever cycle is appropriate to the kinds of things that they do. And in the end, you get alerts that are fancier, that have more information in them. So this is what I think is a reasonable strategy to try to improve alert quality. So the big takeaways are, I know you're all in suspense. Where so I just went, well, that's the big punchline there. Basically, that equating anomalies and alerts is probably not a good idea. The idea is to add context, thereby getting better alerts. to add context, take the effort to create a semantic model, as much automated as possible, but with human interaction as well. And think of analytics and all the data science that you put into a monitoring system. Think of that as discovering just additional attributes. And finally, take the approach, separate the action decision from the data collection process. Okay. So the best monitoring is all the math, all the analytics, but you need context as well. So that's it. Thank you. What's next? Did I end early? I wasn't keeping track of time up here.
You have a few more minutes if you want to take a question.
Are there any questions? I guess if we have a couple of minutes. I worked a lot to get rid of slides, and I'm shocked that I quit early, but it's good.
How many times have you run across a model which is how probabilistic they are? Or to look at the good side and the bad side and not always do one thing but roll some dice?
Yeah, it's rare, I'll be honest with you. I mean, having supervised learning in monitoring context is not as widely available or widely feasible, I guess, as another model. Oh, I should repeat the question. The question was, how many times have I encountered situations where I have information about known goods, known bads, and can create the kind of distributions that you saw up there. And it happens. I mean, there are situations where it can occur, but it's not as frequent in monitoring as in other areas. I think one thing that I heard yesterday, which I think is increasingly a feature that's being built into monitoring systems, is for people to provide feedback when alerts occur. So if you're getting a flood of bad alerts, then you can get feedback about it. And that could be the basis for supervised learning. If that helps. Did that answer your question? Yeah. Yes, question over there. Hi.
How much work is building this semantic model in comparison with the amount of work you're already putting into collecting all of the data and creating appropriate rule sets to take action on it?
Okay, the question was how much work is it to create a semantic model? And I would say it's a substantial amount of work, and that's probably why it hasn't been done. I also think that the sources of information to populate the model are so disparate that also adds a layer of complication. That there are very many specialized tools out there that will discover applications, or tools that will discover network infrastructure, or tools that will discover, transactions in an application. All of those are different. The monitoring solutions tend to specialize in those areas, and they're silos. The actual exercise of defining a semantic model and the entities and the attributes that participate in it and the relationships that exist in it, I mean, that is actually not that hard. What's hard is getting it populated accurately, and then, of course, with the sorts of technologies that have, now populate the cloud universe, it's a lot more complicated. Things come and go. Things that used to be fixed are no longer fixed. There's a lot of different changes that are occurring in different cycles. So and also I think the technologies. I mean, you have technologies for storing time series data. You have technologies for indexing huge amounts of data that's simple. You have relational databases that are, that have constraints that they enforce, that kind of thing. All those different technologies don't play well together necessarily, so it's hard. And I think that's why it hasn't happened yet, but I think it has to happen. So, does that answer your question okay? Yeah. Okay, that's it, I guess.
All right. Ben, why don't you come up and get set? While Ben does that, it's been requested that we take an on-call selfie. And I think we should all be in it. Oh, this is a video. Oops. There's Ben. Hi, Ben. All right. Thank you all. It's been an exciting morning. Ben is going to do a live demo that's being hanged out from his laptop to my laptop that's plugged into the video thing. So he's basically risking death. And rather than make it harder for him, let's give him a big round of applause. Go, Ben.
Thank you. Before I begin, I want to stop and collectively recognize everyone, of course, that Jason mentioned, but also Jason and Will. I cannot believe the idea of finding out 12 hours before game time that you have to have a new venue is like an anxiety dream to me in real life. It sounds so awful, and the fact that this is seems pretty pro. I mean, obviously there's a little duct tape with the Hangouts, but my God, what an accomplishment, and thank you. So, round of applause. Definitely be a good anecdote for everyone in this room, I think. That's what we live for, right, anecdotes? Actually, speaking of what we live for, so why are we here, That could get really deep, but I just mean in terms of monitoring. If you search for existential crisis on Google, this guinea pig is top 10 material, which I really like. But what I mean by this is why are we here in Monitorama? I think that there's a lot of ways to think about that. If this were easy, no one would care about it, right? This is not easy, what we're trying to do. That's why everyone here is thinking about it, and there's a healthy debate going on in these talks, if you think about it, between using statistics and automated things and events and logs and tracing and so on. So we're here because we need to get to why. That's the purpose of monitoring. This has been said over and over again in these talks, but I think it does bear repeating, and it's worth remembering. Monitoring must tell stories. If it doesn't tell a clear story, it's not working. That's the point. In your head, you have to have a story. You look at the monitoring, you hear a story. That is the purpose of monitoring. The more directly those stories describe why something is happening, the more successful your monitoring is. And this is all definitional. I don't think there's anything to debate here. There are a lot of debates about how to do that, but it's not debatable that why is the purpose of monitoring. The stories that we're telling, they got a lot harder recently, which is part of why I think there's a renaissance in monitoring right now. It's because the problem is getting harder, and human brains, they like the hard problems, the meaty problems, and so people are getting interested in this. We feel like there's got to be a way out of this. But let's talk about why it got harder. So we still need to tell one story. The problem is that the number of storytellers is growing rapidly. Microservices are here to stay. I don't think anyone's really debating that, I hope. But they did break our tools. Our tools were designed to tell stories about a single process, or maybe 3 processes or something like that. But processes where as every engineer at your company knew the names of all the boxes, and they knew what they did, and they knew their boundaries well, that kind of world. These processes were divided up into packages, and maybe there is some difficulty in going from package A to package B from a monitoring standpoint, but by and large, you were within a single process, and that encouraged a certain category of tooling. Those packages have been split into services. Of course, this is approximate, but you get the idea. If you used to tell a story by following the flow of control in your program, you still need to do it. I mean, the application semantics are still happening across these conceptual boundaries, but the story needs to cross those boundaries as well. So the first big problem is how do you tell the story about one transaction in a distributed system? Especially remembering that everyone is moving to distributed systems, and this is commonplace. How do you tell a story about that? Okay, so that's one problem. The other problem is that there's not just one of them, there's a lot of them, and they're concurrent. So this is the simple thing. This is how we're thinking about our systems and our brains. At least that's how my feeble brain thinks about it. I'm not smart enough to really think about concurrency in a sophisticated way. But okay, maybe we can model it a little bit more complicated. Okay, maybe they're just happening at the same time, so they're overlapping in time, but it's still not too bad. Well, that's not quite right because it's async and there are callbacks, and this diagram doesn't even do it justice. There's no forks and joins. So that's pretty bad. But really what's happening is this. So it's all async, it's concurrent, and it's distributed. And so each one of your stories is happening concurrently with thousands of other stories in every process. And these processes are forking and joining and telling their stories in one big jumbled mess. And somehow you need to tease out one story from the distributed concurrent system. So that is the challenge before us if we're trying to understand application level semantics, which we are, in the context of distributed systems, which we run. So I will do this in 3 chapters. In my mind, if you're going to tell a story in a monitoring system, the 3 levels are what, where, and why. And I think we have a really great answer for what. We all know this answer. Metrics, they're awesome for what. Really good. Especially if the what is something that you want to alert on or measures some like key KPI for your business or the top level latency or something like that. It's great for that. As an aside, you can, I want to make it clear that metrics can be inferred from other instrumentation, but the point is that what you're getting out of your system is a metric describing something that you really care about. That's great. And so those are the what's of your stories. When you get woken up, hopefully it's because something bad is actually happening, and the something bad should have a metric associated with it. So that's the what. I do have a cautionary note about metrics, especially as we move towards distributed systems. If you have some kind of table stakes for what you want to monitor in every one of your processes, especially in a microservices architecture where every process, it's not just CPU and network. It's like, your RPC framework has a bunch of metrics. All of your connections to other storage systems have a bunch of metrics on the client. Your service mesh has a bunch of metrics. If you put all these in a dashboard, it's just information overload, and the signal noise is so low that you're stuck with so many what's that you can't make sense of it. The way I think about this is the following diagram. By definition, in an application, as far as a user perceives your application, there is a fixed number of things that the user actually cares about from a product standpoint. So here we're controlling, product changes are out of the picture here, but as you add microservices, there is not an increase in the number of user visible symptoms that should actually matter. Those are a function of the product, not a function of your system. That's how I think of it anyway. However, the number of plausible root causes for problems is growing super linearly to the number of microservices. I'm not going to lie to you and pretend I know what the formula is, but it's certainly the case that as you build out complicated microservice architectures, the interactions between the services have some n-squared-ish thing, and you don't want to be enumerating your root causes for a variety of reasons. One is that there are just too many, and you'll go crazy. The other is that when you're on call looking at a dashboard, it looks kind of like this. But the other one, which I'll get to, is that root cause analysis is really hard. This is from my company. I did this actually. I put the slide together this morning. I just picked some random thing that happened earlier this week. It wasn't good. It wasn't terrible. It wasn't good. We have a bunch of metrics dashboards too, of course. And so I took 8 screenshots sort of at random, just tried to fill this screen of this incident. Which one is the root cause? Anyone? I honestly have no idea. I have no idea from looking at this. You can't do root cause analysis by looking at this stuff. Especially when it's not 8 graphs, but it's like 100 graphs, which is commonplace. If there's a real honest God problem, you're going to see spikes everywhere, So you can't do root cause analysis looking at time series data. It's just not feasible. There are too many. Okay, so that's what. Let's talk about where. This is the classic distributed tracing story. Officially, the title of the talk is distributed tracing, how we got here and where we're going, or something along those lines. So this is part of the how we got here. I've been working on tracing stuff for a long time, and this is the problem that we really set out to solve when we got going with tracing. It was, you know that there's a problem, probably latency or errors, maybe at the top of your stack, and you want to know where it originated. That's actually a pretty big step in your storytelling journey of figuring out why, especially if you have hundreds of services, figuring out which one is actually the root cause, even if you don't know why. That's a big step. So that's what chapter 2 is about. So again, metrics, great for symptoms. Nothing wrong with using them for symptoms. But distributed tracing is a wonderful way to get to the where of a latency issue or potentially a user visible error that's originating from the depths of your system. Wow, the font for the presentation is different than my normal font, but I want to introduce Donut Zone. This is something that I've built for this purpose. We're really going to push Murphy's Law today with the relocated conference and the Google Hangouts presentation and live demos, but here we go. So Donut Zone, it's blitz scaling, it's big, it's getting bigger, it's microservice oriented, and it's having lots of problems. It also is built using open tracing. One of the things I want to emphasize about this demo is that the instrumentation here is like really boring. It is not hard, and it's pretty much automated. So there's nothing you'll see today that involves anything interesting from an instrumentation standpoint, except for one thing, which I will talk about, but it's an isolated change. Let's talk about the architecture a little bit. So move fast and bake things. We are taking orders, and there's also clients for admin, like portals for stocking and cleaning the oil machine. There's a BrainPal payment system that we call out to as a SaaS. And then there's some services in the back end that fry donuts and top them with sprinkles or chocolate or whatever. So this is the basic architecture. The goal here is to make something that's complicated enough that we can all kind of, there's suspension of disbelief that this is an actual microservices architecture. Obviously, they get way more complicated. I want to highlight that, like all systems that do anything even remotely interesting, there's some issues here. The issue in this case is that we can't restock the sprinkles and apply them to the donuts at the same time. So there's a mutex there and a queue that blocks behind the mutex. And in the fryer, similarly, you can't fry donuts and clean the fryer at the same time, but we do need to clean the fryer. So again, we have a queue. Now, in a real distributed system, these things would be like database tables, or maybe there's a producer-consumer queue within a process, or maybe it's a producer-consumer queue like Kafka, or maybe it's a network link or CPU on a machine. All these resources are things that can become bottlenecks, but we have two that we're focusing on here. So I'll show you how this works. I'll order some donuts. I'll go to donut.zone, my browser, and okay, so here's some donuts. Looks like we've got some sprinkles, cinnamon, and chocolate. These are the 3 types of donuts I've got. I'm going to order a bunch of donuts, and you can see as I order them, I await them down here, and we have some timing information. Maybe it's a little hard to see. I'll make this a bit bigger. Okay, so they eventually fade away. And there's some inventory information up here about how many of these different types of donuts we actually have, and indeed, if I order too many, I will run out, and there are no more sprinkles. Okay, so that was pretty basic, but simple. I can also restock donuts if I'd like to. I can restock cinnamon, and you can see the inventory is increasing. I actually want to restock a bunch because later on we're going to be eating a lot of donuts. Okay, great. So let's go and look at some sprinkle ordering in a tracing system. So here we go. Here's a bunch of donut orders. I will just pick this one at random. And this is a distributed trace. So you can see it's originating in our browser. Get donuts in the browser. We go to the web server. The web server calls this make donut function in another service. And then the make donut function fries the donut, processes the payment, and sprinkles it with something. Okay, so timing diagram, wonderful. That's important to understand that frying is on the critical path here, and so that's where we should optimize if we want to make things faster. You can see I've really beefed up the inventory. So you saw the critical path. Did that make sense to people, or general nodding of heads? It's not that complicated. Here's another one. I'll just walk through this one too. Get the donuts. Here you can actually see some latency in the Wi-Fi. And I order the donuts, it makes the donuts, and then we go through, process the payment, fry the donut, apply the topping. This is the way the system works. Now, that's great, nothing wrong with that. But there is something wrong with that. So, it's good to know that, where is this trace? That this fry donut span, this is the one that is holding up the transaction. And so that's the where. We got to the where. And I assure you, if your system had 100 services, getting to the where would be a big deal. It's like, great, now we know that's where the problem is. And we do know that. That's where the problem is. That's unfortunately not the same thing as why that was slow. And this is where distributed tracing's dirty secret, is that you can get to the where, but that isn't the full story. You have not actually root caused your problem. So let's talk about that. So why tracing is hard? So this is why we didn't solve this already. There's lots of data. Charity's talk, which I really enjoyed yesterday, spoke to the fact that instrumentation is not the same thing as data. The tracing instrumentation, in theory, is a really magnificent data source. It has not just timing information, but key value tags and causal information for your entire distributed system all the time. And when we were at Google designing this stuff, we ended up, by the time we were done getting to durable trace storage, we'd thrown away 99.99% of it. So we sampled 1 out of 10,000 traces, and the other 9,999 we literally discarded. So it's a lot of data, but by the time you actually get to trace storage, it gets cut into into this just sliver of what you started with. Let me talk about where you might do this sort of sampling. The first place you would do it is in the process itself. The instrumentation might not even turn into an in-memory data structure. So that's the first place you can do it. The next place is between the process's buffer and some kind of other buffer, whether it's a file on disk or some kind of collector process running on localhost or a collector process running in your VPC or in a SAS or something like that. That's another place you can do sampling. And then finally, you can do sampling at the very end before you write to durable trace storage. Now, with Dapper, what we were actually protecting was the cost of the system in durable trace storage. That was what we were actually protecting when we chose our sampling parameters. And we wrote this white paper. It was a funny anecdote. So we wrote this paper about Dapper, which people have read apparently. I mean, that paper got rejected by every conference I ever submitted it to. I submitted that to like multiple conferences. No one would publish it. Because there's nothing of any scientific interest in the paper whatsoever. It's like all like totally old news. And the only thing about it that's interesting is just that it existed and we had some parameters for how to build the system. Unfortunately, the parameters like this 1024 number or the 10,000 number, they're in the paper, but I don't think we did a great job explaining that. The 1024 was not to protect your process. You actually don't need to do sampling in your process for almost any real system. I mean, the amount of data that's coming out of the process, if you just ship it off, those numbers were taken like 2004 at Google, which is a long time ago in a very weird place. In the real world, you don't need to sample in the process. Like, you just don't need to. It's not necessary. So you've thrown away like a huge amount of data, and as I'll get to later in the presentation, data that's a lot richer than I think we even realize in this industry right now. You've thrown it out before the game even began. It's an incredible mistake, like a really, really big mistake, okay? And then the rest of the sampling was done to protect the cost of running the tracing system, which is a real thing. If you take all that data and write it to disk, if you wrote it to Splunk or something, which is admittedly a very expensive product, it's just like mind-blowingly expensive, so much so that you would never do it. So there's a cost problem on that side too. But what I'm here to say is that these first two sampling cuts are actually unnecessary from either a performance standpoint or a cost of goods sold standpoint. You can record all that data. It's difficult. It definitely requires some thought and careful system architecture, but you can do it. And that opens the door to some very powerful things. And that's what the rest of this talk is about. So, all right, so distributed transactions are not independent, okay? They're really not independent. And the corollary to this is getting into the why, is that I have a hypothesis that almost every latency issue that you ever care about is actually a contention issue with something. It's either, again, contention for CPU, contention for memory, contention for a database table, contention for a queue. It's contention. And that is the source of all latency problems. Or if not all, very nearly all of them. Okay, so think about that for a little bit. So in my mind, the real problem we're trying to solve, if we're trying to get to why for latency, is to understand contention in distributed systems and to do it in a way that doesn't require a lot of forethought. Getting back to the enumeration of all root causes, you don't want to specifically measure every source of contention and diagnose them independently. You want a general purpose mechanism to diagnose contention in distributed systems. So this is a way you could do that. Let's imagine that you have tracing instrumentation, and let's further imagine that when you traverse a resource, whether it be a process or a mutex or a database table, that you assign a totally pseudo-random, doesn't matter what it is, identifier, globally unique identifier to that resource. So this is something that would be done in like a mutex wrapper library, which is what I've done in the demo you're going to see, or it could be done in like a database RDB, like a JDBI kind of thing, or it could be done just at the process layer. This is not difficult, and it would be part of the abstraction layer for whatever system you're using. Or if it was an RPC system, it could be around the service that you're depending on. But you assign IDs to things that you might contend on in the distributed system, and you tag spans with that. Getting back to another excellent point from Charity's talk yesterday, this idea that cardinality is a problem is unique to systems where you do your statistical aggregation preemptively, which is what happens in metric systems. This would be really bad news if those contention IDs were the values on a metric aggregation. And there were talks yesterday as well. I think Aditya's talk, which I really enjoyed as well, I think spoke to the problems that you can have if you try and use a high cardinality thing like a contention ID as a value for metrics. But what I'm saying is that for distributed tracing instrumentation, it's totally fine. In fact, I would say it's good to put the contention ID as the value for a tag, because there's no issue with cardinality. We're talking about event data. There's no issue with cardinality. And I'm further going to say that these contention IDs can lead us to automated root cause analysis. And to me, that's really, really exciting, and I think is novel. I would actually love for people to come up to me after this and tell me I'm totally wrong, as I want to study how other people have done this automatically and in a general purpose way. But I think it's pretty interesting. So let's talk about this in pictures, because this is really important. If there's one slide you actually pay attention to, this is probably a good choice. So we've seen these timing diagrams before. It often looks something like this. You have like a parent span and a bunch of child spans. A span just being a timed event in a tracing system. There's like a natural critical path that comes out from these diagrams. We saw earlier, like this thing right here is presumably the critical path that's blocking the parent span. So the question is, what is it contending on and why? So if we had a contention ID, let's say this is blocked on a mutex, which is what ends up happening in donut zone. If this had a contention ID tag, what if we could say, in the distributed system, what if we could say, I want to know every other span in the system, not in this trace, but every other span in the system concurrently that's also contending for that resource. So what if we could issue that query and actually get the results with perfect accuracy? Here they are. Here's these spans that are contending for that resource as well. So the question is, where did they come from? Because that's your answer. If you know where these came from, you know where the contention is coming from. That's like a really profound thing. Okay, so you've gone from knowing your system was slow, which is definitely good. It's good to know it's slow, and knowing where it was slow, which is also good, to actually having a potential answer to why, which is to say, these are the contending spans, where did they come from? So we can do that. Like, we have the causal information. We know exactly where they came from. They each have a parent ID, so just walk the graph, figure it out, and you're done. So like, now you actually have a real answer to this problem. You were contending on a resource, you figure out what else is blocking on that resource, and in that particular time interval, no less, right? This is reduced to this time interval, and figure out where those things came from and do aggregation on that. So what would that look like? Okay, so this is enough slides. Now I'm going to really push Murphy's Law to the max and ask everyone to get your phones out and go to donut.zone on your phones. Or if you have a laptop that's tethered, that's fine too. Don't do anything yet, please. Don't cheat and read the slides. This is a delicate. The chances of this working are double-digit percents, I think, but that's all I can say about it. Okay, so hopefully people have arrived at donut.zone. What we're going to do here is split the room in half. There's going to be this half, I'll call this the right half from your standpoint, and the left half. And you all are going to be group A, and you all are going to be group B. And what I'd like group A to do is to just start ordering any old donut that you want, but not too many, okay? Don't go nuts. And then group B, I want you to order sprinkles. Go. So group B, just hit the sprinkles button. Group A, order miscellaneous donuts. I'm going to go and check out how things are going. Inventory is going down quickly. This is actually very impressive. You guys are fast. Wow, this is awe-inspiring. Okay, that's good. Stop. This is amazing. I can't believe. So the fact this has even worked this much is like, it's almost a bit of a surprise. So let's look at some of these sprinkle orders. Oh, they're taking a long time. So first of all, let's just talk about how crappy it feels to use a product that doesn't respond quickly, right? 8 seconds is a really long time. It's like an eternity when you're on a device. And yet, like, a lot of websites routinely render pages in that sort of time frame. So I'll open up one of these 8-second traces. It's going to retroactively assemble this thing. You can actually see the network lag here is significant because this is mobile. There's a while before we even got to the server. But again, you know, we order the sprinkled donuts. There's a make donut thing. We process the payment, and then we fry the donut. Frying the donut, this took a long time. In fact, it took all the time, really. It was like 250 milliseconds waiting. This is kind of hard to see, huh? 250 milliseconds processing the payment on BrainPal or whatever. But frying the donut was 8.7 seconds. That's the problem. That's what we'd like to understand. So let's figure out where the load came from. So here we've done this analysis in real time, okay? So here's fry donut. It was called by make donut, but you can see the sprinkles is the critical path here. Not critical path, sorry. Sprinkles is the problem, okay? So you can see this is a backtrace of 100% of the data that overlapped with that particular 8-second interval, okay? And then we're looking at those backtraces and summarizing them. You can see that the other people who are ordering chocolate donuts, and there's actually a background robot that's always ordering cinnamon, just loves cinnamon donuts. And then we have some other people ordering cinnamon donuts, some real people. But 90% of it came from sprinkles. That's really powerful, right? I mean, so now you know that this latency that we're experiencing is due to sprinkles. And what's cool is that if I go and look at chocolate orders, I have a bookmark for this, we'd see the same thing. So the chocolate stuff was actually pretty, relatively speaking, was not that contended, but we'll get the same end result. Again, sprinkles are the problem. So it doesn't matter how we got here. So if you imagine these are two totally separate features of your product, but you're having latency of something, it's usually not that thing. That's the thing that's so frustrating about our job, right? It's like the problem is the other team that's like, you know, dominating your shared resource. So what if it just told you? It's like, it was slow? This is why. Like, it's right there. So the data's there. We instrumented it. We already instrumented it. It's there. Like, what a feast that we're leaving on the table, right? And there's nothing preventing us from doing this, except doing it. Okay, so that's round one. Let's go to round two. Now everyone on this side, just order whatever donuts you want. We've run out of some donuts, so I'd like everyone on this side of the room to go to the restock tab at the bottom of this thing. I'll do it too. And just start restocking stuff. Don't go, every time you click it's 10 donuts, so you don't need to go nuts or anything. And we'll do a little bit more restocking. Yeah, supplies are increasing. This is probably enough. You can stop. Wow, look at that. That's impressive. So we've got a lot of inventory. So let's see. We'll pick cinnamon this time. So I'll go and look for order donut cinnamon. And wow, these are taking a really long time. So let's figure out why. I'll click on any one of these, doesn't matter which. We'll assemble this thing. Oops. I knew something would go wrong eventually. Hold on a second. Let's see. I'll do a couple. Here's like a 4-second one. Okay, so now it's interesting. Now the critical path, we do see a lot of contention around. We see a lot of contention around frying still, and it's coming. Oh, someone cheated and went and cleaned the fryer. I didn't say to do that. Don't do that. You're scooping me. But anyway, so you can see now there's a pretty even distribution of people frying. So there's no clear culprit here. But when we look at the sprinkling process, we can see we're only contending with restockers for cinnamon, which is interesting, which is what you'd expect actually, because the different toppers were sharded. And so we only contend with transactions that did this. Now, I want to be clear, the instrumentation for this, it's just a class called smartlock.go. Doesn't know anything about any of this stuff. None of it. The only thing I did here was to add a contention ID to the lock. That's it. Okay? And we can get this interesting interference effect between restocking and ordering, and we can see it just naturally. And you can see how the shards line up and so on, and where the contention comes from. So to me, again, that's a pretty powerful thing to know, that the live get donuts are contending with just the cinnamon restocking. And, oh, 1 minute? Good, I'm almost done. Last demo. We're greasy, okay? We need people to go back. I'd like the same arrangement from before, but can I ask you to go to the cleaner and just hit clean a bunch of times? Okay, great. Just get started. Okay, everyone go nuts. Wow, this picture. Oh yeah, it's a gross picture. I'll show everyone see. So only one person cleaning. Here's the cleaner. Okay, that's great. And now I'll stop. I'll refresh this thing. I hope this worked. It's not totally guaranteed that it did, given how many people are doing this right now. Wow, people are really going nuts. The thing I didn't expect for this demo is just how many people. Maybe I'll look at the clean fire just in case. But yeah, if I look at the frying latency, well, yeah, it was a little unimpressive actually, because there's so much latency from other stuff. But this is supposed to take like a really long time to clean. And if it had taken, there was a circuit breaker in the code in case latencies got too high, just so people didn't like time out, and it triggered here. So bad programming error on my part. But if this cleaner had taken 10 seconds, even though only one person was doing it, you would see that here. So it only takes one request to bury everyone's latency, and you can catch that in this sort of setup. Okay. Anyway, what I was here to say was that we have to get to why. Latency is actually contention. And that tracing of the future, which is basically now, can do this automatically. Thanks a lot. Oh, last thing, if you want to talk more about this, I'm going to have a Birds of the Feather breakfast tomorrow morning at 8:30. Just send me a message on Slack. As long as you do it before 3 p.m. today, I'll add you to the invite, and it would be really fun. We're just going to nerd out about this stuff. Thank you very much.
You should come up. All right, we have 3 sponsor talks, and this is going to be interesting. Can you try clicking? Just aim at Jordan. Sweet. Okay, it's kind of working. So 5 minutes for Joe from Wavefront. Sorry, dude. You're all paying attention. Good job. So you get 5.5 minutes because I screwed up. Joe from SolarWinds, thank you.
All right. All right, everybody hear me okay? So yeah, so I'm here from SolarWinds. If you're not aware of who SolarWinds is, it's a very long-standing company in the network performance management, application server performance management, and data centers on-premise. But in the last 3 years, and what we're here to talk about today, is we've built an extremely compelling portfolio of best-of-breed hosted SaaS solutions for monitoring all of your IT infrastructure. And I'm going to walk through, so probably about a minute each, just do a quick hit on what the product is. We'll walk down the stack and see how we help you on your digital transformation. A little latency on the clicker. All right, so Pingdom, I hope everybody's heard of Pingdom. This is digital experience. That's what Gartner calls what your user feels, right? So is the site up? Is it slow? Transaction, real user monitoring. What Pingdom's been working on, and the other thing I want you to come away with, because this is a very sophisticated crowd, is what we've been doing. So we've been improving our transaction monitoring. So we've got more check locations. It's easier to write checks. We're doing these with the Google Chrome browser. And pricing all these products, SolarWinds mantra is this better? I keep getting feedback. SolarWinds mantra is simple, powerful, affordable. All right. I don't think I have to tell you what tracing is. Ben just did an amazing job of that. So the takeaway, we recently brought in the fold last fall a product called TraceView. And the important thing about this, full distributed tracing, the original first commercial vendor to provide distributed tracing. This team was way ahead of their time. And the important thing, fully automatic instrumentation. And so this means you don't have to go in, you don't have to write custom code to stitch your spans together. We have the broadest set of language coverage. We have PHP, Node, Ruby, Java, .NET, Golang. I think I'm even missing one more. We have support for different applications, infrastructure applications, like Cassandra, MySQL, Nginx, Apache, and this all comes out of the box. Install it, get rolling, see your app map, see your traces, dig in. Here's some of our APM screens showing you one service at a time. You can drill into the heat map, see your outliers from even just a single event. Got our traces here showing across all of our microservices. All right, going down the stack. Tracing is amazing, obviously big fans. Also, we're joining the open tracing. We're working with Ben and his team. We're super excited about that, the industry coming together. So obviously very excited about tracing. I'm excited about events and what everybody is doing with that in the space. But to paraphrase Mark Train, the death of metrics is greatly exaggerated. In terms of your system metrics, the temperature in your data center, the depth of your queue, these are things we need to track. We need to be able to see them on dashboards. We need custom flexibility. We need to get our metrics out of CloudWatch or Google Cloud. This is what Librado provides. What we've been doing in Librado, a very significant shift for us. So in January, after almost 6 years, we brought forward a fully customizable tagging data model. So we literally rebuilt the entire underlying data engine. We now support arbitrarily custom tag maps, and you can group and select. You can wildcard on those. We have a super flexible, terrible resolution GIF of going into a dashboard and segmenting on our EC2 Redis cluster, different AZs, instances. Down the stack, logging, paper trail, the stop of last resort. And so what we do here, we aggregate all your logs from one place. We've done a couple really cool features here. Click to search, so this is live tail. So first of all, live tail is pretty amazing, but now we have built in out of the box, you can click on IP addresses, server names. We have several built out of the box support. Just click that, immediately filter. You can also create custom filters that you can click to filter on your live tail. We have log event actions now, so you can generate links to a particular log event and all its context. You can take that over to the command line and easily then show that same set of logs from the command line. You can also link that to your teammates or your colleagues and bring up the exact same set of context. And most importantly, we've built this portfolio, this composable monitoring portfolio, through a series of acquisitions, but we're also focusing on bringing these, as we call, smarter together. And so we're doing things, so now from your Librado, your metrics dashboard, metrics generated from log searches, you can click through with context over to the log search, filtered to the same time window. For our tracing and APM solution, we're generating all of the metrics from the tracing data, making those available in your telemetry store. And last but not least, just last week, we've added in now we call Pingdom Server Monitoring. So if you're familiar with Scout Server Monitoring, they've joined the team. We're rebranding it as Pingdom Server Monitoring, but this is dirt simple, straight out of the box server monitoring, very powerful, very elegant, and we're bringing that together with the Pingdom brand. And then just a couple housekeeping. We have a booth. It's not here. You may not have noticed. This is a different venue. But tomorrow, touch wood, it will be back at the old venue. Our booth will be upstairs. If you come by, we're going to be raffling off an NES Classic. And if you know anything about that, this is like by far the best odds you will ever have, roughly, of getting an NES Classic. So come by the booth, just say hi, get your name in for that. It was literally required to get here, so we do have socks. They're orange. And then last but not least, we're hiring. So if literally anything to do with monitoring and building those systems interests you, we do have the full stack. I'm sure we've got some work that would be a great fit. Come see us. That's it.
Our next sponsor is Cliff from Nuitive.
Thanks, everybody. As Will said, I'm Cliff. I'm a support engineer from Nuitive. And slides. So Nuitive is a full-stack monitoring solution built on top of a machine learning analytics platform. Our architecture is based on open source technologies. We run on AWS. We practice continuous delivery. We have over a decade of R&D in data science and machine learning capabilities. And our core passion is to make monitoring more intelligent and easier to use for everyone. We built Nuitive because it's clear that a new approach to monitoring is needed in modern environments. Traditional monitoring fails because infrastructure, application, and cloud architectures are complex and dynamic. It's become too hard to manage your environment by just watching graphs and configuring alerts with static thresholds. We hear from users every day that they have too many tools, too much alert noise, and cloud costs which grow month after month. Our platform is designed from the ground up to address these monitoring challenges using machine learning technology. We integrate with several open source and open license agents for monitoring your application performance, your infrastructure, and your middleware. We have the ability to bring in text-based events from tools like Logstash using our API, and we can pull detailed billing information from AWS for your cost reports and analysis. And all of this data is fed into our unique machine learning engine to provide you with dashboards for centralized visibility into your KPIs, alerts based on our multivariate correlation analysis and learned behavior, and reports showing your capacity utilization cross-analyzed with your AWS billing data. This means fewer tools, which means you can spend less time managing your monitoring tools and more time on anything else. You can troubleshoot faster by having your data in one place. You'll be able to proactively detect problems, receive fewer false alerts using our anomaly detection technology, and you'll have access to our cost capacity reports, as I mentioned. Our customers run the gamut from small DevOps shops to some of the largest enterprises. This is the point where I would normally show a live demo, but so configuration is quick and easy to start with. You would set up an integration, AWS, IAM role, agent script-based installation. Once data is coming in, you get pre-configured dashboards for quick summaries. You get pre-configured policies for meaningful alerts. Those alerts will get you events and notifications. Notifications and events get you right back to what actually happened. You can see where the anomaly happened and why it's relevant. We also have capacity utilization reports and cost and performance and recommendation reports, as well as this sweet ASG report here, looking at the size of the cluster over time versus the performance. That's the long and short of it. Hit me up for any answers to any questions you may be left with. I'll be around here, Monitorama Slack, and on Twitter.
And our final sponsor of the morning is Richard from Moogsoft.
All right. Waiting for the slide. So if you're expecting a vendor kind of pitch and introduction to the product and company, you'll be sadly disappointed. It's not what I do. If you're expecting slides like I am, so the good news is, when I last presented a couple of years ago, I think I used all of 3 minutes and 55 seconds of my allocated 5 minutes. So I should be pretty good at squeezing this into a narrow time slot. I don't think my display's mirrored. Closer. Okay, this is something to work on now. So when I entitled my little presentation, Stuff Happens, I promise you I did not predict an underground fire. It was just kind of in the context of what we do as a business. All right. Nope. Yes, we're there. Okay, so I've been doing monitoring for quite a while. In particular, working on the business of reducing event noise for operators. Originally in network operation centers, more recently in sort of like DevOps type environments. But I always start with the mantra, the first thing you have to do is deduplicate. Remove the repeated messages, the stuff that's annoying people. So you can imagine what I said when 2 years ago, this happened. So, twins, the irony of, right, deduplication. And by the way, for those of you who are in this sort of space as well, this is what happens when you let twins, 2-year-old twins, do their own temporary tattoos. Oh, and that. So that's the first thing I learned, is you always expect the unexpected. You can plan, you can analyze, you can model, you can create rules. Something's going to happen. Stuff will happen. So this is actually something that the company's been building a business around, right? Which is the notion that it's the unpredictability of what you're trying to do that catches you out. And one of the realities we found, and this is actually probably quite an aging quote now, but it's kind of like formed the basis, the nucleus of what we as a company at Moogsoft are doing, is trying to get ahead of understanding what's happening. When your users are impacted, you should be the ones telling them, not them telling you. But that's just not life, right? So, oh, by the way, there's lots of quotes in this little miniature presentation. The first one was me, this one's... So our marketing team, when they realize that end users are realizing that they're impacting issues before other people, say, wait a minute, there's this new medium called Twitter, and that's where people go to complain when something happens. So they came up with this brilliant notion that what we should do, particularly when we're going to talk to a potential customer, is do a bit of research. Go back into Twitter, query for the, the help desk, and see what users are saying about the service offering. And they came to me and said, Richard, is there a way you can automate this? Is this something we can do with our software to make it a little bit more automated and intelligent? And my first reaction, of course, is, yeah, if we're going to customers, telling them about what a really bad day they've just had is a perfect opener and a perfect introduction. But from a technical standpoint, it's actually a little bit tricky, because it's very easy to go to the Twitter user interface and type in something and search back through months of history of tweets and find one damning tweet from a customer who was upset. It's a lot more difficult to do that in real time, because you're really just sitting around waiting for something to happen. And that's where I learned sort of like lesson number 2, which is the Twitter API is not a fire hose. You've got to be very selective about what you're looking for. So, oh, there we go. So Homebrew looks really good on this screen, right? So what that basically is my attempt using a node wrapper to attach to the Twitter API and look for specific keywords. And what I did was, after a bit of thinking, I turned it around and I said, instead of looking for a specific company and waiting for something bad to happen, what I should do is actually attach to the Twitter API and look for keywords. And one particular keyword created pay dirt, which was outage. So outage is a word that people like to use when they're upset about services not being available. Actually, that's when I learned my lesson number 3, which is ordinary people don't hashtag. I was really surprised by that. I just thought, I'm used to people who write entire tweets comprised of nothing but hashtags, but people don't. So I actually created a mechanism that I called pseudo hashtagging, which is basically just a keyword search, but you treat it like a hashtag. Okay. And this is where the Vendry bit gets in. So what I did was I wrote this little wrapper. I plugged it into a node client that we have that's available. I'll should have put the name up in a second so you can download it and play with it yourself if you'd like. And then fed the feed into our product. And the key thing was to use time and linguistic clustering to try and associate tweets. So I'm looking for the hashtag outage, or pseudo hashtag outage. And what I'm going to do is group together all the mentions in a tweet. So that's basically the person who's sending the tweet and anybody they @mention. Group those together and cluster around that and see what happens. And that's when things got interesting. So hopefully I've redacted this enough to protect the individual. So what this created was a cluster of tweets where a particular service provider, an internet service provider, I think in the Northeast, was mentioned. And you can see everybody tweeting about, apologizing to their customers, saying, I'm really sorry that our website's down, but our internet service provider is out right now. And so that was really interesting. And that's kind of like what, everybody's talking machine learning, right? We too. But for me, the goal of unsupervised machine learning is for the product or the technology to tell you something you didn't already know. So instead of looking very specifically for organizations and companies, I threw in there a keyword like outage, and it started telling me who was having a bad day. And that led me to lesson number 4, is that every day is a bad day for some people. Power companies, for one. I learnt over the weekend and the few days that I was playing with this, and a couple of weeks afterwards, every day is a bad day for Kenya Power, for example. I did not know that. And also telecommunications companies, cables, TV providers, they have bad days every single day. So, but it's the question is, what do we learn from this? So I was really kind of hoping you were going to learn something. So as I promised, if you wanted to tinker around with the software that I was tinkering around with, the client software is available on NPM. It's Node Moog, and if you find that pink button on our website, you can we'll spin up a container for you where you can actually feed events in on tweets and things and play with a bit of clustering. And then finally, the obligatory we're hiring. We are, and we're looking for really interesting people. But even if you don't want to join us as an individual, we'd love to have you as a sort of a customer, a technology partner, and hopefully we can make stuff happen. Good stuff. No, thank you.
We've almost done it. So our final speakers before the break are Rebecca and Laura. Come on up and get set. We'll give you a round of applause in just a second. Thank you all for being patient, especially given that there's coffee right over there. Please hang on until the break if you can, and keep conversation to a minimum so we can focus on the speakers. But a round of applause before we get started with Rebecca and Laura.
Hello, I'm Laura Thompson. This is Rebecca Weiss. We come from Mozilla. We make a little browser named Firefox. And today we've come to talk to you about science. Louder?
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 Am I too loud?
What about now?
I'm fine, right?
Okay.
She's, okay.
Okay.
I'm usually the loud one.
I just talk. Nothing. There we go. I just talk too fast and have a funny accent, so. Okay, so this talk is about how we reinvented ourselves to become more data literate, experiment driven, and ship faster. But actually, that's a lie. We're still in the process of doing that. We are in the process of reinventing ourselves. So I wanted to be strictly honest with this audience. In the beginning, there was no data, and it was bad. So Mozilla's a pretty old company. I have been there for nearly 10 years, which is like an epoch in the scheme of things. And when I started at Mozilla, there were about 80 people, and now there are about 1,200 people. And we have always stood for the user, right? We're a non-profit. We care about your privacy. And what that meant was that collecting data about our users was very bad, right? We did not do that. You're a bad person for wanting it, right? Not allowed to have data. People who want data are bad. Data is bad. You're a bad person. You make bad systems. You do bad things. But at this stage, we only had 3 pieces of data that we were allowed to have. We knew the number of downloads. We had a little mechanism called block list pings, which was basically once a day, Firefox would phone home and say, is the current version of Flash vulnerable? And if so, we would say, yes, please switch it off. And we would count those, and that would give us a proxy for the number of users. And the third thing was that we would collect crash data, and we still do. This is when your browser crashes, you send us like a subset of the contents of memory, which is incredibly toxic data, right? It has like the URL of the bad thing you were looking at, and like your IP and your email address, and the credit card number and SSN that you typed into a form, and like really bad stuff. So we hated collecting data, but we had this really toxic data. So we were forced to keep it in a monastery and have it guarded by ninjas, and I know this because I was one of those ninjas. So overall, this was a very bad situation. Oh, this is actually like a simulation of what's happening in downtown right now also. Okay. So we were sort of in this world where we were making decisions without evidence, right? We were shipping code, we were beta testing it on hundreds of millions of users with no information. And we were making product decisions based on what engineers thought were a good idea. Also, I need to point out that sort of going back 10 years, we didn't have product managers because we didn't really know what that was. So we found ourselves facing questions like, I shipped this new feature. Did it affect retention? Did in fact it make people want to use Firefox more? Did we regress performance? We had test infrastructure, right? So we knew if Firefox got slower on our test harnesses, but it turns out users have all kinds of crazy graphics cards and very old operating systems and all those kinds of things. So, how often do users experience jank? Jank being that thing where you try to scroll and it kind of doesn't, and it's really ugly, and we didn't know. And how many users do we have anyway, right? We had this block list ping, but it wasn't very informational. So, real questions, ones that we could not, in fact, answer. It turns out that making a browser is kind of hard. It's not like making other software in many ways. I came from a background as sort of web dev, DevOps sort of person. And client software is hard, right? So here's basically what we do in a nutshell. We take a piece of compiled software and we install it on hundreds of millions of machines on every combination of hardware and every operating system in 200 different languages in 200 different countries, and we let the end user download arbitrary code from the internet and run it on our client. It's a little bit kind of challenging. So it's kind of like an app, except it's sort of not. It's also kind of like a service, except it's sort of not really one of those either. It has some service-like attributes, right? We have embedded services, we have Firefox accounts, we have location services, now we have telemetry. But there's some slightly different characteristics about writing this kind of software, and that makes it hard. But the way we like to think about this is not to say that Firefox is a special snowflake, But then in fact, Firefox is a beautiful, mystical whimsicorn, gambling through the clouds. But yeah, so we have measurement problems. Browser usage is very seasonal. It turns out when the weather is nice, people do not use their browsers as much. And also college students are out doing things other than sitting at a computer. It's very complicated. You know, we have the web changes every day. People ship new websites every day, and they ship a new website with new JavaScript that breaks everything. And people use the internet in ways that we don't expect. And we have to work all of the time despite all of these things. Because the first time you load a website in a browser and it doesn't work, that's when you switch browsers, and there is zero switching cost. Okay, so we decided we would start building some measurement systems, and this is how we went about it. We have a question. We will build a specialized, precise system to answer this question, and we will answer it. Yay! Then we will ask another question of the same system, and because we built this specialist system and deliberately constrained it so we wouldn't collect any more data than we had to, we would fail. So then we would go forth and build yet another measurement system. There's nothing wrong with this approach whatsoever, especially if you are somewhat, don't have an infinite budget and are somewhat constrained in what you can collect. And we ended up with kind of 4 main systems. I talked a little bit about the block list ping originally. That one is default on. You can turn it off if you want to, but it's on. So we have a reasonably good idea of the number of people using Firefox every day. We then built this system called telemetry, which is what it sounds like. It's a telemetry system. And it measured performance. It was very engineering-y things. We had histograms from the very beginning, which is nice to know. But they would tell you really useful things like, this is the number of milliseconds to first paint, and here's a histogram with buckets of how many bookmarks users have on average, and those buckets are like 0 to 100 and 100 or more. We later then built a thing called Firefox Health Report, which was the very first opt-out telemetry we had built, and this was incredibly controversial. You can look back at the bugs, and there's people saying, you will never be able to ship this in Europe. Google won't be able to ship it in Europe either. You cannot have any kind of client ID. Every measurement has to be independent, and no longitudinal measurements are allowed, and no client IDs. It's very challenging. Other than that, we also obviously continue to run our crash reporting system. So, if you want to know how we deal with privacy, by the way, our privacy policy is on our website. And if you don't trust us, you can go and look at the open source code to make sure that we're telling you the truth about what we do with it. And if you are more paranoid than that, I do work with some people who have very shiny tinfoil berets. We're working on binary transparency, so you can in fact verify that the code that you see in the repo is the same code that's running on your computer. So we bend over backwards to make this work. If you would like to adjust how much data you send us, this is in your preferences under advanced data choices. It tells you exactly what you send us, right? Which is really nice. We're very transparent. Okay, and now I will let Rebecca tell you about where we have come to after all of that mess.
Yes, because I'm on the data science team, and what ends up happening is all of these different collection systems, they're all really just sampling methodologies that are sampling at different levels of observation. And so from a perspective of a data scientist, this means that there's these interesting statistical properties to every single one of them, which means that every single time someone would ask us a question, even a simple one, we'd have to go through this list of caveats about what you could and couldn't conclude from a particular way of measuring a thing, because that's just the way that the math works. And no one wants to hear that, because it's a lot of caveating right up before you could even get to answering the question. So what that meant is that an engineer would be like, I don't want to deal with that, I don't want to deal with that, I'm just going to build my own thing because I know what I want to get answered and I understand this policy and I'm just going to make it work. So we think there are like 4, there's probably a lot more, but these are the 4 that we end up doing a lot. The other thing is yes, privacy still is a thing that we have to worry about, and we didn't really have a clear policy, and we still are kind of developing our policy around how we think about it. We don't really have a lot of guardrails in this case, because to the user, your privacy is protected until it's not. And then it's a violation of privacy, and that's a reality that we have to live with. So we kind of just had this world where we were only thinking privacy and collecting more data, there's zero sum, we either protect privacy or we don't, and that meant that we had no flexibility with the way that we approached the problem. Next slide. You guys are seeing all of our notes. I'm cheating. Next slide. Can you press play, please? No one likes to look at red for this long. Yes. So, what this meant is that we were in this world where we were our own worst enemies. And if you look at any of these bug threads that are related to any of these measurement systems, you can see how much we like fought about this. And it's this horrible position to be in because you want to make a better browser, you want to make a better product, you want people to enjoy the web the way that we think that they should be enjoying it. But you can't do that when we don't know what's going on because we don't actually have any measurements to help answer these questions about like what's driving users away, like what do they not like about this. So we were our own adversary. We were beating each other up. Next slide. And meanwhile, we're not unaware of the reality of the world. Next slide. Maybe I should just take this thing. Yes, I can do this. Yes, we are aware that our market share is going down. So this is the global desktop market share as reported by StatCounter. And the way to look at this graph, it's not so much this is the number of users that we're losing, or this is the number of dollars that we're not making, because again, we're a nonprofit. This isn't the way that we think. The way that we think about this is that this is our mind share. This is the vision of the web as according to these companies that make these browsers, and our vision isn't winning. And that's a real problem for us. And it's a real problem for you.
So we decided that we needed to move on. And really, we have been talking about this as if it was a data problem. And what it really is a culture problem. Surprise, surprise, they often are. So it turns out this is hard, and we needed to get better at it, get more transparent about it. Skipped ahead. And we figured out that we needed to change the way that we measure, have better measurement systems, and find ways to be more experimental. And all of that means culture change. So we decided we would build a data culture based on scientific principles, which sounds much more scientific than it is, to be honest. But there are 3 basic pieces to this. And I'll talk about each of them in more detail. The first one was that we decided that we needed to focus on consistency and reliability over trying to build very precise, specialized systems. That's one. The second thing was that if you've ever built a system for a small number of users, which probably everybody in this room has since you mostly make tools, you realize that you end up building consultingware. Like you end up building features for the people that scream the loudest, as opposed to sort of serving a general audience. So we wanted to try and prioritize a situation where people could serve their own needs pretty easily. And the third thing was that we really wanted to build like a badass experimental platform and do it very quickly, because we had left it kind of late. You saw the graph. Things were bad by this time. Okay, and we also settled on having a single data collection system. Not 4, but 1. We're not there yet, but we're getting there. It would be the one true ring of data collection systems. My precious. And we focused on this. There are many, many different kinds of things that we need to measure, right? From performance measurements to user interactions with the browser. You know, we had no event measurement on, we don't even know if anybody uses a particular feature, right? Think about that, it's kind of blinding. We wanted to have one good system instead of many, many half-baked systems. And a single mental model for what a ping looked like, right? What was the structure of a piece of data collection? We settled on kind of like a rich structure, which I'm really happy with. But it also means that we have one set of quirks. You're not trying to deal with the combinatorial quirks of many different systems, and one set of errors. So it's just much more easy to reason about something like that. So in terms of this, we're trading off for sort of precision on specialized measurements, but that is a thing that we can deal with later. It is hard to be precise if your systems are not up. So, okay, so choose ops, choose self-service services. Most of you have probably seen this cartoon. If you have not, I will read it to you if you're in the back row. How do I query the database? It's not a database, it's a key value store. Okay, it's not a database, how do I query it? You write a distributed MapReduce function in Erlang. Did you just tell me to go fuck myself? I believe I did, Bob. Now, the really sad thing about this cartoon, and I've had it pinned up on my wall for several years, which is when we started with telemetry, this was true with one exception, except that it was Lua instead of Erlang, right? But this represented reality accurately. And it's kind of fine if you're an engineer, but when a product manager comes to you and says, I really want to know if users like this feature, and you say, you can just write a distributed MapReduce function in Lua, Bob. And then they punch you in the face. So self-service is important. Okay, so we have built what we have on a series of open source tools. And some of these are going to be familiar to you as a group, and some of them are not. The first one in particular, put up your hand if you've heard of Redash. Not very many people. Redash is awesome. I want you to go forth and embrace Redash. So it's a Django-based web app. It talks to just about any tabular data store. So we have it talking to like Presto and Parquet, but it also talks to like Postgres, MySQL, whatever it is. And it lets you easily build dashboards for relatively simple queries. The thing that is really nice about it is that it is social. I can look at the dashboard that you made, and then I can view source for the code. It's like the web. And then I can fork your dashboard like it was on GitHub and tweak it a little bit and make my own dashboard. And this is awesome, and encourages a lot of people who are like, well, I kind of know, did a little SQL in college, but I haven't done any since. Or even if they haven't done anything, it's like the web, they can teach themselves. And it's been incredibly, incredibly successful. So we like this so much, we gave them an open source grant to make it even better, and I encourage you to go forth and use it. Other things on this slide, Airflow, which is Apache project, monitoring and job scheduling for dataset creation. We use pretty standard tools, Apache Spark, Parquet, Presto, and many, many more that I'm sure I am not listing out. And Rebecca's going to talk about the workflow for data science.
Yeah, because you might have noticed that the thing that's common about all of these tools is that they encourage a lot of this visibility between the stages. So the way to think about this is that in science, you have this idea of like knowledge has to be reproducible. You have to be able to identify that a thing was observed and that a thing was true at a time, and what were the steps that were taken in order for that thing to be verified as actually still true. We still see this all the time because the truth is when you work at a place with a lot of opinionated skeptics, you need to bring a lot of evidence to the table. So every single step of the number that we get in a slide, we wanted to be able to audit it all the way down. So yes, so this idea of like enforcing a citation needed culture, it might seem a little bit like aggressive, but the truth is, again, like you want to have evidence to back up your decision making, especially if you're the kind of person that has to make a judgment about some kind of really challenging thing. You want to be able to feel like you've made the most informed decision as possible, and so that means you need to trust the data that you're getting. And this is a problem that we were running into, that when people couldn't touch the data, or if they couldn't see how it was created, they didn't trust it. And it was super, super easy for you to say, well, but what about this, and us not having an answer for that. So now we can say, well, this is the number in the slide, and if you click on this number, here's the redash chart that it comes from. And if you want to know how that data set was created, here's the Airflow job that created it. And if you want to know the fundamental theory about why we even started looking at the data in this way, here's the notebook or the R markdown script or whatever it is that we're supporting at that level that allows you to say, like, from the pings themselves that came from the client that was measured with this code, because our code is open source, this is exactly where it all comes from. And we can audit that number all the way down. And that is something that we it's just been sort of like a really monumental change for the way that we think about knowledge.
Yeah, and actually, whoops. I want to tell a story about why we make this citation needed joke. I think this is an anecdote that kind of illustrates how much trouble we were in. We had a slide that had been presented to the board, and we needed to update that slide. And it doesn't really matter what the data was that was on it. But the person that had drawn the graph on the slide had left the company. So we set out to draw the 3 months later version of the graph. And we had 2 different data sets measuring that thing, and neither of them could be used to make the graph on the slide. So we drew some different graphs, and then you have to have that great conversation with your board about we don't know what we're doing. But here's the new data, and now we know what we're doing, and next time it's reproducible, and now it has a URL, and you can go and check it for yourself every single day if you want. So we learned that one an exceptionally hard way, and I would not wish that on anyone. Okay, so we're making progress, and this is kind of what success smells like. This is a graph of the number of active users on Redash. So we have 623 accounts on there now. If you know that there are about 600 people that work on Firefox directly, it's a pretty good number. We have about 150 active weekly users. That is people who are actively coming and digging into our data every week. That's awesome. I'm really excited about that. Okay, and some of the data, we're trying to publish more and more of it because it's not all public because of this sort of conflict between Mozilla desperately trying to be open about everything and also being really conscious about preserving user privacy, right? So we are trying to publish as many of our data sets as possible while doing that. One that's relatively new is the Firefox hardware report. If there are any devs in the room, probably interesting to you, there's a URL where you can visit this. And it tells you things like what graphics cards are people running and what processors do they have and what do we see as like the spread across the market. And this is really interesting data, right? Because there's a really large number of users involved in this. Okay, the other thing, the third dot point in the platform was to build a badass experimental platform. So now I'm going to talk about our experimental approach. We don't really like to say that we're data-driven because that sounds like you have no volition, but we're data-informed and maybe a little experimentally driven. So, okay. Now, one thing I need you to know is, I know there's at least one person in the room that used to be a Firefox release engineer. The way we build Firefox is complicated. It's very old. We have one of the earliest continuous integration systems, I think, that was sort of like publicly documented or shared. We still have extensive use of BuildBot. It's kind of disturbing. And so working into any kind of like experimental thing where we had like pref flipping, feature flipping, A/B testing, very, very challenging. So I left out the slide with the horrifically complex release infra diagram because the world needs you all in this room. We need you to be sane. Right? If you look upon this diagram, it's like looking into the abyss. The diagram will look back at you, and it knows where you live. Oh my God, I forgot to take it out. Don't look at that. Don't look at that. Cover your eyes. Okay, so moving on. In the bad old days, we still managed to find ways on top of this horribly complex infrastructure to ship experiments. And we had three kind of initial ways. The first thing was an idea of a thing called a funnel cake. I do not know where the name came from, but we talked about donuts for half an hour, and now we're talking about funnel cakes. You're all really hungry, right? A funnel cake was a special build. So with different code, we built it from scratch. Still took more than 12 hours to build it. And then we ended up like A/B shipping it through like an Apache rule with some kind of random dice roll. Do not ask me how crafty this was. It's exceptionally crafty. So yeah, pretty crafty. Second thing was what's called a telemetry experiment. That was where you made an add-on and you shipped it, but there was a lot of paperwork you had to do first, and you had to talk to lawyers because we were so worried about like infringing on our users' rights by shipping them untested code. So that kind of sucked. And the third thing was this really good idea called Test Pilot Mark 1, or somebody was calling it Test Pilot Classic, but we all know Classic is the good one and new sucks, so I'm not going to call it that, which was the idea that users could opt into trying a new feature and tell us if they liked it. Okay, and the problem with these was that they weren't really open science, right? They kind of sucked. The barriers to entry are really high. You had to be able to make a special build of Firefox. You had to do so much paperwork and so much approval, and every piece of data you wanted to collect, you had to be able to prove there was a direct user benefit to that specific piece of data, or you would not be allowed to collect it. And it just wasn't very production-y, right? Like, it didn't scale. If you wanted to do one of these, it was going to take you like a month, 2 months to get it out the door, and that's really not like a velocity that you can sustain for, making a living. So we invented this program called Go Faster. Yes, I named that. Engineers should not be allowed to name things. And as one of the people I work with, Dave Camp, pointed out, you shouldn't call it Go Faster, you should call it lower latency. I'm like, that's even worse, Dave. Let's not call it that. But there are several parts to this program, and one of them is a thing called system add-ons. And these are actually not, so to speak, an experiment, but they sort of form the basis for some of the other work. A system add-on is a part of core Firefox that we ship as an extension to Firefox. So if you go and you install like uBlock or Ghostery or NoScript or whatever it is, it works the same way as one of those, except that it's privileged. Like we know that it's made by Mozilla and it's signed with Mozilla's signing keys. The nice thing about those is they're web stuff, right? They're written in JavaScript, and you don't need to build Firefox to ship one, and you can ship one every day, or more often if you want to. You ship it like it's a web app. It's really nice. So they're not really an experimental mechanism, but they have enabled us to be more experimental. It took us a really long time to ship electrolysis. If you hang out in Hacker News, you may have followed some of that. That's like a multi-process architecture. And using system add-ons, we could ship those because we put a whole bunch of intelligence into the client that decided whether your client was ready to turn this on or not, basically. So it was good. Second thing we did is Test Pilot Mark 2. I encourage you to look at it, testpilot.firefox.com. And this is a place that's very product-y. Like, this is where we actually try new features on you and see if you like them. They're very early new features. A lot of it is just like, do you think this is a good idea? Is this something you would use? Some of them are further along. And the nice thing about these is successful ones can actually graduate into Firefox. We're doing our first one of those right now. I think it's going to be in Firefox 55, but don't quote me. And that's Firefox screenshots. Try it out. It's actually really cool. So that's program 2. And the third thing, which is kind of the really shiny thing, if you ask me, is Shield. So Shield is a program that lets us do a bunch of things, but Shield studies use actual statistically valid sampling to sample our users and offer them the ability to participate in an experiment. And in those experiments, we can do a bunch of things. We can flip preferences, we can install a brand new feature, we can collect extra data, and we can have multiple experiments in flight at once. And this is like the promised land, right? And Rebecca's going to tell you a little bit about this specific graph, which is from a shield study.
This graph's kind of cool because, again, you have to remember that we don't know a lot about what you're doing with the browser. We just have a lot of assumptions that we think are true, but we don't actually know, and we don't have access to your camera, and we're not looking at you, and we don't have your microphone, so we can't listen to you. All we can do is observe you with some degree of respect. So this was a study that was written that allowed for us to start asking people, why do you hit the reload button? Because we had no idea. The reload button could be, the page is broken and I don't like it. Or it could be you are a web dev and you just are constantly developing. Or the thing that we were all kind of that can't possibly it, but maybe it's some part of it is you want fresh content. And so what this graph does show, which we're not going to go into all the details of all the sampling and everything, but the gist of it is the gray bit is we didn't ask you, because you always have to have a nothing burger in an experiment. The red one is you just, you got the prompt when you hit the reload button and you didn't respond. The blue one is fresh content, and everything else was all the theories that we cared about. So what that revealed to us is that our fundamental understanding of why people use the reload button was wrong, and that we needed to start thinking about this entire way of thinking about user flow differently, and that's what we're actually starting to do now. So the thing to remember is that we are sort of mid-stride at this point. That's kind of actually the theme of this talk, because again, we haven't actually reinvented ourselves, we're kind of in the process of doing so. But the important thing was for us to recognize that we can still be this privacy-protecting company. We can still believe in our principles and the mission that we have, but we can also evolve on the way that we think about data and collection and measurement, because it's just kind of again, not to belabor the point, but we're not doing all that great in terms of mindshare. And part of the reason why this is not the KPI you want to measure yourself against, because this is an experiment against driving users away. And that's not a good way to think about building a good product. And this is a very coarse measurement. It doesn't allow for us to actually look at feedback on the way that our browser's working. It's kind of like a lagged indicator, and it's not a one that we should really be trying to practice on. So the gist is that as we get better at thinking about measurement, and as we get better about monitoring and building these tools and infrastructure to actually answer some of these questions about what's making users' experiences not so great, it's going to influence the priorities that we put into what technologies we develop. It's going to change the way that we think about feature development, and it's going to change the way that we think about the browser as a product entirely and the web as a whole. So for all of you people that think about monitoring all the time, there's a real story here for you to help understand and help us understand what the web should become and what it should be, because it's going to be driven by the data that we collect on this platform. So with that, I would say contact us if you have more questions or if you have some feedback.
Thank you.
All right, thank you, Rebecca and Laura, and you take your laptop. It is break time. We have a full 15-minute break. We're running about 10 minutes behind. There's coffee and snacks over there. Stand up, stretch your legs, and come back in 15 minutes. Thank you. So I won't make any jokes or stuff because I think we're tempting fate. We have 2 talks, a sponsor, and then it's lunchtime. Lunchtime, it's still beautiful out. You can go refuel. We're going to be back here in the afternoon. We're going to keep on keeping on. And we're back to the normally planned schedule for today. So we'll have speakers, lightning talks, and then we'll wrap up, hopefully, to schedule. We're running slightly behind right now, but we're going to stick to it. Lunch will be a few minutes shorter, but we'll plan to start as scheduled at 1:30, I think. So thank you. Please take a seat and give a round of applause to Doug.
Okay, let me check, is the mic working? Sounds like it is, great. And give me a second to warm up the laptop. I'm not doing anything nearly so crazy as Ben did. This is not a live demo, this is not a Hangouts, this is just me having my speaker notes to read. Louder? Okay. And also, if yesterday's set was pretty clearly the holodeck, I think that Moriarty set to try to get out of the holodeck and escape into the rest of the ship. And so this today must be the part of the episode where we've chased them all down into the shuttle bay, so good job. And I can't wait to see what happens tomorrow. Okay, so hello everyone, my name is Doug Krieger, and I'm a software engineer on the Interneto team at Google. Our job is to monitor the edge between Google's network and the public internet, looking for performance and reliability problems. And today I'm here to talk to you about packet captures. I hope to convince you of 2 things. First, that packet captures can tell you useful information about your application, which you can't easily get from other data sources. And second, that you don't need to make any fundamental changes to your monitoring stack to tap into this new data source. So you'll get great new intelligence in a minimally invasive way. What's not to love? So to start with, let's dig into a hypothetical music streaming application. And we're going to keep things nice and simple. The user asks for a song, a particular song, and the application server starts streaming an audio file to our client. Our client receives the file and starts to play it. You know, do, very nice. And since the audio file is pretty big, we're going to start playing the song before it fully arrives and continue playing it while the rest of the data comes in. Simple, right? Bring in the investors. We've got a good working app. So we've got an app deployed to production, and for the most part, things are working great. But we start to receive some reports from our customers. They're accessing the application like they're supposed to. They request a song. The file starts streaming back. The client starts to play the song, but then they get pops and drops, and the audio starts to cut out. This is not good. The skips aren't very long, but they're long enough to be annoying. And I think the first important point here is that you can tell that this is not a happy story, since the problem was reported by our customers. And that's not great. We want it to be detected by something automated so that we can mitigate this and fix it before it turns into an actual user-facing customer quality issue. So not only do we need to dig in and figure out what's causing this problem, we want to do so in a way that we can monitor continuously moving forward. Now, based on our understanding of the problem domain, we can make some educated guesses. The skipping tells us that we probably have an issue with throughput, how quickly the data is being sent or received. And in particular, our client is probably not receiving the audio data quickly enough to keep up with the playback. We receive some data, we start playing it, and then we run out of audio to play before the next portion of the streaming connection arrives. Great, so we have a hypothesis. How can we test it? Is there anything we can get from our existing application? Well, we could check the server. We probably got a good set of server logs that we can query. And it doesn't really matter here how or where the logs are stored or how you access them. The key point here is that they tell us that we sent, for instance, about 10 megabytes spread out over about 5 seconds or so. And that gives us an average throughput of around 250 kilobits per second. That's something to keep in mind. We'll probably measure amounts of traffic, amounts of data in bytes, but then we're going to measure rates in bits because, of course, we have to use something different there. So there's going to be a factor of 8 difference in some of these numbers, in case you were trying to do the math there in your head. Okay, so 250 kilobits per second is our average throughput, and we know that we encoded the audio at kind of around 128 kilobits per second. So according to our server, our client should be receiving each part of the audio stream with plenty of time to spare before it needs to be played. But clearly that's not happening because of the customer reports that we're getting. Okay, what about the client side? Yesterday, Guy talked about some really cool instrumentation that you can add to your client-side app. And this is especially useful if you're writing your client from scratch and you have access to some low-level native APIs. But let's say that this app that we're writing is browser-based and we're just relying on standard HTML5 support for playing the media files. The best we could do is keep track of how long it takes the audio file to arrive and how big it is. But that's not telling us anything different than what we got from the server logs. So we're back to square one. Our customers are definitely having a bad time, but our logs can't tell us why. Both sides of the application insist that our average throughput is fast enough. Now, if you're a suspicious person like I am, you might guess that the problem is that word average. Yuck. No averages, right? That's exactly right. If we were looking at a metrics dashboard, we would never allow ourselves to look at something so gauche as an average. We want percentiles or a full histogram. And in this case, showing how the throughput of our connection changes over the course of the connection. To do that, we need to peer inside the connection in a way that's not easy to do with server or client-side application logging. So to crack this, we need another vantage point. Our client and server logs have the best intentions, but as we kind of expect, they're lying to us. We need to look past them and instead look at the network itself to see what our server really sent to the client and when, instead of what it thinks that it sent. Okay, so what do we want to capture from the network? Historically speaking, there have been two things that are relatively easy to collect. The first is called flow data, or net flow. And this is the traditional answer, partly because business-grade routers, can collect this in hardware and will often provide it to you for free. So this is good. You don't have to worry as much about the collection side of this data source. You can just sort of tap into it directly and start seeing what you can see. And that's good. Unfortunately, flow data isn't going to work for us in this particular example. Just like our client and server logs, it can't peer inside of the connection. It's going to be a summary of the behavior of the connection as a whole. So it's going to give us that same average throughput metric that we were already getting from our application level logging. So not very helpful. Instead, we're going to focus on packet captures, or PCAPs. These provide a wealth of information. You get to see the size and relative timing of every packet in a connection. And you can see whether and when individual packets arrive at the receiver. And you can see into the state machine that TCP uses to decide when and how quickly to send data across the wire. This is exactly what we want. This is the visibility that we need to capture the information that we need to debug and solve our problem. Now, one nice thing to point out is that we don't need to look at the payload of our connections, the actual HTTP requests and responses that are being sent. Instead, we just need to look at the packet headers that our transport protocols use. Now, that's useful because it gives us a better privacy story. We don't have to look at any potentially sensitive information in the network traffic. And it also means that we don't mind if the payload is encrypted, which obviously more and more of that is true these days. More and more sites are moving to HTTPS. Quick is encryption non-optional. So if you need to sort of do deep packet inspection looking at the content of the packets, more and more connections are going to be outside of your visibility. So the fact that we don't need to do that is a win. This is also useful because otherwise our packet captures would contain a lot of data. I mean, a lot of data. Every single byte that's sent on the wire. But if we only care about the transport headers, we can ignore most of that. Don't collect it in the first place. And that's great. That gives us a substantial savings in the amount of data that we have to store and analyze. Okay, so we're going to collect some packet captures and we're going to test our hypothesis by looking at those PCAPs, both for the problematic connections, the one where we know that the customer is reporting this popping and audio dropping. And then we're also going to look at some of the PCAPs for non-problematic connections. And we're going to see if there are any interesting differences in the throughput characteristics of each. Okay, so let's look at a non-problematic connection first. So Julia, yesterday, mentioned Wireshark as a great way to dig into PCAPs that you've collected. And it's a great tool, and you should definitely be using it. So let's see. If we open up a PCAP in Wireshark, what do we see? I would argue that this is actually not very helpful. Wireshark is great. I'm not saying don't use it, but in this particular example, it's very dense and it's not really giving us immediately useful, actionable information. And in particular, can you tell me what the throughput of this connection is, just looking at that table? Right? If you've got really good eyes, you can maybe squint at those numbers and tell me, right? Because, I mean, the data is there. You can see the size of each packet. You can see the relative timing of the packets. And so if you do the math, you can figure it out, right? And you could certainly write some code that sifts through that as well and calculates those. But for manual investigation, I would argue that this is not going to cut it. And instead, what we want is a visual representation of the connection. So this is a notation called tracegraph, which has been developed by my colleague at Google, Van Jacobson. And now, without having told you anything about how this visualization works, you can at least see that it's like a nice, pleasing line. There's not any kind of weird kinks in it or anything like that. So just sort of viscerally, you can see that this is a well-behaved connection. But let's go ahead and dig deeper. What does a tracegraph show? So the x-axis is a measure of time. So it's usually the number of milliseconds or seconds since the start of the connection. And the y-axis is the number of bytes. Okay. So what's nice about this is that if you divide bytes by time, you get a bandwidth number. And so the slope of this graph is the throughput that you're achieving with your connection. So we can see not only that this connection is nice and steady, it's an evenly, an even line here without a very much, change in derivative or anything like that. But we can also run the math and we can see that in particular, it's holding steady at just under about 4 megabits per second. Pretty good. Okay, now what else can we see? Let's go ahead and zoom in this lower section of the graph here. So it's the very beginning of the connection. We're going to get to see if the behavior is any different as the connection is ramping up. Okay, so here we've zoomed in a bit, and we can see that at the beginning of the connection, it's not as well behaved as we thought. Now, we can also see now that we're zoomed in a little bit more that there's actually multiple lines on this graph. It's not just a single graph of the data in the connection. Okay, so in particular, we've got this green line, and apologies if the colors are a little bit washed out. I'll try to highlight it with the pointer as well. We have the green line, which is the sent line. So this is the data that the sender is trying to inject into the connection. And then the blue line is the acknowledged line, or the ACK line. And this is a measure of how much of that data and how quickly is arriving at the receiver. And now those are definitely going to be different. The entire point of TCP is to detect when there are differences between what the sender wants to do and what the receiver can accomplish, and to do the right thing in response to that. So it's completely expected that these lines are different and they have different shapes and gaps between them. And what's going to be interesting is looking for particular patterns in how they're different. Okay. We also have this yellow line here, which is the receive window. I'm not really going to talk about the receive window. If you know more about the particulars of TCP, we can graph it, but we're not really going to talk about it for the rest of this talk. Okay. Now we can also see that there are retransmits. So this place here where the green line is sort of moving up nicely, and then it jumps right back down. This is where the sender had to retransmit some data. So remember, the y-axis is the bytes in the sort of life of the connection. So if we see a particular y value appear in the graph multiple times, that means that the sender tried to send that byte multiple times. And so that's why this is an indication of retransmission. And you can see it very visually. There's a severe drop down in the sending line of the graph. And we do also highlight that with these red circles as well, just to really call it out, because those are often going to be sort of important points where you need to investigate what's going wrong. Okay, so now let's zoom in on some of those retransmits. So now we've zoomed in far enough that we're actually seeing individual packets. So we've got the individual sent packets here, and again, with the outline, the colors might be even harder to see, but in general, the one to the left will always be the sent data, and the one to the right will always be the received data, because otherwise you've got some weird non-causality thing going on. So we can see the individual packets being sent by the sender. We can see the individual acknowledgement packets coming back from the receiver. And when we do have retransmissions, we can see the individual packets that were being retransmitted. So that's great. We can zoom in pretty closely here. And we can also see this blue shaded region up here is what's called a cumulative ACK. So that's when a single acknowledgement packet comes back from the receiver, and it's acknowledging multiple sent packets from the sender. This usually happens because of a dropped packet or out of order packet arrival, but it doesn't have to be that. Okay, great. So we're seeing a lot of things here, and from this we can see that the sender is trying to send data faster than the client can receive it. And eventually the sender infers enough information about what the client can support, and it ramps down and it eases back. And we end up with a steady state behavior where the sender is sending data at the same rate at which the receiver can receive it, right? This is exactly what the beginning of a TCP connection is trying to do. And we can see visually into how that process works. Okay, so let's zoom back out again. Ignoring the beginning of the connection where we have that, sort of detect what the client can support behavior. We've got a nice steady state where the TCP machinery is humming along nicely. If we were to measure the overall slope of this graph, right, so just take the total number of bytes, divide by the total number of time, we would get the average throughput, exactly the same number that we would have gotten from our server logs and our client logs. And that's great. We can use this just sort of as a validation step that what we're seeing in the two different data sources lines up and is consistent with each other. Okay, so now the story is different if we see a connection whose throughput changes over time throughout the course of the connection. Now this is not one of those misbehaving connections that's causing the audio popping. This is just sort of a still smooth connection in the sense that TCP is humming along nicely and responding to changing network conditions. But those are real network changing conditions, right? We're seeing different throughputs because the network is actually supporting different values at different points in the connection. So we can see here at the beginning, we're getting about 75 kilobits per second, but then something causes it to ramp up. But maybe we're not congested as much. Maybe we're not sharing the link with the wife who's watching Netflix at the same time that I'm watching something on YouTube, as an example, right? So then the throughput that I can achieve starts to ramp up, and eventually at the end of the connection, we're getting more like 800 kilobits per second or so. So again, this is possibly when we're seeing differences in these graphs, it's not necessarily that there's anomalous behavior or misbehaving connections. It could just be that we're seeing into what the network is actually doing. Okay, so now that we've got this new tracegraph tool, let's actually take a look at one of those problematic connections. This here is zoomed in on just a portion of a connection that's misbehaving so that we can see some of the details better. And this does not look very happy, hopefully. Again, we haven't been looking at trace graphs for very long, but this is not a nice smooth line. It's not steady over time. There's clearly something going on here. The sent line is skipping all over the place. It's trying to send pretty quickly, and then there are these flat parts here where it can't send anything at all. There's places where it jumps back down and has to retransmit. And the flat parts here are going to be especially problematic when we dig into this a little bit more. But what is it that we're seeing here? This is an example of something called Bufferbloat. And I really like this frog. I think he's a good spirit animal for network problems like this. Bufferbloat is a pretty insidious problem, which we've known about for a while. But we've only really started paying attention to it in the last 10 years or so. But what is it? So let's go back to the trace graph. What can we see about the throughput here? So as I already mentioned, the slopes of the sent line and acknowledgement lines are different, right? So here we're trying to send, the sender is trying to send around 102 megabits per second. This is clearly not the exactly a packet capture from this example application, because I didn't write that example application. So the 102 megabits doesn't line up with the numbers I was quoting earlier. But the sender is trying to send really, really quite quickly, and the receiver can only keep up with about 25 megabits per second. So the sender's sending a good 4 times as quickly as the receiver can keep up with. Okay, so it's not just though that the slopes are different, because that's what we saw in the well-behaved example as well. That was just an example of TCP ramping up and figuring out what the client could support, and then taking that into account and being a good citizen and only sending at that rate. But if we were to zoom out from this connection, we would actually see that TCP is never recovering. We're always seeing this spurty behavior where we've got too fast of a rate, and then eventually things collapse somehow, either with retransmissions or with gaps. And then after a bit of time, it recovers, and we try to start sending again, but at the same too quick rate that ideally we would have detected and gotten around. Okay, so that's not good, right? The spurtiness isn't just ugly, and these flat periods here are the smoking gun for that behavior that the customer is seeing, right? So overall, on average, we're achieving a throughput that should be able to support the application use case that we care about. But what's actually happening is there's these large gaps here. So the client receives some amount of audio data, starts to play it, and then the connection drops out. And by the time the sender starts sending more data, the client has run out of audio to play. And so they have to stop. And so yes, on average, we can maybe sustain the rate that we care about, but it's not the average that we want. We want to look at these histograms, just like we talked about. And so these flat parts here are especially bad. Okay, so this is great, right? We've figured out what's going on. We've solved our problem. Well, not really. We've explained the behavior, but we haven't fixed it. So how do we do that? One option is that we could have our client buffer the audio data that's coming in and wait a little bit longer to start playing, right? And what that's really going to do is it's going to mean that there's more wiggle room, right? We're not going to solve the network conditions. We're not going to fix them. We're just going to try to mitigate them when they happen. So if we have a large enough buffer, then we can continue to play the audio while we wait for the the connection to start back up. And the hope is that our buffer is long enough that we can, sort of get over any kind of gaps that we do to discover. Now that might seem like a hack, and it's probably not the best user experience, right? They're going to ask for a song, and we're going to say, oh, I'll start playing that song for you in about 30 seconds so that I can hopefully get around any network conditions that happen. That wouldn't be the best. I will say it's at least a hack that's informed by data, right? We can set that buffering value to actually be in line with the network conditions that we see for real customer traffic. So not ideal, but in some cases it might be the best that we can do. Is there a better way? What's causing the buffer bloat? And can we get rid of it? If so, then we wouldn't have these outrageous gaps that we have to smooth over. So this is a nice segue into another one of the performance metrics that you can see visually in a trace graph, and that's called latency, which is a measure of how responsive a connection is. So not how much data can you send and how quickly, but a raw measure of how long does it take any individual piece of data to arrive. And the specific thing that we usually measure is called the round trip time. How long it takes for an individual packet to make it from the sender to the receiver, and then how long it takes for the acknowledgement from the receiver to make it back to the sender. So round trip because it has to go both directions on the wire. And we can see the latency of a connection, the round trip time of a connection in a trace graph, just by looking at the horizontal distance between the sending line and the acknowledgement line. And that's telling us for an individual packet, or a byte of data in that packet, how long did it take for that byte to be acknowledged by the receiver. Okay, so for this buffer bloat connection, what's interesting is that we're seeing very, very different latencies at the beginning of each, I'll call it spurt, than at the end. The latency grows sort of as the data is being sent along the connection. And what's happening? This is the smoking gun that tells you that this is a buffer bloat problem and not some other kind of performance issue. Very, very briefly, the problem is that there are some routers in between the sender and the receiver on the internet. And those are very deep in the bowels of the internet inside of ISPs that we have no control over, and we have no control over how they're configured and what they do and how they're linked together. But we do rely on them for our data to make it from the server to the client. Now the problem is that some of those routers have buffers in them, and the buffers are too large, hence the name buffer bloat. So now when the server is sending data too fast, TCP relies on some kind of feedback mechanism from the client. Basically a signal saying, whoa dude, back off. And if we can detect that signal on the server side, the server is well behaved and nice and gentlemanly, and so it backs off and slows down to a rate that is sustainable. And the problem is that these large intermediary buffers out in the internet get in the way of that signal making it from the client to the server. There's interesting technical details in how exactly it gets in the way, but the take-home message here is that the sender can't detect the signals that the client is trying to send, saying, I can't keep up, back off please. And that's what causes the sending rate never to tamp back down, and eventually the ability or the inability of the client to keep up becomes catastrophic. Right? It's not just that like we're dealing with packets being dropped every now and then. It's that we actually get into one of these failure cases where we're not sending any data at all, or where we have to start resending data a lot. Okay, now the ideal solution here would be to get those intermediate routers to shorten their buffers. But again, we don't have control over those routers, so we can't make that kind of a change. That's not really an option. Now, if you're running a fairly recent Linux kernel on your server, you can activate what's called BBR, which is a new congestion control protocol that some of my colleagues at Google have developed. They published it in a paper, and they've committed it upstream to the Linux kernel, so it's available now for use. There's not nearly enough time to get into how it works, but the short version is that they use a better, hey, please back off signal from the client, one which is more able to make it through those large intermediary buffers. And then the server can detect that signal and ramp down its sending rate, everything's hunky-dory. And it works in the presence of those janky routers that we don't have any control over, which is really the key there. So all is not lost, kind of. We have a solution if you have control over what kernel you're running. If not, there's various sort of application level things that you can do to mitigate. I won't try to claim that we've solved everything here with happy unicorns, but we've at least got some data that we can work with to tell a good story about what happened and what we can try to do to react. Okay, so what have we been doing with all of this? We've been looking for interesting patterns in these PCAPs. And ideally, we were able to do some of that visually, which is nice because as humans, we're much more visual people, so that's better for our pattern detection. But we really haven't talked about how to get those PCAPs in the first place, right? I sort of started with, hey, I've got a PCAP, let's open it up and see what happens. But how are you going to get them in the first place? So let's start collecting some packets. We've got these huge stream of packets going in and out of our servers. How are we going to capture them? So a good first step is to just run TCP dump on your servers. Try running it a few times manually to get a handle on what a PCAP file looks like. And I'm going to sort of defer here to Julia, because she gave a really good overview of that yesterday, and she's got a great zine that you can download that goes into more detail. So definitely check it out. Now, in her example yesterday, she used TCP dump as a one-off, right? She was responding to a particular problem, so she logged into the server and started running TCP dump with a very particular filter expression because she knew which packets she was looking for. And she saved those and looked at them and answered the problem. And then, importantly, she turned TCP dump off when she was done investigating this problem. Okay? We want to do the same thing, but in a continuous, long-running way. We don't know in advance which packets we'll need to look at. And we don't want to turn off the packet collection until we turn the servers off themselves. Okay? The good news is that you can still do this with TCP dump. Instead of starting it manually, just let your existing job control system make sure that a TCP dump process is always running on each server. Right? You've already got something, presumably, which is making sure that the server application itself is running there. You're not logging in and manually starting that. So use the same mechanism just to make sure that TCP dump is running. TCP dump includes options for rotating its output files in a number of ways. So if you use one of those, your long-running TCP dump process will end up creating a big pile of PCAP files in a directory of your choice on the server, on each of your servers. Okay, so now you need to ship those files to some other location first so that you can analyze them in a single centralized place. But more importantly, so that you don't fill up the disk on your servers, right? We're writing lots of big files, we've got to get them away somehow. So again, let's not go crazy. If you don't already have some kind of dedicated file shipping service to draw on, just use rsync and a cron job, right? It doesn't need to be rocket science. This is a great start, and it doesn't rely on any tools that aren't readily available in your favorite Linux distribution's package manager. So it's great. Okay, but you might need more control over your packet collection, in which case you should switch to libpcap. This is the C library that TCP dump is using under the covers to actually tap into the stream of packets flowing through the kernel. It's not that bad of an API to program against, and you can find bindings for it in pretty much any higher level language that you might want to choose from. So this is not saying that you have to start writing anything in low level C or anything like that. So writing your own packet capture program opens up some interesting possibilities. You can create a more complex filter than you could get from TCP dump's filter expression language. So for instance, Google, as you might expect, has a lot of traffic flowing across the edge of its network, all of the cat videos that anyone's watching on YouTube in particular. And so we need to sample our PCAPs somehow. We can't collect everything about every single connection. There's just too many of them. So what we do is we use a flow sampling filter where we don't collect information about every connection. We only collect information about some of them, a statistically sampled subset of them. But importantly, for every single connection that we collect, we want every single packet in that connection. So we need to have something about the connection itself be part of our sampling logic. Now that is something that you could write as a filter expression for TCP dump, but it's going to be hairy and ugly, and it's not going to be fun to write by hand. So you could do it in code instead. You can also have your filter expression change over time. So one of the things that we're doing in our stack is that we are biasing our sampling to target customer populations that we think are, or that we suspect are having issues. So sort of like we're sort of collecting nice and evenly, and as particular client populations start to give us signals that problems might be occurring, we shift it so that we collect more packets from those instead of from other client populations as a way of trying to verify that sort of suspected outage that we're seeing. And that's something that you can only easily vary over time if you have a more programmatic interface with your packet collection. And lastly, it means that you can make this more real time. So with a custom collection program, you don't have to write the packets into a file and then rely on something like rsync to send them back to an analysis server. So at Google, for instance, we have a nice, well-supported company-wide RPC system. And so our packet collection daemon can just inject the packets directly into that and send it back to our analysis servers without ever having to write it to disk first. So that's good because we're saving some disk on the server side, which, that's a non-trivial win. But it also means that if we do a small amount of the analysis at the collection point instead of back at that centralized location, we can get a really useful signal about certain bits of high priority outages within seconds. Right? We're doing it immediately as soon as we see the packet that exhibits the behavior, and we're sending a signal about that back to the rest of our monitoring stack right away. So you can definitely do something with libpcap that's pretty cool. Okay, great. So at this point, we have a good story for capturing packets from our servers. And we have some interesting patterns that we can look for in those PCAPs. But you'll notice that this was a pretty manual process. Whether we were using Wireshark or Tracegraph, we were only looking at a single connection at a time. And we don't want to throw that away, right? That's definitely useful when you need to do manual debugging. But we also want to turn this into something more automated, requiring less human intervention. So with this audience, I can safely assume, hopefully, that you have a decent story for that, for automating your monitoring story based on signals coming in from all of these data sources. Or at least that you know that you need a good story for that, and you're actively working towards making it happen. So what's nice about these packet captures is that with care, they're not really different than any of the other data sources that you might want to tap into. So what do I mean by with care? Well, we're not injecting the packet captures themselves into your ELK stack. What we're passing into that is the results of this analysis process. So you end up with something that looks like a JSON blob, right? You've got the timing information about the connection. You've got some aggregated or anonymized information about the client and server side. And then importantly, you've got the results of your packet analysis. Did this connection exhibit buffer bloat or black holing? What was the throughput that it achieved? Okay, so we're done. I'm being signaled that we're running out of time, so take-home messages. Packet captures are useful. You can find useful information in them that you can't get from other data sources, I would claim. But in order to leverage that information, you don't need to make any outrageously large fundamental changes to your monitoring stack. This is just another data source. Okay, and with that, thanks very much.
And we'll have a brief sponsor interlude. Thank you to Big Panda.
Hey there, hear me okay? Good? Just gonna do something a little bit different, but due to the demo issues, I'm gonna wing this, which means I'll talk really fast. So anyway, Big Panda's been a sponsor of Monitorama at least every year it's been here in Portland, so the past 3 years. Super stoked to be back. Big Panda's not based here in Portland. I am and work remote, so I had all my New Relic and other startup friends around here. So I'm going to talk a little bit about just sort of monitoring landscape in general and some thoughts around machine learning and how that can help. To set some context, we did the State of the Monitoring survey last year, and essentially the idea was to kind of understand who was using what tools, how they were solving the problems, what some of the major challenges were. We updated it again earlier this year, and you can find the full version on our website. We were looking for like about 600 responses, and I think we got over 1,500, so there's a fair bit of interest in that space. Ultimately, the first bullet just kind of makes me sad. Despite a lot of the awesomeness that comes out of places like here in Monitorama and some of the new vendors and tools, monitoring is still generally perceived to do fairly challenging, or at least to do it properly. And the common theme in a lot of this is just sort of the tool proliferation problem, right? Lots of tools, lots of old crusty tools that can't be removed, and lots of new tools coming down the pipe. And one thing we did this year was segment it out by SMB or enterprise, and things are a lot worse for enterprises. And by that I mean essentially companies with more than 1,000 people and tend to have some sort of centralized knock. So one of the things we announced last year, and this looks like a bit of an eye chart here now, so I apologize for that, is this construct called a monitoring scape, which was really just a bit of a handy index to try to track who's doing what in this space. And so we update it regularly. You can find the full interactive version on our website. It's got a lot more details. If you're a vendor and you'd like to be listed, just reach out to us. It's intended to be community driven, but just sort of like captures how busy the space is and what the new people are doing. So essentially, this comes down to you have a bunch of tools. They're generating a bunch of different alerts, and in many cases, a bunch of different notifications or tickets. So I don't think I really need to explain to this crowd sort of the challenge around monitoring tool sprawl, nor do I need to really explain the fallacy of like one monitoring tool to rule them all, right? I mean, that's just never really going to be the realistic case. I think different people and different teams are going to always have different tools to monitor the specific things that they essentially have to support. There's always new things coming down the pipe, but tool replacement's really, really painful, right? There's often legacy tools that are just there to monitor. Oops. Sorry. Legacy tools that are there to monitor legacy systems. And there's been a ton of work like setting up monitoring tools. There's a ton of configuration. Just ripping and replacing is really, really difficult. But I think the point is that there is actually a lot of value in that very specialized monitoring and the monitoring data, because it is tuned for the things that it's being monitored for. The trick is kind of figuring out how do you harness that, right? So one easy approach is this construct of alert correlation. And so we heard yesterday why one alert should not necessarily equal one page, particularly if there's a bunch of alerts and those things are related. But in order to do correlation at scale and to do it quickly, you need to be able to do it automatically and accurately. And so machine learning is actually a fairly good application to do that. The basic process is to essentially get all of the raw alert data into one place, then normalize it so you can manipulate it, enrich it, and by enrich it is essentially adding that important context we heard about earlier today. For large enterprises, that often means pulling in metadata from things like CMDB, which surprisingly, yes, still exists. ITIL is still a thing. And then once you have that, you can essentially use these patterns to apply correlation logic and generate dynamic clusters to essentially group the related alerts into events or incidents. So if you break down, that's essentially really a bunch of manual repetitive work or tasks that could be done by humans, but are better suited to be done by machines. So it's a really good fit for essentially machine learning capabilities. And here's a really brief example output of using machine learning to essentially automatically correlate alert data from multiple sources and then roll it up into the construct of a simple incident. I think that's over like a 4-hour time frame. And again, the idea here is not necessarily to be able to say, here is exactly what the problem is, but rather to understand, where you might want to do more investigation, or for large teams where you want to escalate or bring in other people for help. It's pretty straightforward, but again, if you had to do this manually by looking at a bunch of different graphs, a bunch of different data sources, it would take a fair bit of time, particularly if you were doing it during an outage. So, alert correlation is well serviced by machine learning, but if left unchecked, uncontrolled algorithms can actually result in under or over alert correlation. That's not really going to help with alert fatigue, and it actually could make things worse with a bunch of false negatives. So I think the real, or a better approach here is when you can sort of augment a lot of the machine learning algorithms with human inputs to better tune and adjust the underlying patterns. So if you can sort of show the patterns that may be automatically detected and then allow humans to provide inputs to sort of adjust them, you can essentially create correlations with a lot more confidence. Without that, you're just kind of like ceding control to the algorithm is a bit of a black box. So there's some, automatic correlation is kind of a space where a lot of things are happening today. There's some newer things coming down the pipe, from dynamic thresholds, anomaly detection. I'm actually stoked to see some of the people here releasing some things that actually make this maybe a little bit nearer future than I was expecting. So I'm pretty optimistic about what the future holds. Or it's just going to be Skynet, and then we'll get to hopefully play with a bunch of laser weapons. Anyway, I know I'm blocking lunch. I'm Canadian, so I figure I should live up to the stereotype of apologizing for that. So thanks for everybody to be here.
All right, and our final speaker before lunch is Eric Ziegler from PagerDuty. Round of applause.
Thank you very much.
Your water.
Here we go. Here we go. Pointer. Da, 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 da. All right. So howdy. My name's Eric. And I'm going to talk a little bit today about instrumenting the rest of the company, and looking for useful metrics. Alternatively, this title is called Lies, Damned Lies, and Hacky Scripts. A little bit about me: I've worked at a whole bunch of different companies. Apparently, I can only work at companies that have a green word mark for a name. But slightly more useful is that I've jumped back and forth a whole bunch between being an individual contributor and being a manager. And one of the weird things, this is also a slide, is why I can't tell what I want to do when I grow up. One of the things that I noticed when I first switched from being an engineer to being a manager was that I spent a lot more time in meetings. But beyond spending more time in meetings, I'd spend more time in meetings with people who weren't quite as metrics inclined as everyone in this room. I'd spend time in meetings with sales folks and with marketing, and I hear this common pattern over and over, and it went something like this. We have a problem, foo, so we're going to do bar. And it would literally just kind of be thrown out as an assertion of fact. And this was kind of nerd sniping for the engineer in me, because I would immediately go, wait, how do you know? What data did you know? How did you find out that foo is a problem? How do you know about this? And if you do bar, how are you going to measure that it's actually going to change anything? And I'd kind of get this response that would sound an awful lot like Charlie Brown's teacher noise of womp, 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 womp. Well, we really can't actually measure either foo or bar. I'd hear this high-pitched noise in the back of my head that I was pretty sure was Demings doing 5,400 RPM in his grave. Because without data, you're just another person with an opinion. And a lot of meetings I would be in, I would just be like, we're just arguing about each other's opinions and not actually facts. And I'm an engineer. I like solving problems. So I'm going to go out and I'm going to start to write code. Even though I'm a manager now, I've got that engineering background. And so over time, I would just show up at the next meeting with facts, or like, here's what I found out. And over, I would do this. And then people learned to nerd snipe me into doing their work for them. But I started to have this collection of shell scripts, or Ruby scripts, or Perl scripts, or whatever at the time, and I would keep this on my local laptop. And I actually started to get kind of, felt bad about this. I'm like, I'm being an engineer when I should be a manager. Apparently I'm supposed to have arguments about opinions. I also like that apparently my naming scheme is more consistent than my choice of language. Apologies for the small font. And it turns out I talk with other engineering managers, and they do this too. So the kind of first takeaway from this is that if you're looking for metrics, the odds are somebody else in your organization probably is too. So what I thought I'd do today is share 3 little stories about different ways I've gone hunting for instrumentation and telemetry in my companies that I've worked in, and hopefully you can take some of them back and maybe do them in your own organizations. So this first story here was sitting there and was hearing about new folks coming on board, and I heard kind of a complaint. And it was, we have a problem with people not knowing what the chatbot does inside our company. So we're going to write better documentation. Wait a minute, this is a chatbot. Really? We use the chatbot to deploy, we use the chatbot to find out about, oh, I have to aim that way. We use a chatbot to find out about the environment, we use a chatbot to converge chef, we use a chatbot to provision hardware, and apparently there's a lag. And really, we have to write things on Wiki that nobody else is ever going to read? What's actually going on here? Why are people finding it difficult to understand how to use the chatbot? Can we use Slack? Can Slack's metrics basically tell us maybe a little bit more? Are people getting confused? What's the instrumentation there? This is the grand total of what Slack gives you for statistics. That's probably a good thing because Slack is awesome in many other ways. But what we really need is we need to just grab the set of events and what's coming off this chatbot and record it, like a stream of events, and then show them on a graph. If only we had such a tool. So we did. What we did is we ended up writing a plugin to shove pretty much everything that we saw come across the bot framework into StatsD. And it's the same Datadog dashboards as we use for everything else in developing the product. So it's a convenient tool chain. It's already set up. The chatbot host already has StatsD for all these other reasons. So it's just one more set of data. And we started to dig into it. It's like, okay, cool. Here's when there's valid commands being sent. Here's when there's invalid commands being sent. Here's who's sending them. Here's what the syntax is when it works and when it doesn't work. Here's the most popular plugins. Here's the least popular plugins. Why are they least popular? Of course, what we also found out was that Lunch was one of the most popular plugins. Thousands and thousands of hours and lines of code to provision code and provision hosts, and Lunch is what's most popular. And so the outcome was that instead of writing documentation on a wiki that nobody was going to read, we were able to dig in and actually find out, oh, okay, here's the commands where somebody is having a problem or isn't getting the syntax quite right. Let's go fix that. And so it's a better experience for everybody involved. And our bot now has KPIs. Our bot actually now has basically, you should not have this many invalid messages sent to you, or you should have this many valid messages sent to you. And it's a way better way of thinking about internal tooling than just as, it's not working again, complaint. So reusing your existing metrics toolchain with other internal tools in your organization is useful and it can make sense. The second story came about, again, apologies for anybody who's ever run Jenkins or things like that. This can be a little sensitive. But sitting around engineers one day, and we have these flow tests. So what we're going to do is we're basically going to complain a lot about it. And I actually don't mean that as negatively as you might think. So the problem was that the engineers and everybody writing these tests or using the CI system, they didn't know what the problem was. Some people thought that it was the database fixtures framework. Some people thought that it was we were doing too many of a certain kind of test. Some people thought, well, our CI hosts are under provision, so we need to change to a different CI tool. And everybody just kind of kept taking random guesses and complaining about it. And so, okay, let's dig into this. Well, what's the first problem is you're saying that CI is too slow. Define slow, right? If I was to go to you and say the website's slow, one of the first things hopefully you'd ask is, what does slow actually mean to you? Is it 1 second? Is it 5 seconds? Some sort of a threshold, and get that baseline so that we know what to start comparing against. And it turned out that pretty much every engineer would run tests locally on their laptop, and if the CI system was any slower than what they were able to do on their laptop, then they started to complain. So, okay, cool. Let's go into the CI system and start grabbing the metrics. And Lo and behold, the CI system didn't quite have the same good way of getting metrics. Let's use the same trick as before. Let's stick a script at the end of the CI, at the end of the test run, and let's grab timestamps all throughout, and let's just emit those back in as statsd. And we have kind of a complicated setup, so we're able to capture like the different build dimensions across a build matrix. Okay, yay, we get a pretty graph. And the pretty graph shows that tests are running and nobody was doing anything in the middle of there. But the problem is when we got the pretty graph and we got the instrumentation, it didn't show that the tests were that much slower. They were kind of creeping up there, but they weren't creeping up there anywhere near enough to be the problem. So a little bit of lag. So we dug into it and we're like, okay, so we've just had instrumentation now. We can show that the tests are taking about the same amount of time on CI as they are on your laptop. Broken down for build matrix and all that. And dug in further and it's like, oh, so what you're perceiving as the test being slow is actually the time that little dot goes from yellow to green on GitHub's pull request status. Oh, okay, so this is more along the lines of the tests are taking too long to start, or they're taking a variable amount of time to start. Okay, well, we can't actually grab timestamps from a script if the script hasn't started running yet. So let's go to the CI tool and see if it can start to give us some of the data from its API. Only problem is that its API didn't expose, this is a job queue waiting time, and the API didn't expose it. So once again, scripts to the rescue here. And this is a sort of script I actually found that somebody else had written the exact same copy of in the same company to answer the same question in a different way. And let's go emit those metrics into Datadog and start to dig into it. My apologies, I don't have quite a pretty graph here, but the outcome of digging into it and finding out how many jobs were being run and when the queue wait time was we have Scrum teams. Those Scrum teams work on 2-week sprints. Those 2-week sprints have ends, and they would all wait until the end of the end to merge their pull requests. This is actually a good thing, right? Because what we did is we found out, okay, our CI worker capacity needs to be related to the number of engineers, but we also got to have a conversation with the agile coaches about, let's maybe have a conversation inside our Scrum teams about not all merging on the last day of the sprint. So the takeaway here is that there are metrics that you can grab, but you might need to kind of reverse engineer your way into them and find basically the overall metric and then kind of dig around to find the specific one inside it that you need to find, that you need to use. So for the third story here, so like I said, that question is about we're going to do foo because of bar. Well, sometimes you can't actually stop bar from happening. In this particular case, the engineering managers at this particular company and the senior leadership wanted to ship faster. And it was kind of recognized that the organization wasn't working right. So we're going to reorganize. Great. Not going to probably stop that. But everyone who's ever been through a reorganization's probably asked the question, why are we bothering with this? Or did this actually do any good? When we reorganized, did we actually do foo? Did we do that shipping of that code faster? And well, this is what tools like Jira are for, right? Oh yeah, well Jira will just show us the sprint burn down chart, and we'll have magic graphs that will go bottom to down and to the right. But I guess that's a good thing. The problem is though is that Jira and some of these productivity tracking tools, they're not actually showing where the bottlenecks are. They're showing the kind of overall team behavior and the team health, and they're valid. But if you're reorganizing and you're trying to find ways that every team can, say, own their own service and their own repo and be responsible for their own production hardware, you may not be able to capture all of that inside of these kinds of productivity tools. So what we did is we said, okay, what's the unit of change? What's actually shipping code faster mean? Well, it means pull requests. Pull requests stay open way too long. So if pull requests start to close in less time, then we're probably shipping faster. Problem is, again, GitHub doesn't show pull request length of pull request time fairly easily. So what we did is a little bit of overkill, but we piped GitHub metrics into, in this case, AWS Redshift and Mode Analytics, which is kind of a visualization tool. There's Looker, there's all sorts of other stuff. And it's a little bit of overkill, but the not the good part is that the BI team already knew about all of it. It wasn't introducing another new tool into the tool chain. So they are taking care of that GitHub data import. And it's one less thing that everybody has to worry about. So, okay, cool. Now we've got the data in a data warehouse, GitHub pull requests in a data warehouse. And you can use things like SQL. Okay, so now we've gone from, well, I really hope that pull requests answer faster, or even hacky shell scripts, to SQL that's just sitting there running in the rest of your business intelligence tools. And what we wanted to ask the question was, this dark green line here, right, this is median pull request open time, how long it stays open for. It's like over 20 days. It's like over almost 2 sprints. And the whole point is you're supposed to ship in less than 1. So let's go start making all of these organizational changes and having lots and lots of one-on-ones where everyone asks if this is really worth it. And then being able to show the graph. Yes, it's not just you. You're not just imagining things. Your pull requests are closing faster. And being able to show that across the whole organization. So it only took, the outcome was productivity success. It only took a year's worth of pain and sweat to do it. So the takeaway here is that sometimes you aren't going to be able to instrument exactly what it is that you want to find out. Human beings don't have stats-D endpoints yet, or hopefully ever. But you need to make sure that you can find those proxy metrics. Just be really, really careful and choose wisely, because sometimes you'll pick a proxy metric that might incentivize the wrong behavior. And a couple of little potpourri items here that I couldn't fit into any of the other stories. First one is that there's a lot of different ways that you can find this data and then start shipping it into a stats-D on a regular basis. Culling through chat logs, culling through your email. One of the more entertaining ones I've seen is a former manager of mine has a script he runs every week that basically culls all of the calendars for everyone who reports to him and does a percentage time in meeting. And that's tracked, just like, and it's, it's not like a thing that anyone's going to get docked for in their performance reviews, but it's tracked to be like, hey, I noticed you've been in a few more meetings than normal for the last couple months. How's everything going? It's another indicator of health, and it's easy to collect. Cross-validation of the metrics. I didn't quite show this earlier, but one of the graphs that I was going to kind of show was, we showed that the pull request time was going down, and then we were also able to show that in Jira that the sprint velocity kind of increased. So it's good to necessarily sometimes look at the different metrics to be able to cross-validate, hey, did we actually collect the data we think we collected, and is it behaving the way we think it is? The problem is when you start to think about metrics and metric behavior, this is a whole talk, but there are a whole series of cognitive biases around metrics that also can act like kind of combo modifiers and basically multiply on each other. So it's not just one cognitive bias, but a whole bunch chained together. And one last thing here's a problem I haven't really seen anybody solve yet, and I would love to hear if anybody has. Plotting against organization metrics. So when you hire additional people, like the overall number of engineers, like we saw earlier, plotting number of engineers versus number of CI workers, or revenue numbers or things like that, plotting against those can also be really helpful. So to kind of jump through my takeaways real quick, because I'm sure everybody wants lunch, useful metrics are everywhere. There's all sorts of data if you haven't gone looking for it. You aren't alone in digging for it. The existing toolchain, stats-D, is meant to be flexible. It's meant to be this flexible toolchain that you can put any metric into. This is just another kind of that data. You can reverse engineer and find proxy metrics for a lot of the questions you might want to ask. Thank you.
It's lunchtime. Go away. We'll be back here at 2:30. We'll be back on track in the afternoon. There are speakers, lightning talks, and then we'll be done for the day. Thank you. So we're going to have a really chill, really quiet afternoon. It'll be great. And to get us started is, did you say J. Paul? Yeah. Cool. Is J. Paul, who's going to talk to us about science and monitoring. Sure. Yeah, cool. You're talking about science now.
Science, yes. Science. All right, welcome to the second half of Monitorama. So I just wanted to actually, before we get started, call out Jason and Will and the whole Monitorama crew for dealing with the interesting situation this morning. They've been doing a great job making sure that the speakers are up to date, you're all up to date, so I think we should give them a round of applause for that. They've done a great job. The one thing I will say, I don't know why they just didn't load the holodeck program from yesterday's. That's kind of odd. Also, channeling my inner Joe D'Amato, greetings Pacific Power. They tweeted this morning, and I know of at least one person who might have a question or concern about their service. So you might be saying to yourself, chaos. That's kind of interesting, whispers in chaos, what is that about? Well, today we're going to be talking about incidents. And I'm going to do a little survey to start us off. And I want you to keep your hands raised. Raise your hand if you're an operations person who deals with incidents. All right, so raise your hand if you're a developer who gets pulled, keep them up, or raise your hand if you're a developer who gets pulled into incidents. And raise your hand if you look at these people working incidents and just want to know when the website's going to be back up. Okay, that's like pretty much everyone in the room, right? So there's an interesting question that comes up. How do you know an incident is occurring? How do you know an incident is occurring? We're at Monitorama. Monitoring. It's not a trick question. Someone in the corner is like, Lisp. Lisp is how you know that incidents are occurring. No, just monitoring. But so once you know that an incident is occurring, then it's a good question to ask, well, how do you know what to do when an incident is occurring? And you might think about that. Like, have you ever thought kind of in a meta sort of way, how do you know what to do when an incident is actually in progress and you're responding to it? How do you know what your team is doing, right? So a little bit about me. I'm not going to go through this slide. This slide is mostly about the tweets, so you can tweet me. It's got my Twitter name. The other thing that I would note is I'm currently a Masters of Science candidate in Human Factors and System Safety. And the reason I mention that is because a lot of the things that we're going to be talking about actually come from the Human Factors and Systems Safety Sciences. So the first part to sort of answering this question of how do you know what to do when an incident is occurring is to look at how humans react to problems in general, how the human brain reacts to problems. And you might have heard of this. There's generally two systems in the brain. This idea of system one, which is sort of automatic, quick, no effort, no real sense of voluntary control, if you will. And of course, then this idea of system two, that actually takes time and attention. Our brain actually has to use some sugar to do some work, right? And what's interesting about system two, actually, is that when your attention gets diverted and you're doing a system two problem, work on the system two problem actually stops. It's kind of interesting. Now, if you've heard this theory, it's from Thinking Fast and Slow. This book is a really interesting book. It's a very thick book. I think it's like 600 pages because it covers all of Daniel Kahneman's work throughout his entire career. He won a Nobel Prize in economics, I believe. So what do we mean by, what are some examples of systems one, systems two type thinking? Well, system one, complete the phrase bread and cheese. That works. Bread and butter, right? 2 plus 2, right? Stuff like that. One of the things that we'll come back to that I find really interesting, finding a strong chess move is actually a system one thinking if you're a chess master. So that's kind of interesting. And of course, system two, the examples they give there, counting the occurrence of the letter A on the slide. I like that filling out a tax form is supposedly less complicated than checking the validity of a complex logical argument. So, like most things with the brain, though, it's more complicated than that. And that doesn't necessarily tell us much about how we might react ourselves and how our team members might react while we're dealing with an incident. So to look at that, we're going to look at some research that this gentleman did. And if you know who this is John Allspaw. He worked on the Velocity Conference as one of the conference co-chairs for a number of years. And he actually did his thesis on exactly this issue. If you can't read that, it's Trade-offs under Pressure, Heuristics and Observations of Teams Resolving Internet Service Outages. Are there any people, I know there's at least one person from Etsy. Are there any other people from Etsy? Because if you probably knew this, he studied one of Etsy's incidents. So the beginning of the incident on December 4th, 2014, during the busy holiday shopping season, it was reported at 1:06 p.m. that the personalized homepage for the logged in users was experiencing loading issues. So that was the incident, and that's what the engineers working that incident were faced with in terms of that was the information that they had. Now, if you've seen me present before or you've read Sidney Decker's Field Guide to Understanding Human Error, you've probably seen this before. This is his sort of example of what a really good timeline would look like. And so you can see it's got data, it's got what people actually did, and then of course what people said. So one of the first things John Allspaw did is he actually made an incredibly detailed timeline for this incident. So this is kind of a data trace just for one engineer that shows a number of things, the diagnostic activities that they took, the actions and responses. He actually had logs of dashboard access, so he could look at what logs people loaded in their web browser. Also staff directory access, so who were people trying to find information to go talk to. Princess requests, which I believe have to do with deployment, is that right? Pre-production, yeah. And then production site requests. And so what's interesting is because software is a team sport. Oh, one last thing real quick. And he also basically identified what he calls episodes. So that's what these lines are. So he was able to start correlating, okay, well, if you look across all of these things that this one engineer is doing, and there's a timeline up here, a time-stamped line that shows these episodes, well, because software is a team sport, he actually did this for all of the engineers involved. And this is a bit of a different trace. This is actually a trace of IRC lines in an IRC log. So when who said what. So he identified 3 heuristics, or what we might call sort of monitors for our brain, things that our brain might look at, that engineers use to work on an incident. Oops. Heuristic number 1, change. Did anyone change anything? Did anyone deploy anything? Was there a commit that got through the continuous delivery pipeline? Answering this question, so what has changed since we last had a good known state? So that's the first thing that engineers go to, right? Who changed what? When did they change it? And that seems pretty natural, right? That's probably what a lot of us do. But then the question is, okay, well, what happens if nobody changed anything? And that's actually the case in this particular incident. There were no deploys at the time. There were no commits that had been committed. So what do you do then? Well, in talking with the engineers, he found the second heuristic that that those engineers used as operations engineers was to actually go wide, right? And it's funny to read the transcripts from the interviews that he did afterward, because there's a sense from all of them that when I don't know what it is, there's actually, the funny thing is there's a bit of a sense of dread, and also okay, time to go as wide as possible. So we go sort of from thinking about the problem on Earth to like, what could it be at all in all of the universe? And start looking at all sorts of things. Now, this was described by an engineer actually as sort of oscillating between a breadth-first search, and then when you see something, one thing that it might be that, then immediately switching to depth first and going as deep as you can on that particular issue. And as soon as you find that it's not that, or you rule that out, you actually go back to breadth first. And he had a number of engineers say that that's when they think of that problem, they go breadth to deep, back to breadth when it's not successful. So, one of the other interesting, the third heuristic that he found actually kind of facilitates this going wide, if you will. And he called it convergent searching. So, confirming and disqualifying diagnoses by matching signals and symptoms. So this is that idea of how do you actually make that switch between breadth first to depth first back again? What is the heuristic you actually use to do that? And so what he actually found is that engineers are confirming or disqualifying a specific and past diagnosis that comes to mind. So in other words, they will think of things in the past that was very unique and specific that sticks out to them to this day. And they will use that to confirm or disqualify the signals and symptoms that they see or hear. And the other thing that he found is that people will also use their general and recent diagnoses to actually look at these situations. And if you think about it, this is actually kind of fascinating. What this actually is saying is people either use a really, really painful incident that they remember for like their entire career, or they use the stuff that's in your L1 cache from the last incident that you had. And what's interesting about this is that the generalized things are the only things that stick in your L1 cache. So you will remember very specific things that 36-hour incident that you worked, you will tend to remember details in that system and look for those. But when it comes to past incidents that you may have run that may be smaller in scope, you're really only looking for generalized patterns that you can see. So that's kind of interesting that we split, that third heuristic really supports the second one. So, back to the incident. Well, you might be asking yourself, okay, well, what actually happened? What was it? And it turns out it was kind of an interesting confluence of events. It was caused by a CDN cache miss due to an HTTP 400 status in an API from a closed store. So they have stores that get closed for various reasons, non-payment, things like that. Referenced by a blog post in the sidebar from an employee. So what had happened, and you want to talk about the confluence of complex systems, an employee had written a blog post. And a lot of the engineers actually thought it was to do this featured shop module or some of these other modules on the sidebars, but it was actually more from the blog module. That employee posting that post caused the page renderer to make an API call for a closed shop. And nobody ever thought that that connection would actually work. And then because of the cache misses, it was causing this page to take 4 seconds to load. And when you're doing this during Cyber Monday, it's a problem, right? So this is what's called a process trace. And this is kind of the other way to look at it. And I want to point out a couple really interesting things that sort of go back to that idea about heuristics. So the first thing is that infrastructure engineer 2, and you can see that person is, most of their work is represented here and a little bit down here. They focused on frozen shop, which was basically the problem, relatively early on in this process. And if you go back and look at the transcripts, you've got all of the other engineers, network changes, WordPress issue. Somebody asked featured shop, right? Featured shop loading, okay. But this engineer in particular sort of fixated on the frozen shop issue and kept working it for, if you look at the time they took to work it, a relatively large portion of this incident. So that was kind of interesting, and it turns out that that engineer was correct, and the reason that they thought it might be that issue is because one of the first incidents they had ever worked turned out to be a closed shop issue. So that was an example of that first heuristic where it was something that was very painful to them, and they always remembered that you always look to see if the shop is frozen first. Now, one of the other interesting examples that showed up in the research is when John went to interview the engineers, and he sat, I think it was infrastructure engineer number 1, sat the engineer down and asked them about this incident. They immediately recalled something about a varnish cache issue, which was not the cause of this incident at all. But it shows that principle of general things that we remember, but only for a short time, that L1 cache, if you will, of incidents. But it's not very specific. It's not, oh, you really have to look at frozen shops and it's this API call that can return funky things. It's, I think there's something wrong with the varnish caches. And in fact, again, when that engineer was interviewed about this particular incident, his mind went back to the generalization of varnish caches, which, by the way, is one of the things that that engineer looked at in this incident. So we found a bonus heuristic on testing the fix, which I thought was kind of funny. Now, I want to do another sort of simple survey here. When you do raise your hand if when you do a deployment, as a rule, you wait for your tests to pass first. Okay. Now, keep your hands up for a sec. Now, imagine you had an outage and you had time pressure, and people are asking you to just try something, get the site back up. Would you deploy the fix without, put your hands down if you do deploy the fix without running tests and you just deploy, if it was just a one-line config change and you thought you knew you could do it? So I see some of the hands going down. I see one person doing this, which is kind of funny. So that's what he found, actually. He did a survey where 1 would never wait for automated tests, and 5 is always wait for automated tests. And he found that during production incidents, a lot of engineers are actually in the 2 to 3 area, right? The heuristic we use on the elements of expertise. And what they found in their research apply what they call higher level rules. And it's really interesting. They talk about the reason that novice called why expert performance is special and can't be extrapolated a response to criticisms. So he's probably kind of tired of what Malcolm Gladwell did to his So how do you transform expertise into experience? So again, Hoffman and Klein looked at different ways that you can do this. Personal experiences, this is important. It's not just doing the thing. It's not just being an operations engineer for 10 years. It's being continually challenged, whether it's playing the piano or being an operations engineer. So growth, directed experience, receiving tutoring, the point of which is not to get the feedback, but actually to learn how to be a tutor to someone else at some point in the future. Manufactured experiences is training simulation, right? And then vicarious experiences. These are things that we tell stories. We create a narrative and stories that we tell others about because they were so good or bad, as the case may be. And as we've seen, right, we call that on-call. Personal experience is on-call. Directed experience is kind of interesting. If you do training, it's training. But I think the one that fits most is code review or pair programming, right? You learn how to be a good code reviewer or a good pair programmer by having somebody who is good at that did that with you when you were earlier in your journey. Manufacturer experience, chaos engineering game days. I was actually looking up, there's a great talk a couple years ago at Monitorama from the Stripe folks about how they do that. And then vicarious experience. I remember this one incident, and it was DNS because obviously. So the last bit, the second part about how you your ability to sort of monitor, your monitoring ability, if you will, in an operations context, is to do what's called explore discretionary spaces. So this comes from research that was done after actually the 3 Mile Island incident by a Swedish, I believe, although he might be Danish, researcher named Jens Rasmussen. And this is from his paper called Modeling Risk in a Dynamic Society. And it's called the Rasmussen triangle. And so the idea is that you've got these 3 boundaries. One boundary is the boundary of economic failure. So this is the idea that if we cross that boundary, it would be too expensive. We wouldn't do it. Nobody would pay for it because it would be too expensive. We have the boundary of unacceptable workload. So that's the idea that humans are lazy, and I don't mean that in an insulting way. I mean, we all try to get the most bang for the buck out of each molecule of sugar in our brain. So we want to take the least effort to do the most benefit of work or most unit of work. So over that boundary, we won't do it because it takes too much effort. And then this final boundary is acceptable performance, or sometimes called acceptable risk. And you know what happens when you cross that boundary, right? Bad things happen, right? So you have this idea that you have these 3 boundaries. And on the financial boundary or economic boundary, he calls them pressure gradients. And the idea is this is just standard cheaper, better, faster. The business wants things cheaper, better, faster. So they're going to push the system away from the expensive boundary, right? Then you've got people working in systems. They're going to try to do the most amount of work, least effort. So they're going to push less work, right? Now, if you notice what boundary are we happily going toward? The unhappy boundary, right? So sometimes this triangle is shown with a dotted line. And this is sort of our perception of where that boundary is. And these boundaries move in systems over time. So the actual place where that cliff that we might fall off is constantly moving. But this is where we think it is. And so they call this kind of blob the discretionary space. So it's the space that we allow workers in this system to sort of explore. And we can kind of actually think of this as the thing that would go across the accident boundary, if you will. So the goal here is to allow us to actually explore this discretionary space as much as possible. Get as wide a lay of that boundary that we can, so that we have a better sense of when we're going towards that boundary. And if we do things like game days or chaos days, then we also can get really good at, if we cross this boundary, we can actually know that we've crossed it and then wrestle the system back across that accident boundary before it's really a big problem. And by the way, if you look at big organizations that are good at this, this is the difference between an incident and an accident. An incident is you cross this boundary, but you solved it quick enough, and an accident is you cross this boundary and you couldn't solve it for some reason. Either the system was moving too quickly or the right skills weren't there or what have you. One of the things I wanted to point out from the Google SRE book, which I found really interesting, is, of course, monitoring is at the bottom of this, and we're all here, so we all know that. But I thought it was interesting that incident response and postmortem root cause analysis is right above that, right? And that sort of makes sense if you think about it, because that is where all of the operational part that makes complex operational systems work, that's where we learn how to deal with those systems and how to wrangle those systems. Now, one of the other interesting things that I would point out is this is Etsy's debriefing facilitation guide, and I can't tell you how many people do like root cause analysis, postmortems, retros, good, awesome, perfect. And I can't tell you how many people say, oh, well, the reason we do those is because we want to find the root cause and we want to find the remediation item. We want to do retrospectives like Etsy does them because they always find the root cause. I can't tell you how many times I've heard that. And it's really interesting because that's not actually why they do retros at all. The two questions that they have at the end of the debriefing guide is, did at least one person learn one thing that will affect how they work in the future? And did at least half of the attendees say they would attend another debriefing in the future? Right? So they're interested in, did someone learn something? And was the experience good enough for at least half of the attendees that we would keep doing it and that you would want to keep doing it? But it's not about filing JIRA tickets so you can actually find the remediation item, because those model linear systems, and we don't live in linear systems. So, question that we asked, how do you get better at knowing what to do when an incident is occurring? Well, turns out the answer is create space and experiences to facilitate the cultivation of ourselves and our teams to improve our heuristics so as to detect weak signals and ambiguity in the complex socio-technical systems we operate and in which we exist. Or another way to say that, practice makes better. It doesn't make perfect. Expertise takes time and space, so you need to make time and space if you want expertise. You need to make time and space for it. And finally, it may be hard to see this, but for people that know this photo, this is the picture that Voyager took as it exited our solar system. And I really liked it because I think we can all agree that the universe is pretty chaotic. And it's just us out here, right? Everyone that we've ever known and everything that has ever happened that we know of has happened on that little blue dot, right? So similarly in incidents, when we look at our teams and ourselves, it's just us out there, and it's a chaotic world. So as you're going on this journey to expertise, be good to each other. This is really what Blameless is about, because we're all in this together as we're on our journey to becoming experts. Thanks.
I told you it was going to be about science. Our next speaker is Pedro Andrade from CERN.
All right, great. Thank you very much. Hi, it's a pleasure to be here with you today. So, my name is Pedro. I'm a software engineer working at CERN. And as you can see by the title of my talk today, I'm basically going to talk about two things. First, CERN, what it is, and then I'm going to say a few words about how we are doing monitoring over there. Just one quick note before I actually start. As you will see, my slides are this kind of old style, classic slides, you know, bullet points, headers, footers, no funny pictures anywhere. But at least there's one good thing. The font size is more than 10, and I'm not using Comic Sans, so it's all good. Now, CERN. A few things about it. So it's an international organization. We are doing research on high energy physics there. It was founded 1954. This was right after the Second World War, and somehow in an effort to bring the European countries all back together. It started with 12 countries, and since then it has just been keep on growing, and nowadays there are 22 member states. Actually, there are a lot of collaboration with many other countries worldwide, including, for example, the United States, or, for example, there are other countries like India or Pakistan, Turkey, and Ukraine that have a special status. They are associated members, and we are working with them so that one day they will become full member states. For you to have an idea of more or less how big CERN is in terms of staff, we are more or less 2,300 people there, but actually we serve a much larger community of scientists, which is spread around the world, which is more than 12,000 different scientists. So if we move on, where actually is CERN? So, let me move on here. Here we go. Over there, you can see these are the Alps, the mountains. Then you have a lake. You have the city of Geneva nearby. And then you actually have CERN. CERN is here. Basically, CERN sits between France and Switzerland. So this white dashed line here, this is the border between the two countries. On the upper side is Switzerland, on the other one it's France. And then you can actually see here, this is the main site of CERN. It's the site of Meyrin. Actually, this is where most of the offices are. My office is there. The site itself is also half in one country, half in the other country. So actually, my office is in France, and the restaurant is in Switzerland. So I just have to cross the border all the time. And then we have another site, which is really here, and this is the site of Prevsa, where actually the real construction happens. I also profit from this picture to introduce, maybe it will help. This big yellow line there, it's our main project. It's the LHC, the Large Hadron Collider. This is basically a particle accelerator. It's a project that started many years ago, and recently, in 2012, it allowed us to confirm the discovery of the Higgs boson. An accelerator, thank you. As you can see, the accelerator is quite big. So it's 27 kilometers diameter. And then along the accelerator, both on the Swiss side and the French side, there are 4 main points, which we call the detectors, the experiments, where the collisions of the particles actually happen so that physics can actually be done. If you're curious more or less to understand how does the actual tunnel looks like, here you go. So you can imagine now we have a tunnel, 27 kilometers diameter, 100 meters underground. And why underground, you may ask? Well, for just simple reasons. First of all, if we had to build a tunnel at the surface, it will just be too expensive to buy all the land. And second thing, just because it's just easier to build it underground. So there's a tunnel, 3 meters wide, and then inside you have the superconducting magnets, which are these blue pipes that you see there. So actually, we're talking about 1,600 of those superconducting magnets, which are installed in the tunnel. Inside the magnets, you can see those 2 pipes there. This is actually where the particles accelerate, where the beams go. There are 2 of them. One goes clockwise, the other one goes anti-clockwise. And of course, at this phase in the accelerator, they are separate because they don't work now. Actually, the collision will happen in this machine here. So this is an example of our largest detector, the Atlas one. This is something like 25 meters wide, 50 meters long. Sorry about all these meters, kilometers. And for you to have an idea of the scale, there are 2 people that are actually working there, so you can see how big this whole thing is. And inside, in the middle, you can see where the particles are, and then the collision. We cross the beam there, the collision happens, other particles are generated, and then basically there are a number of different detectors all the way that will detect all the collisions. You can imagine that we are talking about a lot of data. And if I take again the example of the Atlas detector, here we have basically something like 40 million events being generated per second. This is really way too much. Something like, if we had to talk about data volume, more or less 1 petabyte of data. Of course, this is too much. So using hardware triggers, we start to bring this number of events down, so that we have something that we can actually work on, and we reduce more or less the noise. We go down to more or less 100K events per second, which is still a lot. And then using some sort of online farms that are sitting right next to the detector and using software triggers, then this number goes down to 1,000 events per second, which actually we then want to store and record for study afterwards. And here we're talking about 4 gigabytes of data per second. Okay, keep in mind that this is one experiment, and I mentioned that we have 4 experiments like this. Well, not all are the same size, but. So if I move forward, of course, this data has to be stored somewhere. For this, we have our own in-house data centers. We don't put actually much of this in cloud. And we have our main site. This main site is built in the Geneva site. It was built in the 70s. You can see some pictures there. However, recently, 4 or 5 years ago, we started seeing that we were reaching some capacity, power capacity problems. So we decided to build or to use an extension site. This site has been located in Budapest, in Hungary, and it is connected to the CERN site with 3 100 gigabit links. Also important to mention is the fact that in both sites we use standard commodity software. For you to have an idea of the numbers, if I put together the Meyrin site and the Wigner site, we have approximately 14K servers providing something like 200,000 cores. Of course, all of them, they have a local disk, but in addition to the local disk, we also have tape storage to archive our data. And in our tapes nowadays, we have more or less 190 petabytes of data stored. Still, even if we have data centers, this is not yet enough. We actually want to process all this data. This data has to be computed. So for this, CERN started the worldwide the LHC computing grid project, WLCG in short. So WLCG provides a global computing resources and storage, distribution, and analysis for the LHC data. It's basically built on a tier model where you have the CERN tier 0 at the center that, of course, is connected to the detectors and it has all the live data. And then this data is distributed in different LHC sites that form some sort of tiers. So you have the tier 1, tier 2, and tier 3. Altogether, the WLCG is a global collaboration that has more than 120 sites that are spread around 42 countries in the world. So as I was saying, you have the tier 0 at CERN, which place where all the data actually comes from. Here we do some sort of initial reconstruction of this data. And then we also archive the data, and then we start sending this data to all the different tiers. The tier 1s, which are basically 13 main other sites that exist. Actually, some of them are here in the US. They do also some sort of this initial reconstruction phase. They do reprocessing, and then this data can actually also be served to the tier 2s, where they actually are used for simulation or for end-user analysis. So by now you have more or less an idea of CERN, the data center, the WLCG project, so I can go on to the monitoring part. One thing that I have to say here is that we are actually not, my team, we are not actually working with the physics data. We are here only to provide a common infrastructure to monitor the WLCG, to monitor the CERN data centers. So what we actually have to provide is solutions to measure, to collect, to transport, to visualize, to process, and to alarm all this data that comes from the infrastructure that is the CERN data center and the WLCG coordination. So if we talk about now in terms of data size, I can push me for another one. So if you talk now in terms of data size and which type of data do we have, so we have a big variety of data, mainly a lot of metrics and logs. And if I have to categorize this data, basically there are 4 types of data. We have the data center metrics, basically hardware and OS. We have data coming from the IT services that run in the data center. And then we have data coming from WLCG, basically data from sites and services monitoring, and data from the WLCG main operations like job monitoring or data management. In total, this is more or less 500 gigabytes of data, of monitoring data that we have to process per day. It's a quite spiky workload. And of course, when things go bad, then we have even much more data and even much more users that we have to handle. Sorry, I'm back. In terms of the overall architecture, and following a little bit of the lines of what Megan was saying yesterday, we try to have, as much as possible, open source tools. We try to have a common solution that we can use both for the CERN data centers and for WLCG. And we try to have and to put all our focus on having an infrastructure that we can scale. If we have more monitoring data, we are fine and we can scale it. So that we can instead give the power to the users to create their own dashboards, to create their own views. And this way we can focus on actually scaling the infrastructure. We follow a quite standard approach where we have basically a phase of integration of data sources. Then we have to transport all this data in a common way. We may have the option of doing some processing. We then store the data in different backends. And then we have tools to access the data. Now, let me give a few more details about all these different areas that we are working on. From the sources point of view, there are basically two types. Either we have internal data sources. And here I'm talking about the metrics that come from the data center operating system or hardware. For this, we decided to go for CollectD. We plan to have CollectD installed in more or less 30,000 nodes with a sampling frequency of more or 1 minute. And then we also have the other type of data sources, which are the external ones, basically coming from the services that run in the data center from WLCG. Here we have to support a mix between push and pull models. And we have also to support different technologies and different protocols. This is some numbers I took at the end of last week. You can see that we have quite an heterogeneous set of data sources. So we have around 45 different producers nowadays. So it's really different types of data. Some of them are just a few megabytes, while in some cases, in others, they are quite large. And we have, for example, data from CollectD, which is more than 10 terabytes, or data from the FTS service. FTS is the main service of WLCG to transport the data, so file transfer service. Or, for example, we also collect syslog data, and we have more than 10 terabytes of syslog data stored in HDFS. So now we have all this data together, and we want to transport it. Here, we decided to go for two main technologies, Flume and Kafka. From the Flume point of view, we have decided to go and have some sort of dedicated Flume agents to actually receive the data. And this is actually where we apply these different, either we have push or pull models. We have Flume agents which are dedicated to talk with different protocols or different technologies. For example, we can get the data from a messaging broker because the guys from Atlas in the US send the data this way. Or we have another Flume agent that gets data from Oracle because some other guys in Asia have this data stored in an Oracle database there. And then we have a number of other Flume agents to get the data from either logs or metrics. All this data is aggregated in another Flume agent that then puts the data in Kafka. Data is buffered in Kafka, and then it can go along and be stored in the different storages. So, as I was saying, we have approximately 10 different types of Flume agents. And if you know a little bit of the Flume terminology, we have something like GMS as a source, Avro as a sink, in other cases, Kafka as a source, Elasticsearch as a sink. In all cases, we always use file-based channels, just because we want to have some persistency of the data there, but we don't want to have a big capacity. The big capacity of buffering, this is done at the Kafka level. We use a lot the Flume interceptors and morphlines. This is mostly for validation, for transformation, where we do some checks on mandatory fields or to apply some common schemas. As I was saying, from the transport point of view, Kafka is the rock-solid core of the transport layer. Today, we have the data there being buffered for 12 hours, even if we want to grow and have a target of 72 hours so that we can have a relaxed weekend. Each data source is stored in a separate topic in Kafka. Each topic is divided in 20 different partitions, and we have several replicas per partition. This is just another of our dashboards. This is actually the dashboard that we have for the internal monitoring of the monitoring. And you can see some plots about how much data, the rate of data that we have in Kafka, or for example, how Flume capacity is. Now we go for the processing. In some cases, we just let the raw data go. We just store the raw data as it is. In some other cases, we want to do something more with it. For this, we use Spark. And we basically have two categories of jobs. All of them, they are all Scala-based. We have jobs which are for stream processing, and basically here we do things like enrichment jobs where we add topology metadata. For example, if I use the example of the FTS service I was talking about before, this is a service that has events that just says file A or event A was copied from site B to site C. It has all the metrics about the transfer itself, but we don't have more information about what is site B or what is site C, in which country it is. So we use this type of jobs to enrich the event with this other information. We have jobs which are just simply for aggregation. Mostly, sometimes we want to do aggregation over time if we think that the raw data actually doesn't really matter that much. Or we have other jobs for correlations when we want to check things between data sets. The other category of jobs that we have are the batch processing jobs. Of course, here data doesn't come from Kafka, it comes mostly from HDFS. And these jobs are used for doing compaction of the data, reprocessing of the data, and of course, the usual reports for the management to have a look. All the jobs, they are built and they are packaged as Docker images. So basically through an automatic process at every push using GitLab CI. The jobs are then orchestrated as processes in Mesos. We use Marathon for long-lived processes, like the streaming ones, and we use Kronos for just the standard recurrent jobs. And then the jobs get executed in Mesos, or in some cases they also execute in a larger yarn cluster that we also have access to. And this is more or less for the processing. Now, if we talk about the storage, as I said, the data is all there in Kafka, and then using 3 dedicated Flume agents, we write down this data to the different backends. And here we use 3 main technologies: Hadoop, HDFS, Elasticsearch, and InfluxDB. HDFS is mostly used for archiving the metric data for long term and for data recovery in case this is needed. Basically, we keep there all the monitoring data forever. Well, limited to the resources, but for the time being, we are still good. We use Elasticsearch for mostly searches and data discovery. There, the data is kept for 1 month because clearly this seems to be enough for most of the data discovery activities that we have to do. And then we put data also in InfluxDB for basically plots, dashboards, and actually the visualization. Data is kept for 7 days, but in addition to that, we also have 5-minute bins that are kept for 1 month, and then 1-hour bins which are kept for a bit longer, for 5 years, so that our users can have their historical views in case they need. In terms of how do we actually write the data, so all the data is written to HDFS by default, and we use some sort of a path like that where we put the data. And all the data is then aggregated more or less once per day in 1 gigabyte files, so that we make the managers of the Hadoop cluster happy. Then, according to basically the use case, according to the user, some selected data sets, they are stored in Elasticsearch or in InfluxDB. In Elasticsearch, we have 2 generic instances, one where we put metrics, the other one is where we put logs. And we basically put each data producer in a separate index. From the InfluxDB point of view, we have basically 1 instance per data producer. From the access point of view, we use 3 main tools: Zeppelin, Kibana, and Grafana. Zeppelin is used mostly for getting data from HDFS, for programmatic access to HDFS and the generation of reports. Kibana just to connect to Elasticsearch. And then Grafana is mostly used for the plots and for the dashboards on the data in InfluxDB, but in some cases we also have some data from Elasticsearch. I'm not going to go in more details about these 3 different technologies, but I just want to show you some examples of some of the dashboards that we have there. This one for example, here is used by Atlas for the job monitoring activities of Atlas, and it shows the 7 days view on the jobs that were executed by the Atlas physicists in order to run their models. And there are things like the type of job, or for example, how many cores its job is using, or what is the site where the job is running. From another example of dashboard that we have, this one here shows the collect the data that we collect from all the OS metrics that we collect from the data center. Standard collect the plugins like CPU, network, memory, disk, and so on. Or another dashboard, this one was actually done by my colleagues from the cloud team that run OpenStack. And here they are basically monitoring how many the hypervisors, how many VMs are there, how many VMs have been created, have been destroyed, and this type of things. One more thing I would like to say now is about alarms. I only have here one single slide about this. Actually, this is something where we are still quite, we didn't actually advance much. We are still using our own old tool that exists, that was developed in-house. It's an old tool set, maybe with more than 5 years old. This was just doing, or this is just doing local alarms based on local metric thresholds. Still, we have some plans to evolve this, and we want to move towards maybe a multi-scope strategy. We still find the local alarms useful, mostly for having local actuators. Here we'll try to also to profit to what Collective can give us. So if you have also any suggestion, I'll be happy to hear. But also we want to have the standard base alarms that we can define from Grafana, or in some more advanced cases, we want also to support alarms by running Spark jobs, which can be, in this case, a bit more service or user specific. Final 3 slides. The one thing I would like just to briefly also share with you is a bit more or less of the size of the monitoring infrastructure that we have. So basically, we run all of our monitoring services on OpenStack VMs. We have a project of 300 nodes there, and today we are running more or less these different types, so this different number of components. In some cases, we have Ceph volumes attached. And for the case of InfluxDB and HDFS, we actually don't run this on VMs, when we run this on physical nodes. Altogether, it's important to say that all the configuration here is done via Puppet. Final thing, a few lessons learned. So we are already running this new infrastructure for 2 or 3 years now, and we have learned a few things. First one that I find it quite nice was the fact that we decided to go for this approach where we have protocol-based Flume agents. The fact that we have one Flume agent which is dedicated just to get data from a messaging broker or from a database, this revealed to be extremely quite handy. It's very easy to add new data sources this way. And since, as you saw, we have so many different heterogeneous data sources, it's quite easy our daily life. Every time we have to import some new data set, we can easily do it. Kafka is definitely the core of the business. Before we actually start deploying Kafka, we spend some good amount of time to carefully plan the deployment of it. How many nodes do we have? How do we partition these? How we do for the topics? It's quite important to do this from the beginning so that we can scale Kafka as the project scales. And once Kafka was running, it's also quite important to actually have a good control about the consumer groups of Kafka and the offsets so that we actually no data is lost. Another thing that we discovered was, of course, as usual, that securing infrastructure takes time. We learned it once again in the hard way. We started with very few secure endpoints enabled, and then we decided to actually put everything secure. And of course, this was quite a long process. You can imagine first enabling secure endpoints in Kafka, changing all the Flume connections, changing all the Spark jobs. It was long, but we did it. Final things, from the Spark point of view, Scala was definitely the right choice. The data frames to decouple from the JSON marshalling, this was something seen as a good advantage. The fact that we decided to have checkpoints for our jobs in HDFS was also a good thing. But also important was the fact that we tried to keep the batch, the jobs, the code of the jobs as similar as possible between batch mode and streaming mode. This also is a nice thing. This way we can switch quite easily. We also had some very good experience with Marathon. It's a quite nice tool, and we were quite happy with it. On the other hand, with Kronos, things didn't work so well. And last thing was the fact that we have both backends, InfluxDB and Elasticsearch. From the user point of view, this could have been seen as a bit of a confusion. In the end, we try to take the best out of the different tools, and we try to make them as complementary as possible. So in the end, it worked out quite well. The infrastructure is there, and all our users are happy, and they can have their dashboards run their jobs. So this is more or less everything I had to say. If you're curious about CERN, about how we do monitoring there, just feel free to stop me in a coffee or talk to me in Slack. And thank you very much.
All All right. Thank you, Pedro. So we have 2 sponsors that we'd like to thank, but before we do that, I want to thank you all for being patient and kind today. It's nice outside. You could have done something else, but you decided to hang out in this aircraft hangar thing. And I also want to thank this space, Pure Space, who were able to accommodate us on zero notice and find a way to fit us in here. So huge thank you to them. Huge thank you to our coffee friends, Nosa Familia, without whom I would be asleep right now. I'm actually asleep right now. They were able to redirect the stream of coffee from the venue that doesn't have power to the venue that does, and that's really important. And then speaking of the venue that doesn't have power, a huge, huge, huge thank you to the PCS folks who came over here to a place that's not their own and have just stuck with us all day doing whatever it takes to make this event work. So thank you. And I'm just going to keep thanking people until we get the aspect ratio sorted out. I do mean this, but we're also working on the aspect ratio. The sponsors sign up for a certain thing when they choose to sponsor Monitorama. They're here for y'all because you're a smart and engaged community, but they're also here for like the tables and the opportunity to give you things and to talk to you. So that's what they're going to do in a minute, but they're also rolling with us as we shift plans and fill into a space here. So thank you to all the sponsors today and potentially tomorrow, which I'll speak about in a second, for being super accommodating. So I'm running out of gratitude filibusters. So this is me dancing. Dancing is, yeah. So let's talk about tomorrow. So as you know, there was a problem today, and our comrades in the Pacific Power are doing their best to restore service to the area, including to PCS. That's our plan. We hope that and expect that that's back online. But we will do whatever it takes to make Monitorama happen tomorrow, whether or not that's true. And so Jason is looking at some other options right now, just in case. So we're watching the same Twitter feeds that y'all are, and we expect to hear by 9, which is the current time we expect, that Pacific has succeeded and their teams have won the day. If they don't, though, we will reach out to you with updated plans for tomorrow. So if you found today exciting, you may enjoy tomorrow. Great question. The question was, what is the best way to track what's going on tomorrow, or perhaps in general? We'll continue to provide updates here, and then the Twitter feed is where we make all the major announcements, and then Slack is the best kind of minute-by-minute tactical place. And if you have questions, it's a good spot to ask. This is my laptop. Any other questions? Does anybody want to know what's going to happen after we do these sponsor talks? Okay, good question. Thank you for asking. So we have 2 sponsor talks, then we're going to close the day of formal talks with Bridget, who's been super patient and kind, as well as everybody else. After Bridget, we're going to switch, have a quick break, and move into the lightning talks. Wow, you're excited. So the lightning talk, yeah, right, we're all excited. Let's clap for that. Thanks. So the lightning talks, we have another set of courageous and awesome speakers who are going to come up here and do 5 minutes apiece. They are also contending with interesting technology problems of the AV variety, and so please be generous and warm when they do take the stage. We'll do our best to keep things on time and move one by one through those. There's a short sponsor section in between, and then we'll be done for the day. Does anybody want to know what's going to happen after that? Oh, awesome. No, I got to tell them the stuff. Slow down. After that, We're going to have a couple events throughout the city this evening. Caleb has already updated the location for the Sensu party. I believe there's a bus that's going to come here and take you there if you'd like to go there. There are other parties as well, but this is an opportunity for you to spend a little bit more time with the sponsors and with each other. So with all of that, I'd like to bring up the first of our two sponsors, New Relic.
Does this move? No? Huh? Oh, there it is. Thank you. Pull harder. Hi, like it says, I'm Pancakes from New Relic. You're all very kind and patient, and really impressed that this is happening right now based on how quickly it got turned around. I'm just here to talk to you a bit about New Relic. So, many of you probably know New Relic as an APM vendor, application performance monitoring. Many of you are probably familiar with this screen, which is kind of the main screen in APM, in our APM product that kind of gives you a live look at where your application is spending its time. However, what some of you may not know is that New Relic is 9 years old. That shocks me every time I hear it, because I remember when it wasn't that old. And in those 9 years, we've added a good half dozen or so other products. I'm here to tell you a little bit about the latest addition to the family, the infrastructure product. It's a very aptly named product. It is for monitoring your infrastructure. So when you first get to the infrastructure product, what you see is compute data about your about your collected from your nodes by our collection agent at a 5-second interval. There is a bunch of other stuff that you can't really see because of the resolution. There's a bunch of other kinds of data you can look at, but we collect, there's network, storage, etc. So by default, when you get in here, you just see data for all your hosts, but an average for your whole infrastructure, which in this case is our entire staging infrastructure, is not super interesting. So how do we drill down? Again, this was supposed to be a demo, but I converted it into sketch images with arrows where I would be clicking as quickly as I could. If you want to drill down and not look at all the hosts at the same time, we can click that little filter thing, button, it's not a thing. And what I want to point out is just the sheer number of things you can filter by. Like this is a scrollable list of all the different things. There is an autocomplete, so you don't actually have to scroll. And the other thing to point out is you can't really see, but all these things have an EC2 prefix. Those are all pieces of metadata pulled in from EC2, including your tags. And what that means is if you already use EC2 tags or some other taxonomy to classify your nodes, we will pull that in, whether automatically or through a config file, and let you navigate your data the way you already think about it. So if I want to, for example, filter to my Mesos agent, that's what that says in that blurry little box. That now says 13 hosts, so now we've filtered down to a smaller set of hosts, so it's probably a little more interesting. And now we can also look at host level data by toggling this thing called group by. Cool, I just showed you a bunch of places to click in the UI, how interesting. But the reason that I'm doing that is because that little thing is very powerful, right? Because you can change what you're grouping up by. So right now that says host name. You can change that to say EC2 tag role, which is the same thing we were just filtered by. And now instead of looking at host level data, we're looking at a cluster at a time. The most powerful and my favorite thing in this product is the process monitoring. This is top for your whole infrastructure. This is all the processes on whatever host you're looking at. So in this case, it's our Mesos host. We've also filtered down to only containers, so we're just looking at the containers running in our Mesos cluster. Again, group by is still here, so you can group by a container label. In our case, we have a container label that's called service name, which our agent pulls in from Docker automatically. So if you install the agent, you get it. I don't know why that's there. I don't know who put that there. By just toggling a couple things in the UI, you can answer different questions. You can answer host level questions, cluster level questions, container level questions. It's super powerful. The other thing that's super powerful is that it's all backed by our Insights Analytics database. So every chart has that little button that says View and Insights. That drops you into Insights with the exact query that we used to build that chart. Now you can't see anything, but it's a SQL-like language where you can select average of or whatever. There's a bunch of different functions you can do, and we kind of let you give you a preview by letting you see the queries behind our charts. I don't want to take up too much more of your time, but we are here. There's a lot of us. There's a lot of engineers and PMs from all over New Relic that are in the crowd. We would have been at a vendor table, but instead we're just kind of here mingling. So if you have any questions or you want to know about what else we're up to, come talk to us. And that's all I've got. Thank you.
Thank you. All right. Thank you, New Relic. And our second sponsor is Are you in suspense? You want to know? Yes, excellent, great. Ready? Bugsnag.
Thank you. Hi all. Thank you very much. Happy to be here. It's been some interesting talks I've been listening to and some cool conversations I've had. My name's George. I'm a production engineer at Bugsnag, and Bugsnag is an error monitoring platform for your production applications. And I want to talk to you about how we monitor our own infrastructure. The punchline is we use ourselves, but I just want to kind of give you a breakdown of how we did that. So last year, we came across the need to build out a better metrics monitoring solution because the current one we had in place wasn't serving our needs. And so the way we, I want to talk to you about like how Bugsnag exactly works. And the way we do that is by providing notifier SDKs for all major languages that let you basically send exceptions to our system. And we gather these exceptions, we process them, we enrich them. For example, for Android and iOS, we symbolicate them and add more information to them. For JavaScript, if the file is minified, we enrich the file, the crash by applying source maps and unrolling it. We also classify and group the exceptions, and we can do further processing, such as send them off to integration APIs that we're plugged into, such as PagerDuty, HipChat, Slack, Jira. And so this is what we do. And the need arose out of our infrastructure growing and our current monitoring tools that we had in place not being able to serve our requirements. And so the three major requirements that we had was we needed something that we could get up and running quickly. We needed something that had a low learning curve. And we also needed integrations for APIs that we could use to automate our debugging and monitoring workflow. And we also had a requirement that this wouldn't necessarily be monitoring. These could also be automation tasks, such as performing backups or cleanup jobs. But we would have liked, ideally, to have all these things in one place where we could quickly kind of write checks and tasks like that. And we looked at several solutions out there, and we did end up implementing a better monitoring solution. But we still had a gap left after that, which wasn't fulfilled by the tools that we implemented. And those were the requirements that we had for very Bugsnag infrastructure specific tasks that were not easily expressible in the context of the tools that we ended up using. And so we thought to ourselves, wait a second, we already have a product that has all these integrations, has error monitoring, and why not write another app that behaves, that is an infrastructure monitoring app and treats checks, failed checks as exceptions. So for example, if we were to execute a service check and it were to fail, we could present that in the way of an exception and send it to our own system. And that's exactly what we ended up doing. And so I want to show you a small screenshot because I can't have a demo right now, but this is what our inbox view looks like. And the app is called Shepherd. I wrote the app, and it just basically performs periodic tests in our infrastructure. And whenever either of these tasks or checks fails, we throw an exception, or if any of the underlying code we use fails, we also throw an exception, and we detect it and display it here. And so this is basically what I'd look at every day, and you can see there are multiple layers here. So yeah, this is the Shepherd, I guess, filled in our need quickly, and we, like I said, it fulfilled all of our requirements pretty well because we already had all the integrations to the external APIs in place, and we were able to, for example, in this case, plug in into PagerDuty, and we were able to, notify PagerDuty when an error severity or error came in, and we were able to, page ourselves and also plug into Slack, for example, so that we would know when they happen and we could start the discussion about it, whether it's an incident or not. But yeah, this is our product, and I hope you like what you see. And this is how I ended up implementing monitoring for Bugsnag by using our own product.
All right, our final talk of the day before we have other talks that are shorter and kind of one after the other is Bridget. Come on up, Bridget.
Thank you so much, Will. Okay, presumably I have slides coming from somewhere. Hey, look at that. See if we can get them to play. Okay, I like this slide. This is, oh my gosh, I hadn't looked out and there are a whole bunch of people still here. This is really exciting. Thank you for still being here. And I'm really also, I feel like, let's see, this is the one that's going to advance my slides. How many people here, I'm just curious, and I know we've all been doing the show of hands thing, but how many people here have a visceral dread of a ringing phone? Yeah, as Cheslock would say, let's talk about it. Because I'm not on call right now. More about that in a minute. Oh, I'm not supposed to walk over there. Not on call right now, but for those of you who don't know me, this is the traditional second slide. Bridget Kremhout. I spent way too long in ops. I live in Minneapolis, Minnesota. We run our DevOps days in the 1 month every year that it does not snow, which is July. But we are running it the week before the DevOps Days Portland. And I do run the shadowy cabal that runs DevOps Days. And the DevOps Days Portland people here, talk to Bill, talk to Alice. Their tickets are available now. Their DevOps Days is August 1st and 2nd, so you probably want to go to that. And I work at Pivotal. I do tech advocacy for Cloud Foundry. And I also podcast with Arrested DevOps. So if you're thinking, oh, that's why that voice sounds familiar, I am the disembodied voice asking people questions about ops, inside your podcast machine, probably Overcast. It seems like more and more of our listeners are using Overcast. Okay, but I did spend an ungodly amount of time on call for production. I went and actually added it up, and I was on call for production from 1999 until August 2015, which I think broke me in a deep way because now I report up through marketing. And I think, by the way, when Andrew Clay Schaefer says, come with me if you want to live, it'll be fun, you won't be on call anymore. What he doesn't tell you about is the 3 a.m. flights out of Bangalore. You'll still not get sleep, it's just for different reasons. But the part where you have all the feels about on-call even if you're not on it anymore is, I suppose, means it took me this long. It took me almost 2 years to actually be able to do a talk about on-call. I had set aside enough of the on-call PTSD. It's never going to be gone. I will never turn the alerts on my phone back on. I'm people message me on Twitter. I'm like, oh, I'm going to see that when I look eventually, but I don't have alerts on my phone. But I do think that change is the only constant. And I went and walked, I have spoken at Monitorama before in 2014. I went and watched the video of that because I didn't want to repeat myself too much. Oh, it was a more innocent time. I mean, I still had AV disasters, but other than that, it was a more innocent time because the main things we seem to all be worried about were the global write lock in MongoDB and, airport carpet. We weren't as concerned about, the dissolution of the global whatever, but we had, I think looking at that talk, I was talking about from zero to visibility or observability or something like that, probably visibility. I feel like I'm now saying charity's observability word constantly, but I was thinking like, how do we get from the, hey, we're talking about these specific tools that we want to use for the stuff we care about, to maybe taking that conversation to a slightly different place. Like, okay, we have, and here in the last day, we've experienced like, hey, there are going to be disasters. Like, this shouldn't be a surprise to us anymore in any way. And yet, I mean, I work at a vendor now, I go in and talk to all sorts of customers, and everybody wants to talk about the ideal thing that they think is going to happen. And I'm like, reality check. Look at this tweet of Cheslok's. That was a delightful picture of the Portland skyline yesterday. It's like, this is the realities that we're actually all living under. So planning for that is where I think most of the people in this room are. This was Laura Bell gave a really good talk at the Agile conference in Boston earlier this year. And it reminded me of how, like, I kind of have this, if you pay attention to Simon Wardley's Pioneers, Settlers, Town Planners thing, where pioneers are, well, you know, pioneering, but the idea of settlers is like, okay, we've got this proof of concept, and now we're going to try to scale it up. Now we're going to try to actually operate this with maybe some actual customers on it. And I think the world spends a lot of time valuing and celebrating the efforts of people who, you know, instantiate something new and not who stabilize something that is in theory great and they make it great in practice. And so I want to make sure we celebrate that. And I know that this room is obviously full of people who are thinking about that. I know that Jesse Frizzell's Maintainerati conference also kind of focuses on like, hey, maintaining things also matters. So a little bit of a digression into, you know, previously on ops life. My last ops gig was for a streaming video site. And you're thinking like, wait, didn't you work at some sort of ad tech firm? And yes, I did. They got acquired, and this is the thing that happens apparently. They got acquired, and I went to go work for a firm that a friend of mine was at, remoting to this little company that was very much like Netflix, if Netflix were much smaller and mostly Korean soap opera, and ran Docker in production starting in October 2013, when I'm pretty sure the main thing on Docker's website was like, under no circumstances should you run this in production. And we were like, YOLO. And they eventually got acquired by Warner Brothers, so I guess, you know, sometimes YOLO works out. Not saying you should just YOLO things into production, but because somebody's on call for that. But like what I learned there is that it's not just the, you know, we have this stuff that we're trying to monitor, we're trying to keep it up, we're trying to scale it out, and that's not the only stuff that matters, because the communication across the team, and you might be thinking like, oh, it was a 5-person ops team and a 100-person company. Like, how much communication trouble could there be? I was like, well, were there more than 2 humans there? Yes. It's like, yes. If there were 2 humans there, there were probably going to be communication issues, right? And like this idea of bringing everything to microservices, and that is in fact what we were doing. We were doing that really fun thing where you, if you're a Python Django shop and you know it's 2014, you start decomposing everything and rewriting them in Golang microservices, because that was the style at the time, I guess. And what we started doing there is trying to figure out how we could make sure we were getting the right observability, like make sure we were going to be alerted correctly, make sure that we weren't going to just burn people out on being paged constantly on all the things, which is obviously a really typical pattern that I think we all fall into. And this is one of those places where we definitely had like the divide between dev and ops in terms of who was on call, and it didn't necessarily map to who understood the systems the best. I'm going to call Ryan out because he's out there in the audience somewhere. I see a wave, a little hand from way in the back. I think he's probably sitting on the floor by the back wall. There you go. And when we've got people where like I might be the ops person on call, I get paged, I'm trying to figure out, what the hell is going on, and this developer understands what's going on better than I do. Like, that's great, for your cross-team collaboration, but that's not necessarily something that your architecture is going to give you, right? Like, you can get that from good communication amongst, between team members, between teams. You're not necessarily going to get that from, say, documentation. So it's like, oh, great, it's 3 a.m. and I'm now going to read a document. Yeah, like, really? No. Okay, so basically, I do want to believe that decomposing everything, I mean, we're in Portland, right? So like decomposing everything into, like super trendy microservices and going with, the sleek modern architecture of everything, I want to believe that that will make things better in terms of, ops life and when people and how people get paged and that sort of thing. But the reality is that it's never going to be that simple, and we've had a lot of talks at this conference about a lot of really great tools, but in many cases, the tools are not going to, cause us or encourage us even really to have the kind of culture that lets us be better. And I know I found Alice's talk really moving because I had a great deal of, on-call stress in my life, obviously, and we'll talk a little bit more about some of the kinds of patterns of communication across an organization that I've seen work well or not well. But just that individual impact on people on your team, like I would challenge everyone to think about what the on-calls are like inside your team. And if you have to say to yourself, like, yeah, I can't recommend that people do this. I can't recommend that people join our team. Like, I have a friend who would love to join this team, and if they're gonna join and the on-call is going to make their lives complete shit, like, would you actually recommend that to them? And I think that's something we all have to think about inside our orgs. And this is, I assume this tweet probably has even more tweets. Sorry about your battery, or I assume you turned all your notifications off on Twitter by now, Pete. But this tweet I think really resonated with people. And if you can't read it, it says that what Pete said in his Vasa talk yesterday: 2 types of ops. People who have fucked up production, and people who will fuck up production. And I had somebody wanting to argue with me on Twitter saying like, oh no, that's devs who do that. And I'm like thinking to myself, it's all of us. I mean, you might have different gates inside your organization about who can press that go button. Maybe you have a really automated deploy pipeline and like someone in charge of product is the one who actually makes the go, no-go call. But trying to pick a person and saying they're the ones who made it all break is like, really? You're gonna have to go back and read more stuff from John Allspaw, who J. Paul Reed was referring to in the recent talk, because it's like, blaming people is not going to actually solve the problem faster. Because I don't know about you, but like when I've felt responsible for an outage and also been worried that maybe I wouldn't have a job because of the outage, that was not a strongly motivating factor for me to be forthcoming about it. And when I went into work that morning and was like, yeah, I fucked up, and my boss is like, it's okay. I'm like, really? I'm like, do I still work here? He's like, yeah, you definitely still work here. Let's fix this. Okay, and yeah, of course, we always have to talk about DNS, right? And it's like, I feel like we can focus on those specific things that maybe are always broken, or those things that may or may not be, what we want to point to, what we want to blame, what we want to say. This is the thing I always check first, because I touched the stove once and it was hot, and now I always check that. And it's like, I mean, yeah, like we know that there are some things in our infrastructure. Everywhere that you work, if you have any kind of operational responsibilities or architectural responsibilities, or if you wrote some code once that you kind of regretted, but the test passed, and you shipped it because, it was Friday and you wanted to go home, like, all of us have something like that, where it's like, we know that there's the stuff we probably should go look at that's probably wrong in our infrastructure. It's like, yeah, that's another, I'm giving you all sorts of homework. That's another thing to do when you get back. Just go look at that thing that has always bugged you. I mean, like, we had, I think I showed you when I was here in 2014, I think I showed you the outage that we had over shopping holiday because of, we were on the front page of a major American toy retailer, and there was, MongoDB and sadness. And I did know that there was something a little bit sketchy about it, and I kind of brought it up, and I kind of wanted to change it, but there was a change freeze because shopping holiday, and so we didn't. And I mean, we did change it on Cyber Monday when it was down, and it's like, you have stuff like that. Just fix it now before it makes you really sad. Okay, and also, like, I have, there are some cat pictures. Sorry, not sorry, but I think that there's a lot of places where people get, hyped up or excited about, we might be able to just get rid of all this. I mean, we can have some serverless and some no ops, and we don't even need to have or be or do or whatever ops anymore. And being on call, it's terrible. And why don't we just have cross-functional teams and nobody ever has to be sad? And it's like, this all sounds great, except for the fact that there are still servers somewhere. Like, maybe you can't SSH into them, but they still exist. And so you still have to care about how you're architecting your applications. And it's like, it's kind of a reality check thing. Like, if you're, and yes, Attack Kitten did grow up a little bit. Like, he's still really small, but apparently they get bigger if you feed them. Who knew? And if you think about, like, which stuff is paging you, and which decisions, like, you probably, as an organization, want to revisit, like, those are the places it gets really hard to have that discussion, because it may not be about getting the new feature out. I mean, hey, features, they're great. Let's just keep shipping features. It doesn't matter if they're broken. Somebody can just be miserable. Yeah, this is not a sustainable plan. You're going to burn people out. You're going to have very angry Attack Kittens if you do that. Okay, so something else, like, I would point out is that we do need that empathy that we sometimes talk about, in that whole, DevOps-y woo thing. Like, the understanding the problems of someone else, even if they are not exactly your problems. Just saying you should learn JavaScript and you should learn HDFS and feel each other's pain, like, that may or may not actually solve the problems inside your organization. It might, but it very well might not. Just depending on people's perspectives, their skills, like what they're coming into this with. And by the way, in the CERN presentation, I was like, HDFS, I remember that. I remember a lot of problems with that. You should probably never run, you shouldn't run HBase on EMR, by the way. Like, AWS calls them job flows for a reason. They expect them to be ephemeral. Pro tip. Okay, and, this is working. Okay, so like I mentioned, I work for Andrew Clay Schaefer at Pivotal, and he likes to say that, like, most of tech is tribalism and fashion, and I think he's right. And I also think that we end up focusing a lot on that stuff, that either the things that seems like we can affect, or the things that seem easy to change. Like, we can definitely add a new technology to our stack, right? Like, I don't know about you, but I assume we can probably read about something on the front page of Hacker News and YOLO it out into production, and it will definitely be fine. It's probably fine. Cheslak, right? No? But I think that it's very easy to get caught up in hype-driven development because this stuff is exciting. And I don't know about you, but I definitely want to develop a novel time series database and, like, get that out to production because it'll be great. Except, like, what problem are you trying to solve, and what are you making better or way, way worse inside your organization? I think is worth thinking about with that. And this is, like, again, back to the, the serverless thing that I mentioned before. This is actually funny. I was prepping for a panel that I was doing at Velocity New York last year with Charity Majors, actually, and a couple of other great people. And I don't know if you can read that. Well, you probably can't read the suggestion. It's funny. Keynote suggested, instead of serverless, it suggested servers. And I was like, you're not wrong, Keynote. It's like, there are definitely servers there. And we're always going to pick a level of abstraction that matters for our organization and a level of abstraction that we're personally going to work in and care about. Like, I like opsy things, and I'm kind of baffled by CSS, And when we're working, on the DevOps Days website, like I'll be playing with Hugo and the static site generator and whatnot, and then, I can write some janky bash to do a bunch of stuff, and then I'm looking at the CSS. I'm like, Stratton? It's not that I couldn't learn it, I'm just not motivated enough, And there's some place that a lot of us maybe aren't racking and stacking servers anymore. And like, that's probably fine. It might make sense for your organization if you're high-frequency traders, and it makes sense for you to put some servers strategically located in the cage right at the colo, right next to the people that you're like, trying to trade with or partner with or beat on those trade games or whatever. Yeah, that might make sense, but in many people's use cases, it might not. You pick your degree of abstraction. Like, that's fine. It will make a difference to, again, like exactly what people are getting paged on. And, okay, so we'll talk about getting paged more in just a second, but I also should point out that like just reorganizing into 2 pizza teams is not going to necessarily make them have better conversations across team. Also, it's confusing because like, how big are the pizzas and how hungry are the teams? But anyway, yeah, we can talk about Conway's Law. I feel like people have talked about a little bit of this stuff. I would just say that like the communication piece is your secret sauce. Like that's how you make your organizations that are scaling work better. Brian Lyles talked in his talk yesterday about like your organization scaling to like, he works at a bank and they're really big and they have thousands of developers. And yeah, not every single person is going to be at every single feature meeting, but that doesn't mean that you can't have communication across those teams. All right. The Vasa talk that Pete did made me very, very happy, and he's actually going to give it at DevOps Days Minneapolis, which makes me even happier, because I love that lightning talk from 2014. And what this makes me think about, like the story of the Vasa has one piece that he mentioned in passing, that the shipwright died during construction, and I'm not sure if in this version of the talk he went into detail about the fact that the plans were actually all in his head, because that was the style at the time. And so like he literally dies and his wife and his buddy are trying to run the shipyard and trying to continue on his work. And because there was no documentation, they obviously had a lot of problems with the fact that everything had kind of changed in flight. And it reminds me that we have this culture of like, okay, we can patch this, we can get it working. There's definitely something on the 42-step checklist that's wrong, but we always skip step 17 and we do step 27 that way. And it's like I think every corporate wiki I've ever seen has something like that in it. And so that's why I don't think that like documentation is the solution. I think that being detailed at the moment of, say, committing the config, or at the moment of making the change in your source. Like being detailed about your rationale then it's a gift to future you. Because like 6 months later, you're looking at the config and you're like, why the F did I do this? And like your commit message says, like change the value of X. And you're like, I can see that. I just don't know why. Like put Y in your commit messages. All right, so in a perfect world, this, by the way, is not photoshopped. For some reason, the license plate of this Super Jeep actually did say yay, which, all right, and you're wondering, like, what exactly is perfect? It looks like, the ice planet Hoth. And my spouse, Joe, and I just celebrated our 20th anniversary by going hiking in Iceland. And it was delightful, and it was pretty much perfect. And, Super Jeeps on glaciers. And also hiking on glaciers and melting glaciers, because that's also happening. But I remember thinking, like, there is an ideal. And the ideal of what we all want in our workplaces is, like, well-documented and easy to debug, and maybe not paging us in the middle of the night, and not horribly broken all the time. That would be super. And sometimes it feels like we're kind of far away from that ideal. And reaching back towards that is important. Because like, I feel like, okay, from the point of view of, if you're ops people, and you would really like your dev teams to, say, be on call with you, I can tell you that at Drama Fever, my last day was 4 days after our Director of Ops' last day, and the two of us had the most understanding of our artisanal homegrown platform, and which, by the way, like, if somebody builds like an artisanal homegrown platform out of Docker and Packer and Chef and Bodo on AWS, and like a bunch of janky bash, don't believe that there's no janky bash underlying all of it. There totally is. But when we're trying to onboard the wonderful, devs who we finally realized, hey, maybe we should get more people into the on-call rotation. Okay, let's give them on-call boot camp because we're both heading out the door. By the way, don't wait until that crisis, and also maybe don't roll your own artisanal homegrown platform. This is our mid-roll, your plug for Cloud Foundry. It's open source. You should probably go check it out. You probably don't need to write all that logic yourself. But the idea of getting your devs on call, it does meet some resistance. But hey, in that perfect world, sure, everybody can be on call. It'll be great. But you can't just put people into your on-call rotation and be like, good luck, have fun, because that's not going to work out well, and they're going to be really sad, and your outages will probably be worse and longer. And so, like, obviously building the automation that you need to build, decontextualizing the like deeply specific things that aren't really documentation, and being open enough to share across teams. And again, if you're thinking, oh, but everybody is just one big happy team. Okay, that's cool. Whatever your org structure says, that's not the actual realities inside your org. Like your org structure might say so-and-so reports wherever, but there will be people who will talk to each other. There will be people who will get information from each other in ways that may not be on paper somewhere. And like building that trust between teams so that they'll actually tell each other what's going on is super important. Okay, so that's like, my advice to ops people. But this does not let devs off the hook in terms of building things that are actually operable. So building for operability is kind of tough, right? Like you need to have the observability Charity was talking about. You need to have debuggability. What we were looking at with like tracing. You need to have the reality is what I'll call it, but it's really just stop assuming the happy path. Like I think in many ways people get excited about their idea and then they get it working and then they want to ship it and then they want to move on to the next thing, or maybe the PMs just want them to move on to the next thing because it works for some values of work. And I'm like, day one is really short, day two is forever. Like you really need to think about the ways that it will not work too, and not just how it maybe sort of worked this one time. All right. And like I've used this slide a million times. This is the classic wall of confusion. I think Andrew Clay Schaefer used this at Velocity in like 2009. And I do remix it to that, because if you separate your teams into people who are they're incentivized in different ways. And this is not me saying put everybody in one team. I'm just saying you have to align everyone's incentives. Because if you have teams that are partying because of the feature they shipped, while another team is like, preparing for their week of hell, like what Alice was describing to us in her talk yesterday, like it's going to be really hard to have good dynamics between those teams. It's also going to be really hard to have, realistic amounts of support for each other's, initiatives and ideas. Like this is kind of, human nature, is if somebody else is, hey, I shipped it, it's fine, it's done, it's hashtag probably fine. If it ruins your weekend, you're going to be really against them ever doing that again. And whether or not you have the authority to stop them, it's like, this is actually, just yell it out. What animal do you see there? Exactly. Yeah, it's the rabbit/duck. Like it's one of those. There's a German philosopher from the 1950s is writing about this. This is a wood carving from like the late 19th century, because it's all about perspective, right? So I would say this is not that devs see things one way and ops see things another way, and so like one is right or one is wrong. I would say like we should, instead of saying, well, I'm on Team Rabbit and you're on Team Duck and I hate you, be like, we're all on Team Rabbit Duck. Let's like try to look at things from each other's perspective. Okay, so, all right, I feel like my laptop went to sleep and I don't want to sit here and unlock it, and I didn't start the timer anyway, so I assume I'm probably close to out of time. But a couple of just quick anecdotes from when I was on call. All right, the first time I was on call, it was a couple of exciting events like Y2K and the Salt Lake City Olympics in 2002. Y2K, we did not actually get paged because we fixed like, all the NTP and other issues, the previous summer. But the 2002 Olympics, we actually had the ops team just take shifts and stay up all night just in case. Because I guess it was kind of, I was working for Quest, and it was like a big deal as to whether or not, the network stayed stable. And so I remember getting a case of balls and like reading Usenet and playing The Sims all night just to stay up. And I mean, our server stayed up too. It's like they were Solaris boxes. They were pretty solid. Pour one out for sun. But like that's kind of, I think, a good example of just, hey, let's just throw some human misery at this problem because that'll make it better. And then like the next time I was on call, it was at a small ISP, and most of the times I got paged, it really didn't have a lot to do with our systems. I mean, sometimes it did. We had a news server that like the hardware was melting down, but a lot of times it was the colo customers who like needed to go visit their servers on the weekend, usually after I'd already paid cover charge somewhere, which was, upsetting. And again, like we didn't really have other teams we could farm that out to because like those weren't really environments we were doing a lot of custom dev necessarily. Then I worked at a university, and the CERN talk we just had was like, oh, memory lane. Like we used a lot of that same, that same stack. And the biggest difficulty there was most of our pages were environmental. And so you needed physical access to the data center to like go in and look at them, and then usually you had to call the building access people to have them come and like fix the water chilling that was leaking under the floor or whatever. And we did actually have developers who wanted to join that on-call rotation because they also wanted to run on the supercomputers. I didn't really trust them. I assumed it was probably for nefarious purposes. Like, they wanted to install the Git binary, and I was like, we have SVN, why do you need that? But like the point was that we actually had someone who wanted to help, and I said no because, well, I was a BOFH, and also like super low trust. I didn't think that they would handle outages the way I wanted them to. And when I worked at the ad tech place that I talked about last time, I mean I was the only person with an ops role, so everyone was on call. Pretty much everyone was on call. Super high trust. Variable ability. I still had a dev calling me at 4 a.m, when our HBase cluster got terminated by an EMR bug. That was good times. And then like the Drama Fever place, like we had, like variable abilities. So there were definitely people who could have been on call, but we didn't invest, as an ops team, we didn't invest in, at least until right before I left, we didn't invest in onboarding the people who could have joined the rotation. So it's like, it's a miss on our parts, but it's also like thinking about how you can level up the skills of other people around you. And at this point at Pivotal, I am not on call, but one of the things that's good about the way on-call works at Pivotal is we do have ops teams in Dublin, San Francisco, and Beijing, so we can do a follow the sun thing, and people don't have to be up in the middle of the night all the time. But another thing we do is have our escalations with like Datadog and PagerDuty set up so that the relevant teams are going to be the first to see an alert. If it's somebody, if of course stuff is architected such, in many cases it is architected such that the right person can be alerted, then you don't spend time having somebody act as a named pipe, a very angry named pipe, calling up the dev who could actually fix it. So that's where that's possible, I strongly recommend. And yeah, basically I think if you invest in your architecture and your observability and your culture such that you can split up on-call to put more people on call instead of fewer, and the more relevant people on call. And if you're thinking like, oh, but we're super regulated and like we have to have segregation of duties and all this stuff. I mean, like, yeah, you build that into your alerting logic so that people who can, through whatever the constraints of your org are, be on call are the ones who are on call. Okay, but yeah, this is Schaefer again, just saying, like, we keep talking about, containers, and we keep talking about all this stuff and, exactly how we deploy our code, but architecture and telemetry are what make a huge difference for being able to alert the right people who can actually solve the problem. Not just to be like, oh, now you're on call too and you get to be miserable, you're being punished. It's like, no, you just want it to go to the people who can actually solve it without it being a huge research project. So, like, I would say these implementations vary because it can vary based on like say, yeah, probably get you some cloud, get you some containers, get you some platforms. The implementation is something you can talk to a myriad of vendors or look at a myriad of open source projects for. But that, I think, makes a huge difference. And where am I on time? I'm sorry, I have no idea. I'm totally out of time. So I'm going to just say I have a lot of ridiculous slides. Wow, I can't actually go fast with this. That's weird. I have a lot of ridiculous slides that we don't need to talk about. I would say trying to have a good understanding of your environment, and there's lots and lots of vendors here that can help you with that, is super important. Because you can't alert properly if you don't know what's going on. And the way we did used to do this, ludicrous. And the way we're doing it now, James Turnbull wrote a really good book, The Art of Monitoring, that you definitely want to go check out. It's available, like, I think it's artofmonitoring.com. So, and yeah, if we're collaborating, and we're gonna say, by the way, if there's a sign, this is in Australia, there's a sign about like bird attacks on this beach, try a different route next time. And I was like, okay, we're already here. This is kind of terrifying. But I would say, like, if your culture has like known problems, just be adaptable and be ready to have those things inside your organization that you already know about, just change them. So this basically, am I saying this? Like, computers are easy, people are hard? And it's like, no. I mean, that's obviously totally a lie, right? Like, it's way, way more complex than that. But we can solve this. Like, I know we can solve this. And this is an episode of our podcast that Pete Cheslock and Charity Majors were on. You should definitely go listen to. It was after the whole left pad thing. And they were talking about, owning your own availability. And it is easy to look at all these cliches and be like, oh yeah, we have metaphors that will like solve all of this for us. And it's like, yes, I mean, no, not really. These are all ways of thinking about it. But I think the important thing that I want to leave you with is we're not going to solve these problems by throwing human misery at them. Like, that doesn't scale, because imagine if you're super successful and now you're going to just have more and more miserable people? Like, that doesn't work. So instead of volunteering as tribute, like, volunteer to invest in your organization's operability and, your monitoring and your people. Like, if you invest in that, like, you'll be so much happier. So that's it. That's all. There should be a comma there. That's the fatal flaw of not plugging my laptop in, which means my screen goes to sleep and I can't see anything. But.
Thank you, Bridget. All right, we have a quick break, so you can stand up, but then basically sit back down again within 2 or 3 minutes, because we're going to start the lightning talks, and you don't want to miss them. If you are giving a lightning talk, you also don't want to miss it. Please go over there, and I'll meet you. Okay, thank you for staying. Please seat. So we are about to start the lightning talks. We have 4, then we'll thank sponsors twice, and then we'll do 4 more lightning talks, and then we'll be done. And you will have sat through one of the more unique days of Monitorama ever. Yeah. So in order to keep us on time, I'm just going to get started. Remember, each speaker has 5 minutes. They'll be advancing through their slides. I will kind of creep awkwardly towards them when they run out of time, and as I do. And then we will move on to the next speaker. So a warm round of applause for Brant, our first lightning speaker.
Hi, everybody. Let me get used to this double system real quick. Oh. So I was going to have Google Translate read this for you because I can't read Latin, but the question is, who watches the watchers? The question of how people can oversee those that they've entrusted with power has been asked rhetorically for millennia. Whether as the primary intent or as a side effect, the systems we build now constitute a vast and pervasive surveillance system. Nations, corporations, and other entities track the actions and habits of private individuals at a global scale, and exploit this information to protect and expand their interests. Collecting so much data about virtually every aspect of the people who use or come in contact with our systems carries a substantial responsibility. The systems that we build and run can have serious unintended consequences for users, especially journalists, activists, and at-risk populations This concern is particularly urgent for groups living under authoritarian regimes or governments willing to use police and intelligence services to suppress dissent or to subvert democratic processes. You may recognize the chief of staff of the Clinton campaign here. So, who watches the watchers? The answer today is surprisingly concrete. We do. For the first time in history, really, there is a group of people that sort of stands apart from those exercising this degree of power and has some influence over it and can say what's happening and have our own say in how that plays out. To me, the risk is that we are sleepwalking towards a Black Mirror future. And so today, I'm saying to you that as the creators and operators of these systems, we must cultivate professional ethics and maintain practices guided by those ethical principles. We must continually consider the effects on our users of the data we collect and actively seek to protect those users in the design and the operations of our software. This spans political alignments. We may not all agree on who the chief threats are, but we can reasonably take away from the last year or two that the threats to our privacy and information systems are more complicated than Mossad and not Mossad, with all due respect to the great and infallible James Mickens, who on, well, I was going to say this stage, but our stage in 2015 said that there are 2 threat models, not Mossad and Mossad. So let me propose an update. Mossad is after you. Mossad is interested in you and your 1 billion closest friends, and not Mossad. I do not have all the answers. No one of us does. This is a call to action. As a community of practice, as information technology professionals, we must have these conversations here, at our conferences, and at work in front of the whiteboards with our colleagues. We must define our ethics as applied to protecting users and fellow citizens' privacies and civil rights. Noted radical Eric Schmidt agrees. He says, you have to fight for your privacy or you will lose it. So let us discuss. I have a few suggestions to this end to perhaps consider on their own for you to implement, but moreover, I'm just throwing these out here as something to spark ideation and seed the conversation. For example, TLS everywhere. The Snowden revelations revealed that NSA was observing traffic that Google thought was private and internal to their data centers, and they were quite gleeful about it. SSL added and removed here, hee hee. Let's Encrypt makes it quite easy for you to provision certificates for all of your hosts. And so inside of your VPCs in your data center at this point, there's really not a huge barrier to having TLS everywhere. This also has some other beneficial side effects, like for if you're doing a zero knowledge network or a Beyond Corp type deployment, that helps sell it in the business office. Include privacy and security concerns in your design review checklists. When you can't lose what you don't have to turn over. You can't turn over what you don't. You can't turn over what you don't have. Oops, I'm way behind. Sorry, this 2-slide thing is killing me. And I know I'm done. EFF has do not track. This is a great project that asks you to honor the user's intent to not track them. They also have the surveillance self-defense system, which is a bunch of profiles of different user types and archetypes, and the concerns that they have, which help you understand. But to that end, I want to encourage you to not assume that you understand your users' risks and security needs. If you have the resources, hire a sociologist, do the case studies, and find out. But I do recommend the research of some people at the end of here. Share your magic with your colleagues, especially your administrative staff. Show people how to use two-factor authentication, make it fun, reference Mr. Robot. Be brave, stand out. Don't wait for the big bad thing. It's going to be too late. Expect and demand more from your companies. Talk to journalists. If you're not getting what you need out of them, out of your company, and there's a real threat, talk to journalists, get it out there. And is this overkill? Maybe, but I don't want to find out that we didn't do enough when it's too late. It's in our hands. It always was. Thank you. Sorry about that. This really threw me.
Give it up for Brant. And next on the lightning stage is Logan.
Hi, my name is Logan. I'm an ops engineer at Kickstarter, and today I want to talk about optimizing for learning, or how I improve my memory to succeed in year one as an ops engineer. So, entering this field is really overwhelming, and I've identified one source of this overwhelming feeling. Ops is heavily based on expert intuition and experience. We had a couple speakers talk about this at this conference already. Experience takes time. I can't control that. However, I've decided to balance this disadvantage with something that I have slightly more control over, and that's learning and my memory. So I decided to give this talk because I realized that this is a challenge that everyone faces, and the faster that we can learn new things and connect them to things we already know, the more effective we're all going to be at our jobs, whether you're in year one or further on in your career. Oh, sorry, that's this. So the first problems on this job I experienced as an ops engineer, I felt like I was staring into an abyss. I had no idea what was out there. I was overwhelmed by information, and I didn't even know what questions to ask. But once I started learning just a little bit about this space, the dimensions of the area I needed to study, it became a lot less scary. That's because problem solving is easier when you have constraints. The more we know about the tools that are at our disposal, the faster we can recognize the constraints of any given project. Once you have knowledge, not necessarily expertise, you can start to ask these better questions. And when you have good memory, it allows you to be more creative when solving problems. So how did I learn about the things that inhabit the ops universe and give myself better constraints? The first thing I did was practice retrieval. This is basically continuous development and testing, but for your brain. So rereading material has been largely proven by studies not to work really well in becoming more familiar with content, but retrieving material or recalling it from memory is. So one example of something I do is low-stakes testing. When I learn a new subject, I make flashcards or just try to force myself to recall the material rather than going back to docs and rereading it. Another thing is reflection. After I learn about something, I always write up either a blog post or just some personal notes about what I learned. This is why doing retrospectives or participating in postmortems has been really helpful as a junior. It can be as simple as asking what went well, what can go better next time. So reflection is key. The second thing I did, which is like a little bit of a step up from retrieval, is I practiced building memory palaces, or expert-level mnemonics. I've used memory palaces to remember concepts around networking, HTTP codes, different Linux features, and AWS services. So you just take a place that you're already familiar with and put different pieces of information throughout that space, tying it to something really visceral or absurd. So I have a memory palace in my living room with tarantulas communicating privately to teach me different things about TCP. So once you've mastered those first steps, then you can begin to construct good mental models. So mental models are the result of an extraction process where you take key concepts from material you're learning and organize them. As we start to gather information about this ops universe and monitoring systems, for example, we're building up abstractions of monitoring systems that will allow us to design other types of systems that aren't exactly the same. So really internalizing lessons you learned and memorizing things about building your first monitoring system will allow you to better build systems that aren't the same in the future. Mental models, in other words, are what makes up expert intuition. So the final memory tool that's been essential over this last year is having and working with other people who have a growth mindset. So there's this 2010 study done on 5th graders by the researcher Carol Dweck, where she gave a bunch of these kids puzzles. Then she split them into 2 groups. After they completed the puzzle, she told one of the groups that they completed the puzzles because they were smart. The other half of the group, she told them they completed the puzzles because they worked hard. Then she gave them even harder puzzles. Kids who were told that they completed the puzzles well because they worked hard did significantly better than kids who were just told they were smart. This is a quote from that study. So many places to click. Emphasizing natural intelligence takes it out of the child's control, and it provides no good recipe for responding to a failure. Just replace child with ops engineer. So learning requires a lot of failure, and learning teaches us how to fail well. Ops engineering requires a lot of failure as well. My advice is to surround yourself with people who believe this. I am lucky to work with a team that praises each other for working hard to solve difficult problems and not for being naturally good engineers. Thank you.
Thank you, Logan. And up next is Christine.
Hello, I'm Christine with Honeycomb. Before this, I spent years at Parse telling people that our pre-aggregated analytics product was the way to go. This is my repentance. I have a real problem with pre-aggregated metrics. They're great in theory in a lot of ways. They're simple to add, simple to reason about. But I found that there are 3 main things preventing them from being an effective way of understanding your systems. The pre. Metrics that rely on pre-aggregation at write time work great when you can predict failure modes in your system and can track warning signs as metrics. And they're also great at making sure that reads are a simple swoop from disk. But they're terrible at answering new questions about your system. Let's pretend we have a brand new system. 4 lovely graphs, reads, writes, simple. Except then we realize that we do actually care about differentiating increments from updates, from deletes, and we care about which table they're writing to, and averages and P95s are great, but more percentiles are better, and sums are the way to understand the total load on our system, so then our graphs look more like this. And relying on pre-aggregated metrics means that we're always constantly constrained by what our past selves thought would be useful, and having to guess what future us might find useful, possibly. And so we can see how we end up in a world where this is our mode of debugging, where we're biased by the graphs that are in front of our faces, and each postmortem adds a metric or 3 or 10 to our dashboards. they aggregated. Besides the model of pre-aggregation fighting us, the implementation does too. By now, enough talks have touched upon the fact that time series databases struggle with high cardinality data sets. Why? Because they all rely on the same system for storage, or the same process for storage. A multi-dimensional set of keys and values comes in and says, I'm interesting. It gets broken up and sliced apart to increment a bunch of discrete counters. This storage strategy, while it's super efficient for talking about high volumes of predictable, constrained data, really relies on that set of metrics being countable and storable by the storage system you've got to store it. And once your requirements cause that number of metrics to start increasing, you've got some hard choices to make. Note that lots of modern time series offerings implement these attributes as tags. I have a dot syntax up here. Tags offer more flexibility, but the storage constraints are the same, so stay with me. When your storage volume is tied to the number of unique metrics, like a couple of talks illustrated yesterday, tied to the number of unique metrics, not like anything you as ops people are hardwired to handle, like something reasonable like total volume of traffic or number of errors. It's so easy to cause some serious stress on your time series storage. And for those of you out there thinking, but we'd just be careful about it, my team's never going to run into this problem, I feel like if it can happen to the fine folks at Netflix, it can happen to any of us. And sometimes it's a mistake. You accidentally included customer ID. But sometimes it's also just reasonable to want to track some other additional attribute, build ID, container ID. And either way, this should be possible, not something you go wag a finger at another team about. Being able to isolate a single segment's traffic and still get the same averages, percentiles, and breakdowns really lets you drill down and understand how any single terrible segment of your traffic can impact your system as a whole. And third, the metrics. These single measurements at a point in time are awesome. Simple to reason about, simple to add, like I've said. The problem is just that. They're individual isolated dots in the big picture of your system. You, by being here at Monitorama, are probably already pretty good at knowing that if something looks funny in one graph and something else looks funny in another graph, there's probably something interesting in the cross product of the two worth investigating. But debugging by eyeballing means that once we've done this breaking up of our wonderful multi-dimensional bag of keys and values into metrics, you lose the ability to reconstruct reality and be like, well, what about, I just care about that part. Why is it deviating from the norm? Why is it changing? I just want to look at that. So, the problem rephrased. Oh, God. We couldn't anticipate this particular thing beforehand as a trouble spot, so we weren't prepared. Even if we had, we might not have had the storage to be able to track all of those cross products anyway. And now that we've identified that there was something interesting here, there's no way to poke any deeper to try and identify the context of what actually happened. Thanks. And if anyone disagrees with me, please come find me afterwards. I'd love to talk. I'll be around.
Thank you, Christine. And to wrap up our first round of lightning speakers, we have Eben.
Hello. Can everyone hear me? Oh, cool. All right. So one seemingly inescapable theme in observability is that a lot of instrumentation is added reactively. First you fix something, and then you add the instrumentation that would have told you why it was broken in the first place. And the difficulty of measuring things is exacerbated when you're trying to better understand third-party software, be it a library or a database that you have to operate or something. And it's especially hard if the thing that you want to observe is the operating system. And you're looking at system aggregates and you're like, network I/O is higher, is that bad? Well, shit, I don't know. So when it's hard to get the data that you need, some pathologies are likely to arise. Weird stuff goes unexplained because it's simply too time-consuming to investigate, and you end up basing your investigation around the data you happen to have at hand, not the questions that you really want to ask, which is not ideal. So the future is arriving, but if you refuse to accept the present, there's still a place for roll up your sleeves, SSH to the server, no holds barred, I don't care how, just get me the data I want investigation. And I think that perf today is the most practical toolkit in your toolbox on Linux for that task. Perf is like the OG event-driven debugging tool on Linux. By that, I mean, instead of showing you predefined summarized metrics like Christine was complaining about, you choose which events to trace, and perf will record them for you, optionally preserving context such as process ID, call stack, and function arguments. So perf does a lot of different things, but what I want to highlight is perf's ability to trace, record, and count. So let's ask a simple question. Which of my code paths are issuing the most MySQL queries? If you don't already have this instrumented, well, you probably should, but it's also probably kind of a pain to do. You have to patch your database driver or wrap all your database calls or capture packets and reverse engineer where the queries came from. So we can use perf to insert a dynamic probe point at a function of interest and then trace all calls of that function along with their call stacks, put it in a file, summarize. Oh, hey, look, this is a bottom-up graph of calls to our query method. I mean, we can see, okay, 44% came from here, and 3/4 of that came from here. And, oh, hey, this is interesting. Fetch sample rate, get sample rate, fetch sample rate, no cache. Why not fetch sample rate? Yes, cache. That's no good. Hey, what's the cache hit rate anyways? We're not measuring it. Well, crap. So let's measure the cache hit rate. So we're going to count all calls to fetch sample rate. Those are our calls that might hit the cache. Fetch sample rate, no cache. Those are the ones that miss the cache. We'll summarize at 1-second intervals for 30 seconds. Look, numbers, that's a metric. A metric is just a bunch of numbers. I have a math degree. That's what I learned in my math degree. Awk magic, 89.9%. That's a statistic. Awesome, data-driven. This is terrible. This is effective. Perf, investigate, iterate, explore, try perf, ask more questions. Thank you.
Holy sh... Thank you, Eben. Thank you to all of the first round speakers. Let's thank some sponsors. Elastic. Hi. Come on up. And while Elastic is coming up, can we get a huge round of applause for our VJ, Ryan McKern, who's been VJing madly?
Where do I aim?
Right at him.
Okay, got it. Thanks. Whew, I got my workout done. So, thank you guys for having Elastic. Thanks, Monitorama. My name is Boyan, and I'm a senior product manager at Elastic. And let's make that work. All right, so I know there's been a lot of talks that says monitoring is dead. We hate monitoring even, but let's be honest. We're all here because deep down, way down somewhere, we all love monitoring, right? Yeah? Woo! And obviously, thanks Monitorama for hosting an amazing conference here. Portland is amazing, beers and coffees and the nature and everything. So personally, that is very much my career trajectory. I was a developer building a monitoring management alerting tool for a database system. And now I am a product manager at Elastic focused on a number of different expect features, including monitoring. So I heart monitoring. I want to ask you guys 4 questions. Any one of you using Elasticsearch today? Whew, wow, I didn't even have to ask. Raise your hands, please. Thank you. If you guys don't mind holding your hands up, I apologize. Anybody using Kibana? Cool. Logstash? Beats? All right. Thank you, guys. I don't have a cool spectacle, but I just captured all of that with my eyes. I monitor. All right, so just want to talk briefly about what we do as a company. Elastic is a company founded in 2012, and we are a company behind 4 open source popular projects, including Elasticsearch, Kibana, Logstash, and Beats. And we are here today because a lot of you and also many, many other users in the world are using the Elastic Stack as part of the monitoring solution. So what you're looking at is a beautiful Kibana dashboard that is monitoring something. Somebody else built this beautiful dashboard, and I'm just using it. But a lot of you probably also know us by ELK or Elk Stack. Yeah, I see some nods. That is an incorrect name. Sorry, as a product manager, I have to iterate this. We relaunched or rebranded ourselves as the Elastic Stack at last ElasticCon, February 2016. And the reason is, well, a lot of different reasons, but one of the reasons was we joined forces with Beats, which is a lightweight data shipper written in Go. And it's been contributing to a lot of different use cases, and one of them most notably monitoring. So some of you might have heard of TopBeat, MetricBeat, Heartbeat, FileBeat. There's a lot of beats out there, and they're all community beats out there, and it's awesome. So we just couldn't continuously adding one character, syllable, whatever, to the Elk Stack or ELK. Otherwise, it would have been like Elkbeat or Belk, and just didn't work out. So it's Elastic Stack. And how we stay in business, we're an open source company, so we have to make money somehow. And we do that by providing support as well as subscription levels. So we have XPack, which is our commercial products. And you might wonder, well, so I use the Elastic Stack for monitoring my infrastructure, but I think in one of the lightning talks earlier, who's monitoring the Elastic Stack? Well, we are. Thank you. Appreciate it. Who's watching the watcher, or who's monitoring the Elastic Stack? So we have XPack monitoring, which is free. So you should anybody who's using Elasticsearch or any of the open source projects in our Elastic Stack, you should go download it. All we ask for is your email address and your home address, your social security number, and your annual income. No, we don't. Please don't come and sue me or the company. No, we just really ask for email address, and that's all. And that's mainly to keep you guys posted on any of the improvements that we make. But it's free, and it's incredibly important because thanks to, again, another lightning talk, and I apologize for not remembering all of your names, but raw metrics are incredibly important, right? So without the XPack monitoring, let's say you're running Elasticsearch on an Amazon instance, you won't have all of the raw metrics that you will need to be able to detect problems and get down to the root cause. And earlier this morning, we had a talk about how to find anomalies and how you shouldn't create alerts based on any anomalies. So very, very recently, actually on May 4th, May the 4th be with you all, we released a machine learning beta in our 5.4 release, and it's basically an anomaly detection, unsupervised machine learning that comes with the context, which allows you to properly monitor anything that's going on, whatever data that you have running in Elasticsearch. You can use our XPack feature called machine learning to be able to detect anomalies. And what's really neat about it is you can even create multiple machine learning jobs, and you don't have to be a data scientist or anyone with, I don't know, a PhD. Clearly, really clever people with the PhD degrees, but you don't really need one to be able to run the machine learning jobs, which is really neat. And you can combine those jobs to look at it from a holistic level and not just in a narrow scope, which gives you even more context. So this is my last slide. Thank you guys all for listening, but please join us at the meetup tomorrow. We're going to be at WeWork, which is a little far from here, but I suspect that most of you guys are staying around the Armory, maybe. Hopefully you guys didn't lose power. But we're gonna be at WeWork. We're gonna start eating and drinking at 6. The talk will begin at 6:30. Our monitoring lead is here, and he's gonna talk about how to effectively monitor your Elastic Stack. And I'm also gonna talk, sort of more deep dive about machine learning and other things. So please join us. I'll put this in Slack, but thank you all.
And our final sponsor of the day is ThreatStack. ThreatStack.
Sweet, Alex. Oh, excellent. Oh, God. What did? Oh, did you? I DM'd them to you on the Slacks. So as it turns out, I have a wonderful marketing team. They use Microsoft PowerPoint for reasons. And they sent me over a deck with some wonderful screenshots. This isn't counting to my 5 minutes, is it? Oh, okay. Oh, hell yeah. I have beautiful pictures. And so, running PowerPoint is hard. So anyway, I'm Pete Cheslock. You might remember me from talking about ships. I'm not going to talk about ships right now. I'm going to talk about stacks of threats. I work for ThreatStack, and what we are is wow, you really have to be right here. We are a cloud security company. We have a cloud security platform that you can use to help monitor your systems, identify internal and external threats, identify data loss, and help you meet compliance needs. The first question I like to ask, just because I'm just really curious, I've been at ThreatStack for a long time, who here has heard of ThreatStack before? Just raise your hand. That's awesome, because I was there before we launched and no one knew who we were. Also raise your hands, because I know there's a few customers and it'll just make me feel good. If you purchase, own, like if you're a ThreatStack user, that's awesome. So yeah, thanks, Will. Cool. So anyway, for those of you who have not heard of ThreatStack before, we have the platform that can really help you understand what's happening on your systems and understand as well if you're running on the cloud, if you're transitioning to the cloud, and give you a lot of useful info on there. So we've got kind of 3 different levels we'd like to talk about, a journey that you go on in security. So I am not really a security person. I came into ThreatStack as kind of security dumb. And I learned a lot about security while at ThreatStack. And so when we talk about cloud security to a lot of companies, it's kind of an afterthought that people add on later. And so we like to talk about the stages, an audit stage where you just want to understand what's going on, and maybe you have compliance that you have to hit, make your auditors happy. Monitor stage is, we're at a monitoring conference, you want to know what's going on. And then in the investigate level is really trying to dive deep and understand, who did what when. So we've got a lot of awesome customers. A few of you are in this room. Thanks a lot. And they use us for a lot of different reasons. So one of the things that we can do is in the audit world is basically give you some high-level info to inform you of what's going on in your environment right now. So if you're an Amazon user, we can tie into your Amazon account. We can give you information about if you're meeting CIS benchmarks and Amazon best practices. And we can give you some high-level information as well about your systems. If you're running Linux and Windows, we have vulnerability management for your Linux systems with Windows support coming pretty soon. We can give you information about, the coverage that you have in your system. So if you're running 900 something servers in Amazon and you only have a few don't have the agent installed, we can give you that information. And again, give you kind of some high-level information about just what's going on. What you can then do is then drill down into some specific information. So if you're scanning using our config audit, your different Amazon accounts, you can see kind of what score we give you a percentage to figure out how well you're kind of doing against benchmarks. And so, if someone adds a new account, I actually had this happen where someone added a demo account and the score went to like 50%, and then it turns yellow, and I don't like that because it's got to be 100%, it's got to be green. And so I was went through and I'm like, who did this? And I was able to find out, oh, well, they added some new account. It's a demo account. They're taking some screenshots and going from there. So, but if you think about, as companies move to cloud, they really have a hard time understanding who's doing what. Someone scans a credit card and it's off to the races. And so being able to just scan after the fact to give you an idea of where to start is where we try to help. You can give me like a minute when I know what's up. I'm not tracking my time at all. We can also inform you. We have integrations with Slack and PagerDuty and webhooks. We can send you email notifications if you're one of those masochists who love email notifications. And when we do send you a notification, you can then log into the application and understand basically the series of events that occurred. So, in this kind of scenario, you can see, some login failures happening, a potential web exploit. Basically, if we see your web server spawn a shell, it's probably not a good thing. If we see kernel modules installed, that's also not a good thing. And then we even have threat intelligence integration. So then if we see these connections out to third-party places, we can inform you of that. What we could also do is tie it in, and we call it cloud context, seeing what happened before and after an event occurred. So I've used this not even necessarily from a pure kind of security, oh my God, we got hacked type of response, but we'll have notifications fire into a Slack channel. And this one time an engineer was like SCPing files around, and I'm like, hey, is our CI build broken? Like, why are you copying Java file, jar files around? And it was like, oh, I'm just trying to test something. And it's not necessarily a security issue that we were writing into, but it's trying to instill good operational practices that actually will make you more secure later. One of my favorite features is the TTY timeline of being able to see actually what people are running in interactive sessions. And this one really is like the get blame of your infrastructure because again, not even as a security tool, but like something went down and you start asking like, hey, like was anyone logged into DB Prado 1? It's like, nope, not me. I didn't touch it. It's like, well, hold on for 1 second. I will find this out. And then you can go through and basically see everything they've done there. And then, like I said, we tie into Slack integration. We can tie into your chat systems. One of the really cool things is we started off having all the alerts going into Slack, and then we'd start adding you and be like, hey, was that you? Did you just do that? And now our engineers preemptively will go in and just say, hey, I gotta grab some telemetry data off this server, and it's like ding ding, and then they go from there. And then you can go through and basically try to find patterns that you want to avoid. If your developers are like, hey, we're going to use this kernel module to do this whatever, you want to understand what they're doing, and you can't always see the changes. And if you're in this DevOps world and continuous deployment, being able to track and understand and answer that is helpful. And then, we've got some nice graphs. We can show you frequency of events. We can show you different system calls that are firing and, being able to track that back to what the original process fired. So, and if you like Jira and you need to track all this stuff, you can fire these webhooks. You can integrate into Jira and, have a whole chain of, kind of chain of command on the events. And then we can tie in for vulnerability management. We can understand what AMIs you're running and, are your AMIs, am I running out of time? Yeah, I'm out of time. So I'm out of time, but, check us out. I have a lot of, wow, way too many slides. You can go to the site. I didn't bring any t-shirts with me today, but you can actually go to this link and fill out some info. Configuration audit is a free service you can sign up and just try anytime. And if you head over this link, we'll send you one of these cool t-shirts as well. So thank you.
All right, the vendors have so many features that they need more time. All right, so we are going to have our final lightning talks, and then we're done for the day. The Sensu and Grafana folks asked me to mention, don't throw out your badges. If you want to go to any of the after parties this evening, the badge will help you get in. So keep wearing it. Cool. To start off our final round of lightning talks, we have Joe.
Okay, I'm Joe Gelati. I work at LinkedIn as an S3 on the monitoring team, and I'm going to talk about how we scaled notifications and alerting using Iris. So before we built Iris, our SolarWinds engineers would escalate manually to SREs and SWEs when a human was required to work on an alert. And that didn't scale once we had more engineers, more people, and more services, so we had to build something to automate that. So that's when we decided to build Iris. What is Iris? Iris is an app that handles escalating to people automatically in its specified orders. It's customizable, and it has a REST API, so you can hit it to say, make an incident using this plan. And it interacts with Twilio for SMSs and calls, Slack and Gmail. In each of these mediums, you can claim incidents by clicking buttons in Slack and Gmail and just typing numbers during the call or during the text. And for incident management, this is the plan editor, where you can choose the order in which different teams and people are called. In this case, you can see that first, it's going to text the on-call of this team 5 times. You can't really read it, but if you could, that's what it shows. And after that, then it would call the person 5 times. If they still hasn't picked up the alert, then it would call their manager. Yeah. And this is the incident view, how you can see the graph that was shown with the incident, as well as a list of messages that were sent, and buttons to claim and unclaim, and so on. And this is the message view, where it has the message that was sent, who it was sent to, and when, and the Twilio status, in this case delivered. Twilio can fail for various reasons, and they'd be shown there if this were to fail. And as a user, you can customize how you receive escalations. Usually, you'd have urgent set to call and low set to email. And then to choose who's on call and when, we built another component called on-call. And this lets you create customizable calendar events for determining rotations and on-call rotations. And this has a REST API. And that's how Iris decides who's on call during the plans. And to create a roster, this is the UI for that, how you can easily make new rosters, add team members, mark them in and out of rotation, and then remove them afterwards. And to make an event, you can click and drag using the simple UI, but that'd take a while, so we also have an automatic scheduler where you fill out a form using the time zone information, you click populate, and then it will fill out all the events you need for you automatically. Iris and on-call today. So over the past week, roughly 2,800 incidents were created. We sent roughly 1,900 calls and 3,500 text messages and 37,000 emails to roughly 700 people. And for our on-call, we have around 600 rosters and 3,400 memberships. And this is in use by all teams at LinkedIn, and it's people are happy with it until it calls you at 2 a.m. And it's completely open source and free. The code happens all on GitHub. And you can go to those 2 links on the top to easily get information. Like if you go to iris.claims on your phone, you can see a landing page for it. And that's all I have. Thank you.
And up next, we have Max.
Hello, my name is Max. I'm an SRE at PagerDuty, and I'm here to talk to you about DNS metrics, which is monitoring DNS as a service providers. And to start with DNS is basically the phone book of the internet. If your DNS is not working, then people cannot find you. And they see your service is down, so it's really critical. You might want to run it yourself, but turns out it's actually hard. You need to massively over-provision it, and you need to monitor it fairly closely because it can be used for not as great purposes. So there are companies that will be, so you do not want to run it yourself, basically. And there are companies that would be very happy to take your money and take care of this for you. But those companies, since DNS is difficult to run, they can also have issues. I did some research evaluating some providers. And here's what I found. Some of those are infrastructure failures. Some of those are denial of service attacks on those providers. But the fact is, even the big players can occasionally have issues. So what can you do? One thing you can do, you can run both. You can run more than one provider. But then you run into an issue that brings me to this conference, like, how do you monitor those? Sorry, skipping slides is hard. Yeah, so how do you monitor? Each one of those has consolidated panels that you can look at and see what is happening across that provider. but also you have a panel per zone. And also, if you have more than one provider, they will have their own panel, and they will have their own panel per zone with different metrics, different scales, different types of output. And when I need to look at so many pages to see what's happening with my DNS, it makes me sad. And this is how DNS Metrics was born. And here's what it does. It polls each of the providers using their public APIs. It normalizes those metrics into a standard StatsD interface, and it sends those into your monitoring solution of choice. Your monitoring solution of choice then can decide to alert you, for example, using PagerDuty. And this is what it looks like in Datadog, which is what we use for this. Some of the charts that you see that are most important for us are the total usage of DNS across all of our providers and zones, and the share, so how do the providers split, how does the traffic flow from different providers is separated, and the status of our zones. Generalizing a bit from DNS to things that are more broadly applicable, I would like to tell you to monitor your service providers. Don't just monitor the stuff that you write yourselves, monitor everything, and in a way that makes sense to you, not necessarily just in a way that those providers give you by default. And the 3 points here are aggregate across different providers and kind of see the splits, because each provider will only have their own view. Surface the metrics that matter to you. Many of those providers have tons of metrics, but only few of those are actually critical to you. And try to have one screen of key indicators that would tell you if your service is working or not. And the second point is demand good APIs. You can demand good APIs from vendors. If you ask for them, they will come. If you ask for them before signing the contract, they might come sooner. And I have an example here for something that could happen. Let's say you want to find one particular data point. If this data point is directly accessible using an API, then it's very easy. But if it's only available as a part of a big analytics report, then you need to fetch that report and extract it. So when I'll be writing that extraction code, I'll be pretty sad. And when I start hitting that endpoint every single minute to get my single data point, the provider will be sad as well, and everybody will be sad. Don't do it. Thank you, that's it. This is a location of DNS metrics, and we have a Docker image for you to try this easily as well. Hit me on Twitter, hit me on Slack. I'll be glad to tell you more about it. Thank you.
Two left, two left. Tommy, come on up. Round of applause for Tommy.
Slides? Oh, nice. All right. Hi, everybody. My name is Tommy Parnell. I go by Terrible Dev on GitHub and Twitter. You can find me at terribledev.io. I was told that I should update my profile picture in these slides because I recently grew a beard. So just in case you find me around, that's really what I look like, not that, okay? I work at Vistaprint. I don't know if you've heard of Vistaprint or not. We sell mostly business cards and promotional products to people. They customize the products in their browsers. We do about $1.5 billion annually in printed goods. And when I tell people that, they believe the office looks kind of like this. But honestly, actually, like, we really love our customers. Our customers are like core to Vistaprint, but they're not like the most tech-savvy people. They're, you know, very resilient to a lot of changes on the internet and UIs, and we're clearly a design company. This is like one of the pages in Vistaprint. It's called Gallery. It lets you look at specifically business cards and different templates we have to offer you. We have this search box in the upper left, and if people use the search box, they will more than likely convert. They will definitely check out, which means that we want a lot of people using that search box. So one day we just decided, hey, let's just make that search box bigger, right? Like, it's a good idea. It's not that many more pixels. I'm sure nothing bad's going to happen. But it turns out that when we have a larger search box, we actually lose customer interaction in search. I don't know how or why, but that's definitely a thing. And when we lose customer interaction in that search box, we actually lose money. And it just makes me like, I just can't believe that that was definitely a thing. So how do we go from a UI like this to a UI much more like this, which is clearly extremely different. It honestly is, actually. Changes to our UI can be very costly. It can be very costly to the business. But so can writing features. Developer time is very expensive. We get paid a lot of money, and it's takes a lot of time to develop features. So we initially started doing a lot of A/B testing. We would write a feature, we'd just kind of hack it together, and we'd come up with kind of like a hypothesis, and we'd do a test on it, and then we'd do another test and another test. Pretty soon, our code looked more like this, where if you're in a test, do something else, do something else, do something else, else. And this was me working in the code base like every single day of the week. It was like basically impossible to figure out where a customer is going to land, what their experience would look like. So around this time, we were really going to the cloud, and HashiCorp came out with this awesome tool called Terraform. And Terraform really lets you make a mutable based infrastructure. And so we came up with this cool idea where if you want to make a new test, you just make a new Git branch, and you kind of like hack your feature together. You push it, and basically you get a whole new environment inside of AWS. We can then immediately expose our customers to the test without having like if-elses all over the place. And then we can obviously compare a lot of the data that is gathered in that test with the control environment or like the regular branch. So we do a lot of like monitoring of our customers' experience. We use like an in-browser statsd just to make sure our our JavaScript is running efficiently. We log a lot of customer interactions just through some custom code that we have. We use things like Adobe Analytics and Telium. And we just check out a lot of our checkout data. So like, are people converting? What's their click-through looks like? What's their shopping cart look like? Are they abandoning their shopping cart? So we end up with this giant pile of data. And basically, we make an R-based spray bottle that I don't really know what goes on. But out pops like actual information that then we can like make a determination on if a test is worth keeping or not. And if it is, obviously, we then like do it better. What we try and do is we're just trying to figure out like how our customers are working with the site, like what the actual story looks like for them. So in short, we can run multiple tests at the same time with like immutable infrastructure. And we know like before we really build the feature if the feature is going to make us a lot of money because we can kind of test it in these alternative environments. We're like able to rapidly iterate over the test. So if, let's say, the search box was too large, maybe we can cut it back a little bit, cut it back a little bit, keep looking at the data, keep reiterating over and over again without affecting like our main environment, like our master environment. And finally, we really know when we've delivered value. We capture a lot of data of how people interact, and when we like really make these features properly and they go to production, we can really see it both with revenue, but also just with how people are interacting with our UI. Thank you very much.
Thank you, Tommy. And we have one final lightning talk from Don't go, because we're going to have something to share with you right after Scott finishes.
Who's thirsty? Awesome. One of our Windows engineers recently described our DevOps journey as a vacation your mom planned to the amusement park on the hottest day of the year. That's the trip you learn that one of your neighbors is really weird, everyone is going to eat way too much junk food, and everybody's going to throw up in the car. But you're really glad that you went on the trip, and for the rest of the time you have that car, you know where to look to see the stains to remind you of the day. A lot of definitions for chatops. A lot of times we talk about chat bots, chat clients, et cetera. For us, it's really about collaboration and people. A few weeks ago, we had a team builder. We were also in the middle of a pretty major storage migration, so rather than miss the event, this engineer wrote the tooling and telemetry to be able to manage and monitor the storage migrations. A change agent is anyone that helps an organization transform by improving business processes or interpersonal interactions. And so chatops has arguably had more of an impact on our DevOps journey than any other single idea. So the question is, are you putting your bot in the corner? Chatops is really good at onboarding new members. So bringing new members onto your team or new teams, They can observe how you interact. They can become familiar with internal customers, peers, and services within your organization. Our last 4 new hires all developed and deployed a chat script on their first day. That's an idea that we stole from Etsy. The great thing about having new hires deploy on day 1 is that we reinforce how excited we are to have them on the team. In addition, they feel like they're already contributing. To make onboarding easier, we developed a process that creates copy scripts by wrapping PowerShell. This helps team members get up to speed quicker as it abstracts the complexity. Engineers move on to CoffeeScript when they need more features or control. And chatops is a gentle introduction to our technology stack. As they commit their first script to our CI pipeline, we can discuss CI/CD, DevOps, and other concepts relevant to our environment. Has everybody heard of Game of Thrones before? It's this really cool show. All of us have friction in our organizations. It could be due to silos, processes, or policies. Hopefully, no one works with people like the Lannisters, though. In Westeros, they use ravens for messaging, which are pretty unsuitable for chatops. They're undocumented. There's no monitoring or alerting mechanism. They're not transparent or interactive. They're really not immutable. And only maesters have admin privileges. And it's a fundamentally unscalable system with high latency, low context, and really susceptible to man-in-the-middle attacks. Luckily, our systems today can address most of these issues and can be a catalyst to help expose sources of friction in your own organization. Before chatops, it was common for one of our engineers to run around to everybody's desk to help them to troubleshoot their PowerShell implementations or Ruby gems or who knows what. When we moved to Artifactory and chatops, that really gave us a lot of stability and helped us to gain momentum. Chatops is that shared console that really lends itself well to a crawl, walk, run approach, and you can really think of it as training wheels for your team. With chatops, you see the stimulus, the discussion, the action, and the outcome in a nicely threaded manner. It's encouraged more decentralized execution with much more responsible outcomes, and teams are more engaged and empowered. Also, it can help you to discover new cross-team interactions and new patterns of collaboration you haven't thought of. We're at Monitorama, right? Okay, let's have a demo. So here's some chatops going on. So in number 1 and 2, that's our implementation of Grafana. Number 3 is a Sensu implementation where we're looking at a smoke test for an application. Number 4, we wrote a VPN saturation monitor to be able to help us on a snow day in Portland this year. And number 5, our SAP basis manager wanted to understand landscape health, so he wrote his own thing. And as we accelerated our chatops practice, it's encouraged more scripts to be created and shared. And at this point, we have more than 200 scripts spanning all major technologies within the enterprise. New scripts are being checked in almost every day. And as every script gets committed, it increases our organizational knowledge and reinforces culture, automation, measurement, and sharing. And hopefully you'll agree that chatops can be a change agent within your team. Thank you.
All right, thank you for staying. So we have some news to share. To share that with you, I'd like to bring up the PT Barnum of monitoring, Jason Dixon. And he won't say this about himself, but he spent all night making sure that today could happen. So thank you, Jason.
Okay. Where to start? All right, let's get the easy business out of the way. Sponsor parties, we already mentioned those. Okay, so Sensu sponsor party at Pearl Tavern and the Grafana Lab sponsor party at Ground Control. Okay, now the hard business. So if you haven't seen me in the last couple hours, it's because I've been riding around on the Bikey Town. Sorry, Ryan. Bikey Town, Bikey Town Orange Bikes, looking at potential venues for tomorrow. As we learned last night, it's better to have a contingency plan in place before you go to sleep than after. So anyways, I've been meeting, there's a venue called Castaway, which is about 10 blocks northwest. Really nice place, sits about 450. Meeting with the ladies over there, we got a contract in place. So we have a venue for tomorrow if power doesn't come back. However, power's back. Hot showers in the morning. Thank you, everybody. Looking very forward to seeing you all in the morning or at the sponsors parties tonight. Have a great time, and thank you again for coming.